Test. Testing 1, 2, 3. 1, 2, 3. Testing 1, 2.
Good morning, folks. We're just doing a few last-minute audio tests, and then hopefully we should be getting started with the conference over the next 20 minutes. We have our keynote coming up at 9 o'clock, and that'll be definitely our hard start. So enjoy the coffee, enjoy the drinks, and we'll be back with you as soon as technology starts cooperating, which could be 2023. One last second audio test.
This is a continuation of the audio test. I'm going to try it from out in the corridor here. If Derek can hear me, then that will be positive. I'll try walking over here. I could recite some. Sorry? It's coming out a lot. Should I try again? Hello? Okay, excellent.
continuing to... Oh, it was fun. Continuing to check audio. This isn't going out to the house anymore, so it's probably changed links.
Do you know how much internet is directly set aside for my connection? It's just saying the connection's kind of slow.
So it is the same mic, but that board is no longer included in the audio link.
Yeah, I put it
Okay,
back in
so it's
my...
back in the original. And I can see that the audio is landing into our laptop. Welcome to the Vitac Captioner, by the way. We are just working through our audio on this end. The conference won't start probably for another 13 minutes. I don't know if you are joined on the chat at all, but we will look for messages there just right now. And I'm not sure what the other method of you getting in contact with us is. But I can hear it coming out of my phone, so it's definitely going out the Zoom link.
Somewhere. It's like it's general.
This is the GNU Radio conference trying another audio test. Also looking to see if this is going out over the caption text. Could you please give us any feedback about the audio quality? This should be pretty standard for the event. If somebody could please let folks in the hallway know that we'll be beginning. I think that the room should fill out slightly more. Grand. I'm getting the thumbs up from the back of the room that I might even be coming over video to the live stream. Let me unmask myself. Mysterious man at the front. Hi, my name is Derek Kozel. I'm president of the GNU Radio project, and I'm very, very happy to have you all here in person and virtually. This is off to a good start, of course. We've had a few audio issues, but it looks like those are now resolved. So hopefully the rest of the event will run pretty smoothly. We are a few minutes behind, so I'm going to launch straight into our first keynote, and I'm going to hand it off to Josh Mormon, maintainer of the GNU Radio project, for a quick intro. And if you could please come up and get your laptop running, we will get going. Thank you very much, and there'll be a much longer introduction from me after the keynote.
All right, thanks, Derek. All right. So welcome everyone to Charlotte, and our theme this year for GNU Radio is speed, faster processing, faster signals. And to tie this in, NASCAR, Charlotte is the home to NASCAR, many of the NASCAR teams. And with us, we're pleased to welcome Mark Bringle, who works for the Joe Gibbs racing team, one of the premier NASCAR teams. So he's been with the organization for 25 years, began as a manufacturing engineer, and is now the marketing director for Joe Gibbs Racing. So he's going to walk us through what it takes to build a race car and what that experience looks like. So I'm going to hand that over to Mark, and thank you so much. So you don't need this.
Yes, am I good? Yep, very good. All right, thank you. Well, I'm pleased to be here with you guys today. The Charlotte area is the home of just about every NASCAR team. We have one that's about an hour away, but you're within about 30 minutes drive of just about every team that's right here in the area. I'm looking around to make sure we don't have any Hendrick or Penske spies in the group. So y'all looking pretty good. You got the mask on, so you can hide pretty easily. But yeah, so we're going to get started. I currently hold two positions right now with Joe Gibbs Racing. On the marketing side and sales side, I'm the technical sponsorship and marketing director. And then we've launched a few new companies within the organization, and so I'm the managing director for Joe Gibbs Manufacturing Solutions now. Now, how many people have no idea anything about NASCAR? It's okay, raise your hand. All right, perfect. So this presentation is for y'all, because I'm going to take you from the very beginning all the way through the entire series. We're going to talk about Xfinity Series, ARCA Series, Cup, what all that is, and then actually what it takes to build a race car, and what do we do with that. So let's get started. All right, so NASCAR started back in 1947. You wouldn't believe this, but it was created mainly from moonshiners. Whenever they would have events, like at local fairs, things like that, the moonshiners already had their cars souped up to outrun the law. So obviously they'd come down out of the foothills of North Carolina mountains and enter these races, and they already had a competitive advantage because back then all the tracks were dirt to begin with, right? And that's what they were used to doing. So we're going to talk a little bit about NASCAR, who Joe Gibbs is, and then we're going to talk about the war room.
It is the biggest stage in all of stock car racing.
It's the biggest day of the entire NASCAR season.
The only thing higher than the temperature is the pressure.
You win a race here, it's heard all around the world.
With 101,000 fans in the stands, a full infield, the suites are packed.
This may be the biggest crowd I've seen here in quite some time.
So we're helping control things we can control and adapt to things that we can't. Have a great day on pit road. Let's get some momentum so we can.
Drivers, start your engines!
We start our way here. Try to dot all the I's, cross all the T's. no mistake. Be focused and execute.
It's showtime!
Ready. Still go. Green.
Wins his second Daytona 500.
This one's for JD. We're desperately going to miss him. His legacy still lives on.
Checker flag, 200, bud. Good job. All I do is win, no matter what.
Side by side!
What a
In the grass.
Short track win number 1 for Martin Truex.
These guys are racing their hearts out.
What a hard tumble for Kyle Larson.
Cercueil wins at Talladega.
Nice work, guys. Way to never give up.
He did it!
His first ever checkered flag.
This is going to be a celebration for the ages.
Kyle Busch rides his brother. Kurt Busch will win easily. The most dramatic finish here ever.
Chase Elliott picks up the win.
You've been ass whipping today.
Denny Hamlin is not going to make this easy.
Aaron Jones wins at Darlington.
Celebration is on for Christopher Bell.
They're wrecking on the bottom. 3, 4, 5 trucks involved.
The wait is over for Stuart Friesen. It's time to start the playoffs.
16 drivers with a chance at the championship.
Facts of facts victories for this 19 hot rod team. Come on.
Elliott noses into the tire barriers.
I cannot believe I just did that.
Here comes Elliott, trying to make the move to the outside.
Hell yeah. Let's go.
Kyle Larson wins at the Monster Mile and Dover.
Firing in stern. He'll nail Logano. Major crash.
Ryan Blaney by inches.
Everyone fighting for every position.
It's insane. I mean, everybody's on 10.5, and there's only 10 settings.
Kevin Harvick wins at Texas.
Across the line goes Denny Hamlin.
They are going to Miami with a walk-off win here.
This is the biggest moment for the championship for
Crafton wins his third Truck Series championship.
Tyler Reddick winning back-to-back championships. Green flag is in the air.
A fast race car, impeccably driven, and no mistakes tonight.
Kyle Busch scores championship number 2.
It's all about this group, though. An awesome moment. It's a dream come true.
So I'm not going to read this word for word, but after World War II, America really experienced their greatest growth in stock car racing. The problem is the tracks weren't talking to each other. They weren't sanctioned. So some of the tracks were better at the racing and not so good the crowds. Some could do both the same. But regardless of the venue, NASCAR racing, just stock car racing itself, just wasn't united as far as the sanctioning body goes. So in 1947, Bill France had a meeting there in Daytona, and after the meeting, NASCAR was born, which stands for National Association for Stock Car Auto Racing. The first race ever for NASCAR was there on the Daytona Beach, was part of it. There was about 60 cars show up, about 50 ran the race. Red Byron was the first winner ever. There was about 14,000 fans there. They all paid about $2.50 a piece. Kind of like the way it is today, right? They're proud of those tickets. So plans immediately were made when the popularity of the sport took off. So in 1950 was the first ever asphalt race, was there in Darlington, South Carolina, and the thing just took off from there. So through the 60s and the 70s, through innovation and technology, the NASCAR series really gained momentum. And then in 1979, the first ever fully televised race took place at the Daytona 500. And that's what launched the sport pretty much. All right, as far as NASCAR itself today, we're either the number 1 or number 2 sport each and every week. Now, having an owner that is an NFL legend kind of ties you into the number 1 and number 2 sport every single weekend. You can see the social numbers there and the views on the internet. It's the most loyal fan base on the face of the earth. I mean, these people are fanatics. And then you can kind of see some of our fan base demographics there. All right, now, back in the day, this was a NASCAR garage. All right, you had a couple cars, you souped them up, you went out to the tracks, and that's what it was all about. But over the years, it's kind of changed a little. So today, Joe Gibbs Racing is about 600 employees. That's about 400,000 square foot of race shop, and we have about 14 teams under the roof. It was started back in 1991 by Hall of Fame legend Joe Gibbs. Joe has 3 Super Bowl wins over his career with the Washington Redskins. He was inducted into the NFL Hall of Fame in '96. And out of his 16-year career, he made the playoffs 10 years. He is in the top 100 all-time NFL Hall of Famers. There's only 10 coaches in that group, so that makes him in the top 10 coaches of all time. So in 2020, Joe was given the Bill France Award of Excellence. He had just won his 5th championship with Kyle Busch. And then he was invited over here at Charlotte at the Hall of Fame. I know y'all are going to be going to that Wednesday night. So there they have a venue, and Joe was inducted into the NASCAR Hall of Fame. So he is in the class of 2020. Makes him one of the only people I know that went into different sports and is in both Hall of Fames. I asked Joe one time, I said, you've never driven a car, you never kicked a field goal, but you're in both Hall of Fames, right? And his comment was, he said, you surround yourself with the right people and they'll make you famous. So that's his claim to fame. He just picks out the right folks.
He is the first inductee in both the NASCAR and Pro Football Halls of Fame. But for Joe Gibbs, the fact that he achieved success isn't what drew him to this moment. It's that he brought so many people to the pinnacle of their success. Like his 3 Super Bowl wins with 3 different quarterbacks and 5 NASCAR Cup titles with 3 different drivers. The depth of Coach's impact stands apart from most who don a headset. Across 3 decades in coaching and now 3 decades in motorsports, the numbers and statistics are purely superficial. You don't win nearly 200 games on trick plays and gimmicks. You don't capture more than 175 checkered flags gambling on fuel. Chance isn't what collects 5 Brickyard 400s and 3 Daytona 500s.
Dale J's going to win the Daytona 500!
The chapter and verse of Coach Gibbs' story is a truth far richer. What Coach achieved on the starting grid and on the gridiron mirrors his daily walk as a disciple of Jesus Christ. Where Coach excels is challenging his teams to live with purpose so they might compete with passion.
Ever since I was a kid, I dressed to this, man. Yes!
To claim their God-given character so they can run their race with honor. Points, poles, purses all mean nothing without divine purpose.
JD's name's on that car. That's his number 11 with Denny. JD had the best view of everything.
The trophies he's collected are impressive. The accolades, all hard-earned. The titles, almost too many to count. But let me tell you which titles mean the most. Disciple, husband, father, friend. That's the man we know as Coach.
He's the one that should be here talking. The man's had a radio and a headset on for 60 years. All the football games, all the races. It's amazing. All right, so let's meet our teams real quick. So obviously Joe's the owner. In the number 11 FedEx Toyota Camry, we have Mr. Denny Hamlin. His claim to fame, he has won the Daytona 500 3 times. He's made the playoffs 6 times. Kyle Busch drives our number 18 car, which the Morris family sponsors that with the M&M's brand. Kyle's won 2 championships and 4 brickyards, which is pretty amazing. The number 19 car, sponsor is Bass Pro Shop. It's driven by Martin Truex Jr. Martin won the championship, I think, 3 years ago. And then we got a rookie out of the Xfinity Series, driving the number 20 car. I think he's in his early 20s, Christopher Bell. And that's our 4 Cup drivers. Now, our series is just like baseball, so the Cup Series would be the same as the major leagues. So we also have what would be the AAA and Single A. So we call this our Xfinity Series, and that's where our development drivers are getting seat time and developing their skill set. So in it, we have in the 19 car, Brandon Jones. And then we have Mr. Burton, Harrison Burton, and he's in the 20 car. Dex is the sponsor there. And then we got this kiddo here that's coming up out of the ARCA series. This is Joe's grandson, Ty Gibbs, and he will win the ARCA series championship this year. ARCA is a single level, which would be the same as, like I said, single A baseball. And then you work your way from ARCA to Xfinity, Xfinity to Cup. So he will win the ARCA series championship this year, and he's already been put into a handful of Xfinity races already, where you can see he brought home the checkered flag about 4 or 5 times this year already. All right, one thing is the pit crew. So I always say they're not the lead singer, but they're in the band. So what we do is we go after college athletes or ex-pro athletes to put them in these pit crews. So we put them in an NFL style weight room. We have 6 trainers. 3 of them are strength trainers, practice choreographing their moves out on pit road. We have a mock pit road that I'll show you. And then 3 of them are sports medicine. So a lot of times if you got a shoulder, a back, a knee injury, we can get you back out on the track quicker by doing all your rehab there at the facility. So at any point in time, there's about 100 individuals training on a daily basis. So just like this morning, 1/3 will be up in the weight room doing their weights and cardio. 1/3 will be out on the football field and basketball field here doing exercises. And then the other 1/3, we have 2 pit cars there that we practice pit stops. So we have an outside awning. We film all the stops for instant review. And then one thing that we're able to do is we're able to videotape all 4 teams, and we can do a translucive on top of each team. So if Team A is so much faster than Team C, we can sit there and show each pit crew member where they're losing time by the faster teams. So this is kind of what that would look like. One team's wearing white helmets, the other team's wearing dark helmets. So every move, every turn, how they pivot, like I said, it's just it's a choreograph is what it is. So we're able to do 4 tires and 22 gallons of fuel in about 12 seconds. Now, if you think about it, you're hitting 5 lug nuts, you're pulling a tire off, you're putting another one on, you're hitting 5 more, you're getting up and running around to the other side of the car and doing the same thing. So under race conditions, this is kind of what it would look like. Kind of gets you upset when you go get your tires changed on your car and it takes 2 hours, doesn't it? We know they can do better. All right, so I'm going to talk about the development process real quick. At Joe Gibbs Racing, we're half manufacturer and we're half competition. So we are a high-performance race car manufacturing complex. Once the product is finished, it is handed over to the competition side. They set it up for the specific racetrack that they're going to, and then they load it on haulers, tractor trailer trucks, and we do 39 events per year. So we start in February, we end in November, and we only have, I think, 2 weekends off. So it's a very busy schedule, but it's definitely engineering and manufacturing driven. So right now we have about 77 engineers. They're broken down into different disciplines, which are aero, design, race team engineers, manufacturing, and vehicle development group. Right now there's over 2,000 different parts and pieces that we manufacture that go in the race car, the engines. If you think about it, shocks, anything that moves or anything it takes to assemble one of these cars, we manufacture it there in the building. Our part qualification, we do a lot of, obviously, simulation, CAE, we do a lot of lab testing, and then racetrack testing. So for those three come together, we call the sweet spot, and that's what qualifies a lot of our parts and development. Because when a part goes wrong, it's a bad day. So this was Chicago. We about lost Bobby that day. This kind of shows you what some of our track testing would look like. A lot of our CAE and simulation. We really have perfected the digital twin, so we don't do as much on the track today. It's mainly done in the simulation room. We're able to do more airflow, more tandem. Like if we're at Daytona or Talladega, we can actually do tandem drafting. And then occasionally we will go back to a full body wind tunnel just to verify that the digital twin is calibrated correctly. We do a lot of testing internally with FEA and CFD. After all the testing, there's build sheets that are created. And so once that takes place, the designs and fixtures are created along with the NASCAR specs, and then a chassis is built. Now, once a chassis is built, we have to transport it to the NASCAR certification facility there in Concord. And what they do is they do a series of inspections on this, and then they put a series of RIFD tags on the car. After a car is assembled, it'd be difficult to check the internal working mechanisms of a car. So all the chassis are pre-certified before we're able to hang a body on the car. Now this is actually one of our Xfinity cars, but the point is all the front clips is a Kevlar composite. All the side pieces is sheet metal, and then the hood and the trunk is a carbon fiber. After the pieces have been assembled, we put very little Bondo and paint in the car because we wanted as smooth as possible, but as light as possible. And then we shoot it with a white light system. This will get you within 1/1000th of an inch. We're able to create a body, 3D model, and then it's then taken into our inspection room, and it gives us a color map on where we're high and low. Long story short, all these cars are built within about 10 to 15,000ths of an inch. Once that's done, the old way, we would check it with what we called the claw, which is just a template that went down over the car. And today, we use a Hawkeye system, which is a 3D reverse engineering tool that we roll the car in. It shoots a series of dots down on the car, and then lasers shoot across the car, collect the dots, and it creates a 3D model of the car. Now, we're constantly trying to keep all the weight out of the top end of the car so we can redistribute the weight with tungsten racing blocks in the frame rail down below the center. So, like I said, we don't paint these cars anymore. About 6 or 7 years ago, we created a printing room upstairs, and we will create these latex wraps that will print out everything. So you wouldn't think about it, but a wrap's 5 pounds lighter than a paint job. Then all the decals that are on top of the wrap are all implemented in on the wrap, so there's not a second surface there that wind's having to go over. And then it takes the guys about 3 hours to wrap a car instead of 3 days to paint one and to decal one. So from a competitive edge, turn it around quicker, it's just a greater product. So this is what a wrap would look like. So for anybody that ever thought we had headlights on the car, yes, it's a decal, okay? All right, we're going to talk real quickly where all the parts and pieces come from. So like I said before, over 2,000 pieces are built there in the shop. We've already built our chassis. Now the mechanical parts and pieces start making their way to the car. The drivers sit in a big box of mush and create a body mold. All the seats are custom to the driver's body shape. Once all that starts taking place, the car starts coming to life. Right now we have CNC manufacturing there. We have about 40 different pieces of equipment. So there's 3 5-axes. There's about 14 verticals. There's about 4 or 5 horizontals. And then there's about 7 lays. All in all, we have laser cutters, water jets, you name it, any way to shape a piece of metal, we can manufacture that piece. One quick example of why we do that, we can do quick turnaround times, but we invest more heavily into complex multi-axis type machines. So this one is a mill turn. We did a case study where the front drag length was 3 pieces, and this is an example of that. We were able to hold that part with a billet in between centers, machine that piece out of 1 instead of 3. So what it did was it took all the weld out of the part, because anytime you hit a part with a welder, it moves. So we were able to take it from 3 parts to 1, 15 hours to machine to 14, 18 hours to set up to 5. Long story short, we reduced the cost, sped up the time, and made a better part. So that's why we try to invest in more advanced pieces of equipment there to manufacture our parts. We also have a metrology lab there, so all these pieces of equipment reside on a separate piece of real estate, so there's no noise vibration that gets into the room. So all of our parts and pieces are checked in a clinically clean metrology environment. We have 3D printers there, so we do those for layups, for molds, and then actually some parts and pieces make their way to the car. We build our own batteries, so this will be a battery tray, be the front and back, and then we'll actually lay our cells in that encapsulates the top and the bottom, and this is an example of a track bar adjustment gauge that we'll print out. We'll put our electronics in it, and it makes its way straight to the car. So all those parts and pieces are printed right there on the 3D printers, and then we're able to take advantage of that technology. The old way, you build a mold and have it injection molded, and it takes forever, and this way you can have your parts and pieces pretty much the next day. All right, so different tracks have different setups. We go from anywhere from a half-mile super speedway, which was this past weekend in Bristol, Tennessee. That's why I don't have any voice left right now. And then we go all the way up to super speedways like Daytona, Talladega, tracks like that. We'll be in Vegas this weekend, which is, I think, 1.5 miles. So different tracks have different setups as far as the camber in the front end and springs, shocks, that type of thing. So there's 4 setup plates here, 1 for each team. All these setup plates are Blanchard ground and calibrated twice a year. Each one of the cars are set on each plate with instrumentation and fixtures, and everything's laser aligned while on that plate. So once the cars are ready to be loaded, then we'll put them on our team hauler. Each team has their own truck that you get 2 cars in the very top of the truck, and then underneath is a shop away from home complete with an engineering suite up at the front, well, in the front of the trailer part of it. These trucks will do about 75,000 miles per year. With our 39 events, we're in California twice, Texas twice, Phoenix twice. We're all over the place. So if you think about it too, is we prepare 2 cars per week, per team, per series. So that's 5 in our Cup Series because we do another team as well. We have 4 in our Xfinity Series and 1 in ARCA. So we have about 20 to 22 cars we're building and preparing every single week. You get 1 race out of 1 engine, okay? We build these engines for maximum horsepower for the liability of a 700-mile race. So I always say a perfect engine blows up on the way to victory lane, right? Because you won the race, and that's the most you can get out of it. So that's how we transport the equipment, and then to transport the employees, Joe Gibbs Racing has its own aviation division, so we have 3 jets. These 2 here will move about 187 team members around each and every weekend. And then we have Joe's corporate jet that moves the executive team in just on race day. All right, so we're going to get into the war room. I'm going to try to explain this. If I lose anybody, you can ask questions afterwards. But so back at Joe Gibbs Racing, which is in the upper left, like I said, we got about 400,000 square feet. All right, so there's 3 different locations that we're going to take place here, but in the upper right is the inside of one of our haulers. At the end of that hallway, there is an engineering suite there, complete with a server room, 7 monitors, and 3 engineers that work there at any given time. So in the lower left is a piece of wireless equipment for measuring tire thickness. And all it is a wireless depth mic, is what it is. In the lower right is a crew chief sitting on the pit box. So when you go to a racetrack, we bring out this big communication box called a pit box, and I got pictures of it, I'll show you. But during a race, we have a crew chief there, and it's his game. He's talking to the driver. We also have a spotter that there's on top of the each track. Spotters stand up there, and if you're my driver, you can't see. You got a helmet, your helmet's restrained. There's 40 other drivers out there, and you're doing 200 miles an hour. So it's very difficult to look around your shoulder to see if there's a car there when you're ready to make a move. So we have spotters that stand up on top of the track during a race, and it's constant communication. There's a car high. Well, that means you don't go up. They tell lap speeds. It's constant information that the spotter is given to driver. So the gentleman on the right is the crew chief. He can talk to the spotter, and he can talk to the driver at any time, and also his entire crew are all wearing radios and headsets. That's how, because all these races are very, very loud, so you got to be able to communicate to everybody what's taking place during a race. So everybody's got a radio, everybody's got a headset. All right, so these are our 4 cars. It was very difficult to get one picture with all 4 cars in the same picture. Because usually you got a guy running in the back and you got some guys running in the front. So this was at Daytona where all 4 are lined up pretty nicely together. And so all 4 cars are at the track. You got 3 engineers up on the pit box at the racetrack. You got 3 engineers back in Joe Gibbs Racing during the race in the war room. They're all communicating. So you got a tire specialist at the racetrack, and you got a tire specialist in the war room. So what takes place, we're just going to talk about tires. There's about 10 different scenarios like I did today, but tire management is huge. If you got lousy tires, if you don't manage your tires, then you won't be able to compete during a race. So you can see the indentions. There's 2 indentions you can visually see right here. So what we do is we measure the tire thickness before they go in the car. When they come off of a car, this is a wireless depth mic that we're actually able to put that in each indention, and we can test our outside wear, we can test the inside wear, and then the 3 indentions in the center is the center zone, and we're able to calculate what our tire wear is, and at the end of the day, you're able to do air pressure adjustments that can or make you win or lose a race. So I took some videos the other night at Bristol. What happens is these tires get real gummy, so it's difficult to take a reading unless you got a nice, flat, smooth, common ground. So what you're going to see, a very small video, is right there at the track. I took my phone out and took a few videos. Is the guys, they take a blowtorch and they take like a putty knife, and they'll heat up the tire and they'll scrape that gum off the tire and get it nice and flat before they come in and take their readings. So that's what you're going to see right here. And then here's another with the 2010. So they're physically scraping that gum off to be able to get a flat surface is what you're doing. So then the tire specialist comes along, and you see he's taking readings in each one of those indentions. There's 5 indentions. Every time he takes a reading, that data is being uploaded to our hauler that's there at the track. Okay? Everybody following me so far? All right, so when these readings are being taken, uploaded to the hauler at the track in the server room, there's 3 engineers there. They then translate that information back to the war room in Huntersville. So, and this is a picture of the hauler. Like I said, down at the end, you go up a series of steps, and that's where the engineering room is. The war room back in Huntersville is receiving that information. Calculations are being managed and made. Air pressure adjustments are being calculated. That information is then sent back to the engineering office there at the hauler. And then that person there has a headset and a radio that he then can communicate that information to the crew chief, which is sitting on the pit box and calling the race. At that point in time, you can see he's got a series of radios on him. He can talk to the spotter, he can talk to the driver, or he can talk to his entire pit crew. And he can go on the radio and say, hey, we need a half pound out of the right front, or whatever. But all this information is being delivered to him through 2 sets of engineers at 2 different locations off of the readings that's being taken by a wireless piece of instrumentation. If you ever come to a race and you're a guest of ours, we have 8 seats on the back of the box. So you're given a headset and a radio. You're able to listen to the engineers plot the race, plan their strategy. We do give a disclaimer because you'll be able to hear what the drivers are saying too, and sometimes that's why we do the disclaimer. It can get a little colorful. And then we obviously have guests there, so we give them radios and they're able to hear everything as well. So this is a picture. You can see the gentleman hanging over. He's got a headset on. Everybody on the pit crew has earbuds in their ear on top of their helmet with a radio in the back, and they're getting instructions from the crew chief during a race. And then when it all works out, this is what that would look like as well. Got to make a pit stop. I got a ending video, and it's about 5 minutes, and I'm right on time. I got about 2 minutes on my time, so I'm going to skip that. In our last highlight reel, we won about 19 races in a championship, so it's about 6 minutes long, and I'm right on time right now. But I do have 1 or 2 minutes for questions. If anybody, and don't ask me radio questions. That's but anything dealing with the race team, what it would take to run a race team, anything you'd always want to know about a race team but was afraid to ask, right now would be a good time. Yes, sir. We invented all the competitive advantages, and then everybody copies after that. No, actually, whenever they did decals, when I started, I've been here 25 years. That's what qualifies me to be with y'all today. I was there when we had 18 employees, and that's all you knew how to do was paint a car and put decals on it. But through years and through technology, wraps weren't around back then. So things evolve. Technologically advances has given us competitive edges over the years. I purchased our first CNC machine, our second one. Today we have 40. I was the first engineer. Now we got 77. So it's really evolved over the years to technologies like that. That was a good question. Yes, sir. Well, back in the day, it was a stock car. They literally, I was talking to Richard Petty one time, and his daddy Lee, raced in NASCAR as well. And he said he'd never forget, people make fun of him because they'd drive around in their family car because it had a number on it and a bunch of decals, and people make fun of them. And then a lot of times they would go to a race and Dad wrecked the family car in the race. So they all had to bum a ride to get home. So back in the day, another story, when we went to Darlington for the first time, they didn't realize how abrasive the track was because we're close to the coast. So it's real sandy and abrasive. So when a lot of fans went out to get in their cars to go home, they noticed a lot of their tires were missing because the guys were wearing down their tires in the race, and they just went out in the parking lot and helped themselves. So it was stock cars back then. Once again, innovation took off. There is nothing on those cars that's stock today. We do race a Toyota Camry, but good luck finding a Camry piece on that car. Yeah, that's a great question as well. Yes, sir. Say that one more time.
Do you guys funnel these innovations back to car manufacturers?
Yeah, so the question is, do we funnel these, when we find out competitive things, do we funnel it back? So inside Joe Gibbs Racing, we have 8 TRD engineers, Toyota Racing Development. So they work closely with our engine department. They work closely with air, wind tunnel, all that stuff. You got different disciplines of TRD engineers embedded at Joe Gibbs Racing. So it's a great partnership with those folks, and what they learn being a part of our race team, they then translate back to the TRD folks. Yep. Great question as well. Anybody else? Anybody on this side? Everybody good? All right, well, I wish everybody safe travels back to everywhere you traveling home to. I really appreciate y'all having me today. I hope you learned something. I hope this brings a little bit more insight to when you go to the Hall of Fame on Wednesday night, and just thanks for having me. Hope you have a good conference. Thank you.
Thank you. So I'm very glad that we got this started. And again, thank you all so much for coming. I'll be doing a project update as our next presentation. And this is my first time doing this. So after years of watching Ben Hilburn do this, I've decided to avoid the classic slide of showing how late everyone registered. Because everyone knows when they registered, and I can tell you again, it was late again this year, but if there's one thing that 2020 and 2021 have taught us, this is definitely a year for understanding and flexibility. So that's going to be the only time I mention that we appreciate it if people can register early for next year. Wonderful. So it says annual update here, and that is what most of my presentation will be. But to start off, I know there's a few pieces of information that everyone really wants, and that's the conference Wi-Fi code. So if you haven't already connected, and I understand that there were some issues with the number of devices supported, I've been told that that cap has been raised now, so hopefully people are able to get on. It's the Hilton Honors Meeting Wi-Fi network, and the password is GNU 2021. The other key bit of information to know is that we do have over 300 online participants, and some of our supporting organizations and exhibitors are only on the chat. Unfortunately, they're unable to join us here in person this year. And so please do join the conference chat. This is a direct link to our main conference space. You may have also seen chat.gnuradio.org as another shortcut. Both of them work. And I'll have some comments later on in my talk about the actual chat system that we're using, because we do think that it is interesting and worthy of mention. There is a participants guide. Hopefully you received an email with a link to that. If you haven't, we will be sending it out again. And you can find most of this information on the conference website, particularly joining the chat, our main stream, particularly if you're remote. Hopefully you're already viewing it, but is out on our YouTube channel. Please do share that around as the main track is for everyone. Information about joining the workshops, I believe, did go out. Most of the workshops are going to be based here in person, and many of them are going to be made available to the remote participants. Those are the workshops labeled hybrid. And interestingly, the first one coming up, the Pluto SDR workshop this afternoon, is online based. So unfortunately, Analog Devices is one of the organizations that wasn't able to be here in person. But I've been getting emails from them, and they are ready to go. So that will be our main organizing areas are on the side. So the workshop areas are just to the side wall here. In terms of where to get assistance, obviously if you're here in this room, the registration desk or one of the organizers is your main point of contact. If you are remote and online, then hopefully you've found the conference chat, and the main help desk is the hash GRCon21 help desk channel. That should be listed in the space that you join when you drop into the chat. And if you're having any trouble with that, grcon@gnuradio.org is the help address. So I think that's the end of my morning announcements that would have normally been before the keynote, but thanks for your patience. Well, that's fun. And you can't see my titles. Well, you can see it on one side. So we'll also get the projectors adjusted here on the main screen. I'm pretty sure that the previous slide was just a large GRCon21 logo, and I'm pretty sure people are getting familiar with that at this point. So I will dive just straight into it. My name is Derek Kozel. I'm the GNU Radio president, and the first thing I'll be talking about is how did that happen? Because the last time we were here in person, it was Ben Hilburn up here as GNU Radio president, and the transition from him to myself is actually a very important one, and it's one that's going to have a lot of implications for the project, not because it's me as president, but because of the process. We announced it in GRCon 2019 and 2020, and we really wanted to transfer from a benevolent dictator for life, you know, the standard open source model that a lot of projects have early on, to one where we wanted much more accountability and we wanted much more responsiveness to the community. Ben was doing a great job, but there should be, it was also too much of a job for one person. So we wanted to distribute it out, and we thought that was a great opportunity to do this. And so the method that we took has been described in past GRCon talks and talks at FOSDEM, so do check those for the full details. But the long and short of it is that we formed an unincorporated association. We have a set of rules around how that's governed, and that includes regular elections. There was a general assembly formed, and this was the group of most active leads at the time of this association being created. And I do have that list on, I believe, the next slide. And since then, we've been voting in new members of the community to be on this General Assembly. I at one point phrased this as a steering committee, and I think that's really the wrong approach here. This is kind of a centralized general situational awareness. The members of the GA represent many of the different areas of the GNU Radio project because we have a hugely diverse base of users, we have a hugely diverse base of contributors, and we have a lot of different areas where organizations and individuals are interested in using and interacting with the project. And for any one person, there just wasn't that awareness of all of these different areas. So what we're looking to do is have the General Assembly be representative of all of these different use case areas as much as possible, and be able to inform and direct the project kind of as a centralized hive mind. However, it turns out that at some point, once a year, somebody needs to stand up on this stage and give a talk about the organization and about the project. And so we put together a board, and this is 3 members, and currently it's myself, Mark Lichtman, and Martin Braun, who are serving as the board, and the most recent election nominated us for the next 2 years. And it is our responsibility, yes, I chose the correct tense on the slide, it is our responsibility to implement the decisions and ideas of the General Assembly and to act as the single points of contact when that is useful. With an open source project that is so community-based, it can be really challenging to do things like sign a contract, send somebody to a specific event to give a keynote, or to represent the interests of GNU Radio in small working group sessions where there's an expectation that your laptop goes to sleep. An expectation that there is somebody who has a nominal amount of authority to make statements on the behalf of the project. And so, again, this is what the board and the General Assembly are there for. Every member of the General Assembly, and there are several here, unfortunately not as many as we'd like, thanks to 2021. And so please do reach out to any of us. I think our information is on the next slide. But the articles of association, the information, our meeting minutes for the board, and our general meeting are all available online. We are learning how to do this. For many of us, this is our first time in a formal structure like this for an open source project. And so we are looking also for feedback on this, because in the end, this is going to be the group that helps facilitate all of the actions of the project. We held our most recent election and general meeting on September 2nd, and the great thing is that there was a unanimous reaffirmment that the current board, the current articles of association, all of our structure that we chose last year actually was well-founded and has been renewed. Yes, wonderful. So these are the members of the General Assembly. Hopefully many of these names are familiar. If you're new to the project, then you will probably soon become familiar with many of these names. Ones that I'd like to particularly highlight, though, is that as the we're going to say the word GA probably quite a lot, and that's the General Assembly. So as the General Assembly grew, we've been able to bring on board Jeff Long, Samantha, Johannes Demmel came on, and Jacob Gilbert as people who were more officially recognized for the roles that they were already doing within the community. And so they've been voted on by the GA, and we're very, very, very pleased to have them on board. And this group will grow over time. That is the intention of it. And so as people step forward with a desire to support the project above and beyond their own personal interests and their work interests, we hope that this group grows. And so this is really one of the big things for me of why this new structure is really important. GNU Radio in the past hasn't really had the structure in place to be able to apply for grants, to be able to make commitments as a group towards things that did need outcomes delivered. You know, we've been very fortunate with maintainers who have been very passionate, but in the end, they haven't been in a position where they could spend dedicated time pursuing focused outcomes. I thought I had my slides in a slightly different order, so this is a little bit of a jump, but we are going to be pursuing grants as the GNU Radio project, and those should be coming in the next year. And the main focuses of this initial set of grants are going to be around project sustainability. It turns out that particularly with COVID right now, a lot of people have been very stressed, very strained. It's been difficult to put together this event, and it's been difficult to maintain the code of the project. The success over the last year is really in spite of those things, and it's taken a lot of sweat and tears from people. And so what we'd like to do is reach out to different sources of funding and actually start bringing on at least part-time contractors or even potentially employees to do project maintenance, sustaining engineering, to recognize labor that's already done on a volunteer basis and try and at least financially compensate some of that, to build up our non-code efforts that have been ongoing, things like event coordination. I have an entire section at the end of this for recognizing the organizers of the GNU Radio conference, but this is something that takes a tremendous amount of time and effort to put together, and we really hope that more and more of that can be done in a more efficient way and in a more properly compensated way. Bringing on interns, there's a program called Outreachy, which would allow us to pair up with qualified interns, and it costs $8,000. It's not all that much, but it's something that the project in the past hasn't been set up to develop those sorts of relationships. And so with a formal structure, with more people working on this, we're really excited that we hopefully will be able to bring on interns more regularly. Tutorials, documentation, and guides. These are things that do happen on a volunteer basis, and I do particularly want to shout out to Barry Duggan, who has been doing a huge amount of work over the past couple of years. It turns out that he has never been to a GRCon. He's been fundamental to organizing this event, and unfortunately just wasn't able to join us this year. So I know that he's watching the live stream. Thank you. We'd also like to bring on people to do more organized development of these, longer, white paper level things. It could extend out to college level entire courses that are made available. These are the sorts of things that, again, just volunteers are not particularly well suited to do without support. The website development, it is functional. You've all managed to find the conference website and hopefully the information that you needed, but we could definitely use some support there. And then further outreach, this is something that we'll probably talk about more in the context of the SETI Institute, but we're hoping to do more things where we show up at more events, where we're raising the awareness about the project, and where we're engaging with communities that just previously haven't heard of GNU Radio or haven't had interaction with us. The last two bits are really both should have question marks, but we're going to be applying for grants to try and more formally verify the performance of GNU Radio blocks, to develop more tooling around that, increase the level of testing so that applications that need that level of confidence have to do less work themselves. This is something that it would benefit it if the project were able to bring this to the table. New feature development, that's really a big question. Being able to commit to new feature development really means having some amount of onboard staff. Having the project be able to say, even if it's just contractors, we know that these people are available. If you want this feature, we can get the people on board to deliver this into the main core of the project. So don't expect that in the next year, but that's where I'd love to see the project getting to. In a bit of a smaller perspective, we're currently looking for ideas for small grants. So please do check out this page on our wiki. These are things where, would $1,000 go a long way in a certain area? $2,000, $3,000, small amounts. And this is stuff that the GNU Radio project does actually currently have the funds to do at the moment. And the idea, we will be working on the process for approving this, but the General Assembly gives us a way of actually voting on spending this money. And that's the sort of accountability that we really needed and which was holding us back in past years from spending money on the project. So an example of where this has already been put into place is with training materials. And I'll be speaking more about this on Thursday during the conference wrap-up, but we are currently contracting to develop training materials which will be a common set of onboarding materials for GNU Radio. So if you want to get started developing with this software from scratch, you may know Python, you may know C++, you may know a little bit of DSP, but trying to wrap all of that together into a 3-day course that could be delivered on-site or remotely, directly by the project and by trainers that we essentially certify, that is already an effort that's in progress, and the General Assembly voted to spend $10,000 on that. So more details will be around on Thursday, but that's an example of the sort of thing that we're already starting to work on. Well, we did update our code of conduct. I thought that I had a little bit of a brief on it, but we've updated our code of conduct based on the same template, on the same original source material, but to version 2. And this is just to keep it up to date with the reach and extent of the protections that we want to provide to our community. Our chat, this conference, everywhere that GNU Radio as an organization and as a community comes together, we want to make sure that people feel comfortable, safe, and that they have an avenue to get responses to any incidents that they see. We hope that these are very small. There have been a few in the past that have been reported, and we were poorly equipped to respond to those in a timely and accountable manner. And so I'm very, very happy personally to say that we've formed a group of dedicated responders. We are looking for people to volunteer into this. So if you are interested in being one of the people who helps respond to any of these reports, and this is throughout the year, we only get 1 or 2 every year at the moment, and hopefully it stays that way or lower, but we are looking for volunteers. There's been a training attended from Otter Technology. This is a well-recognized provider of diversity and inclusivity training, and we specifically looked into the set of steps and processes for being able to respond effectively. So this is in effect for this event. It's in effect for our chat and everywhere else that the GNU Radio community is. And if you have any incidences or even feedback that you'd like to provide, conduct@gnuradio.org is the right place to reach out to. Or if you're here in person, you can reach out to any of the organizers. That's primarily myself, Sam in the back, and then several other people. Ben Hilburn would be another good person to reach out to, and they can direct it out to the group of responders. So that's most of the project update in terms of the organization. Let's jump into more of the material. And as I got to this point, one of the things that I realized was everyone else is already going to cover this. There's talks on all of these topics. And so the signal metadata format, SIGMF, this is something that was hatched at a GNU Radio Hackfest some time ago. Let me just check how much I've run on. Thankfully not that much. So the signal metadata format was hatched at a Hackfest, published online under the GNU Radio GitHub page, and has been slowly matured over the last couple of years. And one of the really pleasing things, and I'm sure it'll be said much more eloquently and in detail in the talk on Wednesday, is that the adoption of this has been really strong. We've seen a lot of government groups picking it up. We've seen a lot of organizations and companies starting to use it. We've seen more and more open source projects beginning to support SIGMF as a format that they're ingesting for signal recordings. For those of you who aren't familiar with SIGMF, I should say this is an alternative to the raw IQ data file. We're all familiar with using the file sync from GNU Radio to just dump IQ data or float data out into a file. And how often have you ended up with folders full of this that are disorganized, lost? You come back to it a couple weeks later and you say, what frequency was that on? What radio was I using? What's the sample rate? And then you realize you're really up a creek without the sample rate. And so the signal metadata format is a standardization of the metadata formats that were kind of already floating around. Took a look at those and said, okay, we're going to write up a spec for this, and the Release 1.0 of that is imminent or already done, but come on Wednesday to find out the latest status on that. I know there was a push to complete that for GRCon. There will also be a workshop on Thursday all around the metadata format and the tooling around it. There are libraries, there are GNU Radio blocks, and one of the efforts that we'll be doing this fall into the spring, however long it takes, is upstreaming gr-sigmf into the core. So at the moment, and I will leave most of this to the code talk tomorrow, but I believe that it looks likely that could be in 3.10 when that gets released, possibly 3.11, but in the imminent future, sigmf will be a native feature of GNU Radio. Volk has been one of the long-term components of GNU Radio, the vector-optimized library of kernels. In many ways, there's not a lot to be said about the development. It's been proceeding very nicely. There's been new kernels added, there's been debugging done on it, there's been work on new platforms, and that's great. The huge news is that it's going to be relicensing to LGPL v3+. And the big enabling bit of this is that it will be usable in applications where the source code is not released for the parent program. Volk is a library. It makes sense for it to be able to be linked to from any application. And we think that this is something that's going to bring in more contributors to Volk, help make Volk a healthier project and extend out to more platforms, more kernels. And we know that there are many people who are interested in using Volk in BSD applications and in other and in proprietary applications where they currently aren't able to. And so they're developing identical projects internally and not sharing out that work. So Volk will be relicensing. This is in progress. It will be relicensed for the 3.0 release. And if you have contributed to Volk in the past, our huge request is that if you agree with this relicensing, please do affirm that you are comfortable with this and you are okay with contributing your code under the LGPL by going onto the GitHub repository and signing on to a document that's there. All of that process is described in a grep, a GNU Radio enhancement proposal that's available online. It's described on the Volk repository. If you have questions about this relicensing, please do come to myself or Ben Hilburn, and we can both talk you through the implications of this. This is something that really probably would have made sense from the beginning, and we're really glad that we'll be getting around to this. Google Summer of Code. We've been really grateful and happy to be accepted into this each year. This year we had Oscar Ekholm, who worked on a view-only mode for GNU Radio Companion. He has a talk later on today at 2:15, but in short summary, it turns out that GNU Radio Companion, when you open up a flow graph, will execute any of the Python that's listed in the variable fields. This is a great and useful feature if you want to have dynamic content there, if you want to be using Python functions to, for instance, create a file name with a date stamp, or you want to do a basic bit of math because it's so much easier to do math.py than try and remember the 10th digit of pi. However, not all flow graphs are from people that you know, and depending on your application space, it might be nice to be able to preview that in a format other than the raw JSON, YAML of the flow graph. And so view-only mode enables that. It'll show you a list of the dynamically calculated values, the formulas, and give you a chance to review that. So be sure to check out his talk for the actual implementational details there. The SETI Institute. This is also something that we announced 2 years ago at GRCon 2019. We have partnered with the SETI Institute. If you bought a ticket, you will have noted and paid for it, you'll have noticed that SETI Institute is now providing our back office support. And this is a huge assistance. So they've been handling all of our finances, payments, transactions, and in many ways that's been the smallest thing that they've done. They've also been providing support, so if you buy one of the GNU Radio t-shirts that will be available tomorrow at the registration desk, The design and printing and all of the logistics of that were managed by them. They've been handling procurement of projectors and equipment for the venue. They've been handling all of the contract signing and negotiation and management there. So all of this support is something that we're learning more and more of how to work with them. This year is a little bit of an onboarding process for them, showing them what GRCon is, what our community is. We've gotten some great and interesting questions as they've seen the talks go up and just asking, so we knew that you did software-defined radio, we knew that you had these applications, but we didn't realize that anyone was using this for underwater acoustic communications and stuff like that. And so definitely look forward next year. SETI Institute will have much more of a prominent role in the organizing and presence here at the event. And I believe that there's going to be a talk later today from Steve Croft, which may touch on some of this in terms of our collaboration with the SETI Institute. We've been working with them over the summer, teaching their summer groups, summer research undergraduate summer experience undergraduate research undergraduate experience. Apologies, but I've forgotten the acronym, gr-iio students. And so this has been 30, 40 students each year that we've been running workshops for on GNU Radio, and they've been going and developing projects. There'll be a talk on Doppler detection in GNU Radio using SETI pipelines, I believe later on in the week. I apologize, I've forgotten which day we've set that for. Daniel Estevez, who is probably a familiar name to many people here, has been instrumental in running a lot of these workshops, and so a huge thanks to him for volunteering his time for that. There will be a workshop about the Allen Telescope Array on Wednesday. This is a world-class distributed array of 6-meter satellite dishes in Northern California, acting as a radio telescope receiver. And we had a Hackfest there in 2019, I believe. We hope that Hackfest will return next year as in-person events become more feasible. But work has continued with that, and there'll be demonstrations during that workshop of some of what's been accomplished with really high data rate processing and being able to ingest samples from that many dishes. Our matrix chat service, and I realize this is a little bit of a shotgun approach to everything GNU Radio, but we have been using Matrix for the past year and a half. Last year's conference, the chat fell over, and we felt that quite strongly. And so we've taken measures over the last year to ensure that the chat is a bit more resilient. At times that's been bumpy. We know that the chat has gone down, that it's been a little difficult to use. There have been upgrades made, particularly in the last week, and we hope that the chat will be much more reliable. For those who are finding Matrix for the first time, it is an open source and open standard chat system. It's federated, so much like email, you can connect to the GNURadio.org home server, or you can be coming in from a Fedora one, or you can be coming in from a corporate one. It turns out that Matrix has been quite desirable amongst many government groups and many educational groups, and so we think that more and more people will be bringing their own accounts to events like this. The FOSDEM conference, the Free and Open Source European Developers Meeting, ran on Matrix as well. It is private, and so one of those pieces is encryption, and the management of those encryption keys is one of those things that has been bumpy. So apologies if during this most recent server upgrade you lost access to some of your direct message chat history. There is a feature for backing up these keys, but let's just say that the usability and user-friendliness of it is something that Matrix as an organization continues to work on. And that is at chat.gnuradio.org. So again, if you haven't joined the conference chat, please do. In terms of other events that have been running throughout the year, this is something that is really great to see. The European GNU Radio Days ran for its third time. It's been an annual event and has been continually maturing and evolving. And so it ran alongside the Software-Defined Radio Academy this year. The whole list of talks and presentations are up online, including some workshops and a Capture the Flag style challenge. So I do encourage you to take a look at those. The workshops were of outstanding quality, and they are looking at running it again next year. They have no confirmed details, and one of the things that they're looking for is how can they better serve the audience. They do run in Europe, and so that may not be everyone here in this room, but hopefully it's many people who are in chat. Should they focus more on workshops? How can they make it more accessible to people? They've been running it on a weekday, and they're looking at switching it onto a weekend possibly. And so they're looking for feedback on this. If you just search European GNU Radio Days, you can find the contact info to reach out to those organizers. Other events, I've mentioned FOSDEM several times. There was the Free Software Radio Room run again last year, or this year still, in February. It was an online event, and there was a very strong GNU Radio presence there, as well as a bunch of other free and open source software-defined radio projects. All of the recordings from that are also available online, and FOSDEM will certainly run one way or another again in February. The next one is one that is really quite sad. Tapper ran the Digital Communications Conference over the last several days, and if there'd been any justice in this year, they would have been co-located with us. They were planning to be here on the Friday and Saturday just before GRCon, and unfortunately, their organization chose to be purely virtual this year. And having organized this event, I can absolutely say that they have saved themselves a lot of trouble and strife and stress. I'm very glad that we've been able to pull it off, but it has required an extraordinary amount of work. We're hoping to align with them again in the future. This is, for those who don't know, this is a very long-running open community, not necessarily open source, but open community around software-defined radio, digital communications, and the development of new and interesting digital communications methods and standards and technology, mostly from an individual basis. So it's a very interesting community, and if you look back to the early days, there were some very early GNU Radio presentations shown at Tapper DCC before GRCon was the event that it is today. So I do encourage people to take a look at that. I believe that the recordings will be up for that, and we hope that we'll be able to be in person with them in a future year. And that brings us to GRCon here. It's taken a team much larger than those just listed here to pull this off, but the people on this slide are absolutely the reason this event has occurred. Between Sam, Barry, Josh, Steve, and myself, there have been meetings every week of the year since last GRCon. And I think many people will have felt throughout the year the challenges of trying to decide whether an in-person event is something that you would attend. And so for the people here in the room, thank you for making the decision to come. We hope that our policies and our decisions have made you feel comfortable and safe. But for those who are joining us online, absolutely we understand that this has been a year where a lot of people are not traveling for one reason or another. And we hope that you'll join us in the future when things have settled. But particularly these people have made this event possible. But there's definitely special thanks due as well. This conference venue was originally booked for 2020. We would have been having this event a year ago. And that event was organized by Michelle Thompson. She was our conference chair for several years leading up previous to that and ran tremendously successful GRCons. She passed on to this new organizing committee all of the contracts, the preparation, the notes and relationships that have been built up with the local area. And absolutely, we took all of her work and just pressed play on it in many ways. Some of the details have changed. Some of the challenges have cropped up since she set this up. But I did want to particularly say thank you, because this event is really Michelle Thompson's achievement. And so anything that's gone wrong, you can blame us as the current organizers. We implemented the plan, but we inherited a very firm and solid plan. And that was also facilitated by the Open Research Institute which she is one of the managers of. This is a open source, open community research group dedicated to evolving digital communications and other open science efforts. The SETI Institute, and again, not enough names are on this slide. There are absolutely people who should be, who are not, but the SETI Institute has been tremendously supportive, and we're tremendously grateful to them for helping us through this. GNU Radio, as I said, is an unincorporated association, and so there's no one to sign on the dotted line, and the SETI Institute has bravely stood by us as we passed paperwork to them, and we're looking forward to all the collaboration that comes from that in the future. And that's the end of my presentation here. There's so much good content in the rest of the week. I didn't want to put in too many spoilers, and I did want to hopefully leave some time for questions. If you have any questions about the project from soup to nuts, I may not be the person to answer, but I certainly hope that I can direct you to the person who does know. So, in summary, thank you very, very much for being here. Thank you for participating, and we're going to have a great year. It's been a challenge to organize. It's been a challenge to get together. But speaking with everybody just over the past couple of hours and last night, there's a deep sense that as this is a community event run for the community, by the community, it's wonderful to see so many familiar faces. It's great to meet new people. It's great to see faces that we've seen online and never met in person. And so we know that this event is going to be that core focus that it is every year around GNU Radio development and about building the relationships that make an open source project possible. So thank you very much for coming out, and we'll have many more announcements throughout the week, I'm sure. There's quite a bit that isn't yet set up, and so I want to hold off on recognizing some of our supporters who definitely deserve it until we're able to do that full justice. But if you have any questions, please raise your hand. We have a microphone that can float around. To those who were getting the captions online, there were quite a few inaudible questions, so please do wait for the microphone to reach you. And if I've stunned everyone into silence, that's probably only due to how fun the NASCAR talk was and how boring business management sometimes can be. The other thing that we are going to be working on is pulling questions from chat. I don't know if anyone's on the conference chat right now, but if you do see questions, if you could raise your hand and highlight it, we'll definitely get you in line.
Okay. So there's lots of sponsors this year.
There are many sponsors this year, and they are the people who I was saying that I was inadequately prepared to properly recognize. Because this event couldn't be happening without the sponsors. And so me standing up here and just trying to name all of the, I believe, 19 sponsors this year from memory, higher than 19, I'm getting an upward arrow, 22 sponsors. You can tell that I am inadequately prepared for this. And I want to apologize to the sponsors for that and hope that the success of this event can be a little bit of a compensation for that. The best I can do at this moment is to reiterate the list that hopefully you all received in an email to say that there will be an exhibit hall opening tomorrow across where you will be getting lunch, and to say that these organizations that have stepped in this year have not single-handedly, but collectively made this project possible to get through what has been a challenging 2 years. The finances of this conference are tenuous at the moment. Our attendance is certainly lower than we expected. And it's the confidence, faith, and an investment that all of these sponsor organizations have made that will make it possible for us to organize next year's event. It takes a lot of money to do it. It takes a lot of time and effort, and without the sponsors, it would not be possible. To simply say that they're supporting the conference is also inadequate, because many of the organizations that are here are not just putting money on the table. that is appreciated, but they're also putting their time, effort, code, contributions also on the table and feeding into the open source nature of the project and supporting it, whether that's through developing hardware that GNU Radio receives and sends data with, whether that's developing software and services and applications based on top of GNU Radio, whether that's just being a user of GNU Radio for internal testing, for internal development, and choosing to reinvest into the project as a supporter. Those are all huge. Sounds like we have either a question or I've gone over time.
Question from online. Is there a particular area of documentation in which help is desired?
Documentation is a tremendously challenging area because each person who comes to the documentation page is usually looking for something slightly different. I believe that we have very reasonable documentation at this point for starting to use GNU Radio once you have it installed. But the install process for GNU Radio remains quite difficult. I'm very grateful that some of the next talks that come up, I believe the 2 following talks, are about packaging GNU Radio and making it easier to use in different operating systems and different environments. But the pages around getting started, definitely need continuous review and improvement and simplification. It's great that there are 40 different ways to install GNU Radio. If you are a new user, you shouldn't care about 39 of them. Additionally, I'd say the other area that could use improvement is guides on development environments. If you are installing an out-of-tree module or you are developing an out-of-tree module, it would be nice to have the soup to nuts answer of how do you fire up Visual Studio Code on Windows and get GNU Radio running in a development environment. A binary installer is only so useful in that case. So in what is an inadequate acknowledgement of our sponsors, please do visit this page, because it is not a trite, small list of people who are supporting the project. This is, in many ways, the reason that we are all here, is that they have chosen to support us, and that there are organizations that are in this room, that are online, that are simply not present as part of this conference, who are saying, over the course of the year, GNU Radio brings us value, and we want to recognize that. And so all of these companies are ones who have stepped up to the table there and are making this possible.
Okay.
Sam.
I have another online question. Being an open source project, is there a cost breakdown for the conference itself?
Well, there's certainly a cost to running it. We're very glad that we're able to make the live stream freely available on YouTube. In terms of like a GNU Radio annual budget, if that's part of the question, we have been putting that together, and we will have more comprehensive financial reports after this event. That's one of the things that we want as GA to make transparent.
I should probably finish the rest of the comment. I apologize. Its pricing is a little high for a hobbyist. It may help make the decision to attend in person. I could never afford the expense on top of the conference fee. So they appreciate the virtual attendance. But
we will, and this is a commitment that we have. We will continue live streaming. We will continue posting the videos freely available on the internet. We will work year on year of making the workshops more and more available. This will be our first year running hybrid, and it's full of challenges. And so we hope that we succeed at all of them, but certainly year on year we'll be making it more and more available, because absolutely is an expensive event to attend. If you buy an early bird ticket, the conference does not make any money. The per attendee cost is higher than that. And so we are doing our best as far as that comes. And this conference, particularly this year, is not a fundraiser. In normal years, it's our goal to be able to fund our usual annual expenses, and that's everything from continuous integration to even mundane things like website hosting, web development, being able to occasionally, and this isn't something we've actually done recently, but buy hardware where things like the Mac M1 platform has been unsupported for some time, and where we may need to invest in buying some of that equipment for developers. Our chat server is a non-trivial expense, not compared to this conference, but in terms of our annual budget. So we do have expenses, and we will try and make it as accessible as possible.
Any other questions in the room? Okay. With that, I think we can probably take our break a little bit early.
Great. Thank you very much. And there will be many more announcements throughout the week and many more opportunities to share good news. We have lots of good talks, workshops, and you'll be finding out so much more about the project there. So thank you very much, and enjoy your break. We'll be back, I believe, at the top of the hour, I believe. So please do check our schedule, and we'll make an announcement when it's coming up. Hello. I hope that you found the snacks during the break and had a chance to get to talk to a few people and meet some new folks as well. We'll be starting up on our next talk, which is by Ryan Volz. Ryan Volz is an academic at MIT and has been doing radio astronomy work. As part of that, he found that there was a great need for integrating GNU Radio within the Anaconda Python environment. And so his talk, unfortunately remote, is going to be all about that packaging. Ryan is active in the chat system, and so if you have any questions at the end of the talk, there isn't time to do a live Q&A, but we'll be taking questions on the chat system. And I'm sure that Ryan has said something by now, so let's try and see. It's trying to send it out over the HDMI. No wonder.
Study the upper atmosphere using radar.
Okay, it's pulling out on my laptop. Should have tried this during the break.
Today I'm going to talk to you about something that experience of my day job, and that is managing the radio installation.
Yeah, I apologize. We're going to have to spend a few minutes trying to get the audio to go out the right output here. Well, it's coming out of...
For anyone out there with a really short attention span, I'm going to give you
unless
everything.
we want to make Ryan sound quite tinny, I think we should probably take a minute to try and get this running. Apologies for the...
at MIT Haystack Observatory, where I study the upper atmosphere using radar and radio techniques. But today I'm going to talk to you about something that is born out of that experience of my day job, and that is managing GNU Radio installations with Conda. Hi everyone, my name is Brian Volz, and I'm a radio scientist at MIT Haystack Observatory, where I study the upper atmosphere using radar and radio techniques. But today I'm going to talk to you about something that is born out of that experience of my day job, and that is managing GNU Radio installations with Conda. For anyone out there with a really short attention span, I'm going to give you everything you need to know on this one slide. So if you get one thing from this talk, let it be this. You can install GNU Radio for Linux, Mac OS, or Windows using my Radio Conda installer, which is on my GitHub at the link shown on the screen. And all the information that you will need to use it can be found at that link or at the GNU Radio wiki. Search for Conda install. Now, to get into the meat of it, I'm going to start you off with a little bit of an introduction to Conda in general, and then we're going to talk about how to get started with GNU Radio and Conda, which is geared towards your typical users, and then to finish it off, we'll dive in with some more advanced topics for the more adventurous. Some of you may be thinking, Conda, I think I've heard of that. Isn't it that Python distribution for data science? No, that is Anaconda, which is the world's most popular data science platform according to Anaconda Inc., which makes it. Or you might be thinking, isn't it that package installer for Python? No, that's pip. Or isn't it that tool to create isolated Python environments? And no, that's virtual env. But at the same time, Conda also kind of is all of those things. So what Conda is it's a tool for installing software packages within an isolated environment. And a key feature is that it is cross-platform for Linux, Mac OS, and Windows. It is written in Python, which is why you are often hearing it associated with Python. But it can package any software. It's not restricted to Python. And it is developed by Anaconda Incorporated, which is why it sometimes gets confused with Anaconda, the distribution. One thing Conda does is it allows you to create and activate isolated environments. So you can type Conda create -n and then the name of an environment, and it'll create a directory for storing that environment. And then you can type Conda activate and then the name of the environment, and it'll put you at a prompt where programs within that environment are on your path, so you can execute them without getting interference from your base system. Another thing you can do with the Conda command is install packages. So from within an environment, you can type Conda install and then the name of the package, in this case Python, and we're specifying that we want to equal to version 3.9, and it'll present a plan for which packages it wants to download and install, and if you approve, it will install those into your environment. Another important task for managing these environments is listing all of the installed packages that you already have. So from within an activated environment, you can type Conda list, and it'll list all of those packages, including their versions and where they came from. So you can see here that after that last install command, we have Python 3.9, and it's 3.9.7, and we also have all of the other packages that Python depends on. So that's just a taste of the basics of what Conda does, but I can recommend that you follow this link and find the official user guide, where you can see not only more commands that you can use with Conda, but also the theory of how Conda works and how it's designed. So it's a really great resource, and I recommend that you check it out if you're interested. Now, it's possible some of you maybe have already used Conda and you walked away from it being not very impressed, thinking it was kind of slow and difficult to use because of that. Well, I have good news for you. because there now exists another tool called Mamba, which is a fast cross-platform package manager, which is a drop-in replacement for Conda. It is written in C++, and that makes it faster and much more pleasant to use these days. So I recommend that you have both installed, but use Mamba preferentially, especially for installing packages or creating environments, because its dependency resolution is much quicker. And in order to install Mamba, you'll probably just use a Conda install command. So something like Conda install Mamba, but you specify -n base to install it into the base environment, and -c Conda Forge to get it in the Conda Forge channel. And we'll talk about channels in a second. Now that you know a little bit about Conda, you might be thinking, well, why is this relevant to GRCon? Why has he spent 5 minutes talking about this? Where's the radio? Well, it's relevant because installing GNU Radio is a hurdle for many. And often people want other packages too, not just GNU Radio, and those packages have to be kept in sync because things are compiled with specific versions of GNU Radio. And building from source is sometimes required or recommended to do this. And this is a known problem, and it's why PyBombs exists. So Conda makes installation easier. You can get up-to-date cross-platform packages that are a command away, and you can even manage the whole software stack, so not just GNU Radio, but all of the out-of-tree dependencies and other stuff that you want to use with GNU Radio. And even expert installation hurdlers who's very used to building things from source, you can benefit from Conda as well. And the great thing is that this is a tool that is sustainably supportable by the entire community, so it's not just going to be on one person's back or my back to keep it operating and keep packages up to date. That said, we're still not quite done with our introduction to Conda. There's a few concepts that I want to cover first, talking about environments, channels, and distribution. First up is defining a Conda environment. An environment is a managed directory. Sometimes we think of these as an installation prefix, and they are usually found in the env folder within your base installation. That's by default, but you can actually create environments at any location. They're structured in the Unix style, so you have your standard bin, lib, include paths within that directory. And on Windows, all of those Unix-style paths are actually found in a library subfolder. And these files are hard-linked, so there's no cost to use the same packages within multiple environments. So creating environments with duplicate packages is not going to cost you any more disk space. A Conda channel is a collection of packages that you can download from, and these are usually hosted on Anaconda Cloud, which is anaconda.org, or there's a new tool called Quetz, which will allow you to self-host a channel of packages. Some examples of channels are the defaults channel, which is put out by Anaconda Incorporated. There's also the Conda Forge channel, which is the primary collection of community-supported packages. There's also focused communities of different packages, one of them being BioConda for biology and bioengineering. And on Anaconda Cloud, you can also have individual users with their own channel. So I have my own channel, Ryan Volz. And it's generally recommended to use only one channel, or if you want to use multiple channels, set them with a strict priority so that you're not mixing and matching packages that might conflict. So you can install from a specified channel with your Conda install command by passing the -c flag and then the channel name. And it's also possible to set the default channels for a particular overall Conda install or for a particular environment by modifying your Conda configuration and adding the appropriate settings. And finally, we have Conda distributions, where distribution is an installer for a base environment with a specific collection of packages. I've already mentioned Anaconda, which is a distribution focused on data science, where all of its packages are in the defaults channel, and it's made by Anaconda Incorporated. There's also the Mini Conda distribution, which is a minimal base with just Conda and only the things Conda needs. And it's configured to install more packages from the defaults channel, and it is also made by Anaconda Incorporated. But then we also have the MiniForge or Mamba Forge distributions, which are a minimal-based distribution with either Conda or Mamba as the main package manager. And these are both configured to install from the Conda Forge channel by default. And these distributions are made by the Conda Forge community. And then finally, we have my Radio Conda distribution, which is a collection of open source software radio packages. It is also configured to download packages from the Conda Forge channel, and this one is made by me. Now you know what Conda is, so in this next section we're going to talk about how to get started for using Conda, in particular with GNU Radio. The first step is to download a distribution so you can get started using the Conda command. I think the best way to start is to use Radio Conda because that'll have most of what you need, and you won't have to dig too much into using Conda itself. But if you want to do that, or you want a little more flexibility, I do recommend the MiniForge or Mamba Forge distributions. So what you'll do is you'll go to either one of these GitHub sites, and you'll download the installer for your operating system and architecture. If that combination is not available, then seek me out, and we can talk about trying to make it available. Next, you'll need to run the installer that you just downloaded. So on Linux or Mac OS, this will be executing the installer from a command line, or on Windows and sometimes Mac OS. If it's a graphical installer, you can just double-click it. You'll have to go through a few steps, the first of which is to agree to the license, and then you'll have to choose where to install. Usually the default is okay, and it's probably a good idea to put this in some home or user directory. Then it'll ask if you want to initialize, or if you want to add Conda to your path. And you'll probably want to answer yes to this. That'll make the Conda command available in your terminal without having to do additional configuration. Then on Windows, it'll ask if you want to use this as your default Python, and you'll probably want to answer no to that, because you don't want to use this as your Python unless you specifically activated that environment. So on Linux and Mac OS, in order for that answer to be no, you'll actually have to go in and change the configuration after you've installed. And so you'll want to set it to auto-activate the base environment to false, so that it doesn't load up this base Conda environment whenever you open a terminal. To use your new environment on Windows, you'll want to open up the Conda or MiniForge prompt, which is installed into your Start menu. Or on Linux and Mac OS, you'll just open up any terminal, and then because you answered yes to that initialization question during the installer, you can use the Conda command already and type Conda activate base, and that'll put you into the base environment. It's a good piece of advice to avoid installing things into the base environment. A shorter package list is easier to manage, and the base environment ideally includes only what it must, i.e. Conda and or Mamba and what those do. This is because environments are cheap, so it's not a big deal to create new environments for the programs that you actually want to use. And this could be a reason to prefer MiniForge over Radio Conda, because the MiniForge distribution is that small base distribution, whereas Radio Conda has everything installed in the base environment. So if you do have MiniForge, you do opt for that, you can create and activate another environment with all of the Radio Conda packages by doing a Conda create command and name that environment Radio Conda. You can tell it to install from the Conda Forge channel and my personal channel. And you only want it to install the dependencies of the Radio Conda meta package, and that'll install all of the packages that come with Radio Conda. And then you can activate that Radio Conda environment, and then as you're using it, if new packages come out, you can upgrade them with the Conda upgrade command by using the --all flag. So what about GNU Radio in particular? How do you get started using that with Conda? Well, these are all the packages that I have added so far to Conda Forge. That includes GNU Radio, which I broke up into a few of its component pieces, so that you don't have to install all those dependencies at once if you don't want to. There's also some out-of-tree packages, GNU Radio Osmo SDR, GNU Radio Satellites, and GNU Radio SOAPy before it came in tree. Then there's Digital RF, which is a package I maintain for MIT Haystack Observatory for recording and storing data. And there's GQRX for exploring the spectrum. And then a bunch of packages for hardware support. So that includes the AirSpy devices, libIIO and the Pluto device, Lime Suite for the Lime SDR devices, RTL SDR, Ettus UHD devices, and the SOAPy modules that support all of those. These GNU Radio packages are compiled against both GNU Radio 3.8 and 3.9, so you can choose which version you want for now. And so this list is nice, but more packages would certainly be better. And so I'm adding more packages when I have time or as particular needs arise, but I'm definitely always interested in help. And hardware testing would be particularly helpful. I've already covered all of the devices that I have or have access to. So if there's a device that you're interested in that's not on this list, please help me test it and we can get a package going. Actually, using GNU Radio from a Conda environment is as easy as activating that environment and using GNU Radio like you normally would. But if you have more questions, here's a list of resources that you can turn to. There's the GNU Radio Wiki and the Conda install page. There's also more information on my Radio Conda repository, in particular for getting the different hardware devices set up and running. Or you can also ping me on the GNU Radio Matrix chat. And if you encounter a bug using some of these packages, and it's a bug in particular with the packaging, you can find the repository for that particular CondaForge package. It has its own feedstock repository under the CondaForge organization, so just Google for that and report the bug there. And if it's not a bug in the packaging, definitely report that upstream. I'm sure they'll be appreciative. All right, now for the more adventurous out there in the audience, in this last section, we're going to talk about a few more advanced topics with the goal of giving you everything you need to know to help me make some more packages related to GNU Radio and maintain them going into the future. Packages are created using a Conda recipe, and a recipe is just a directory with a few basic files. There's the recipe metadata file, or meta.yaml file, where you have the name of the package, the version, and the build number. It has the download URL. It has a list of dependencies for the build, host, and run environments when you're building it. It has some testing commands to make sure the package works correctly, and then it has some descriptive metadata. The build scripts for Linux and Mac OS are build.sh shell scripts, or for Windows it's the build.bat batch script. And these lay out the build steps for Linux, Mac OS, and Windows. And so this is your typical sequence of, say, cmake, and then make, and make install. And then they will install to the prefix or library prefix directory as appropriate for Unix or Windows. The tool that executes the recipe to create a package is called Conda Build, and so you'll want to install Conda Build into your base environment, and then you can run it on the recipe directory, like Conda Build, and then the recipe directory. The steps that it goes through to build a package are it will create and activate the host environment according to the list of host dependencies that you included in the recipe. Then it'll create and overlay the build environment according to the build dependencies. And then it will execute the build script. And then it'll take the installed files that you put into that host environment and package those into a tarball. And then it'll install that package into a new test environment and run the test that you specified. And if it passes, then you have a successful build. On the right here, you can see some of the contents of one of these package tarballs, which is just the files as they will be installed into the environment, plus an info directory where things like the actual recipe itself, the licenses for the source code, and the metadata about dependencies and whatnot are stored. So here I'm going to use the GNU Radio Satellites recipe as an example. You can see the full recipe on the CondaForge GitHub if you search for the GNU Radio Satellites feedstock. So this is the top of the meta.yaml file, where we can see we're defining the package name and the version, the source of where the source code is downloaded from, and Another key takeaway here is that a recipe is rendered in 2 different steps. So the first step is to either keep or drop a particular line based on selectors. And you can see one of these selectors in the third to bottom line, which is that comment followed by some brackets and an expression. So if that comment, that expression is true, then that line is kept. And if it's false, then that line is deleted from the recipe. And then the next step in rendering is to fill in the template with all these variables and double brackets or bracket and percent signs that you see here. And this is using the Jinja templating language. And once you've rendered all of that out, you have a complete full meta.yaml file. The next section in the meta.yaml file is the list of requirements. Here divided into the build, host, and run environments. And you can see we use the selectors here to specify different requirements for the different operating systems. It's important to note that host dependencies can automatically add to the run dependency list if their recipe specified a special value in its own build, run, export section. The section after the requirements is the test section, where you can see we can run different commands, that if any of them fail, then the tests fail. So typically we might check to make sure that the executables run correctly, or to make sure that certain files exist within the packaged tarball. And then another typical test is to just try importing some different Python packages. In this case, we're just going to import the GR Satellites Python package. The last couple sections of the meta.yaml file are where you provide some informational metadata, including web pages that are useful to link to, the license for the source code, and the summary and description of the package. And then also, for Conda Forge in particular, some extra information about who's maintaining this package. You can find much more about writing these meta.yaml files if you search for Conda build meta.yaml. There's a great documentation page here that I refer to all the time to remember how to fill out all these different fields. The other half of the recipe is the build scripts. And you can see here that it's your typical steps that you walk through when you build from source. You make a build directory, you call cmake, and in this case we have to pass it some particular arguments for installing and building into a Conda environment. And then you just, do your standard build and then install steps after that. And you'll notice that these scripts use some environment variables that have been defined ahead of time by Conda build. And I've also referred to this documentation page a lot, so search for Conda build environment variables, and that'll tell you everything you need to know about that. Writing a recipe is the preferred way to install into a Conda environment, but it's also possible to build packages and install them into an environment without using a recipe. I generally wouldn't recommend this because it may be hard to maintain, but it can be useful for development. So the general build procedure is just like a normal build from source, except that you want to install your dependencies into a Conda environment. You want to activate that environment. And then when you build, you want to tell CMake about the environment. So for an out-of-tree module in particular, you want to start within the out-of-tree module source directory. And then we'll use Bomba to create a build environment. We'll install into it the GNU Radio package, of course, and then also a special meta package called GNU Radio Build Deps, which will install the typical dependencies that you also need along with GNU Radio. And then if there's any particular dependencies for your out-of-tree module, you want to install those as well. Then you activate that build environment, and then you go through your typical build steps. You create a build directory, you enter the build directory, you call cmake, and in this case we have to tell it about our Conda prefix, where we want to install into and where we want to get libraries from. And then you just tell it to make and make install, and that's all there is to it. You can find more details, including Windows instructions, since this is in particular for Linux, in this example, on the wiki. Again, search for Conda install. If you want to build GNU Radio itself in a Conda environment, it's the same basic steps as with an OOT module, except in this case there are no helpful meta packages of dependencies, so you just have to create an environment with a big long list of all of GNU Radio's dependencies that you want to use. And so I maintain a couple of these lists on the wiki, or you can copy it from here for Linux in particular. And again, you make that environment, activate the environment, and then do your typical build steps, passing the prefix path for Conda. So once you're comfortable with Conda, the next major step is to contribute back and add your packages to Conda Forge. So let's say that you've got a Conda recipe that works locally. Now what do you need to do? Well, I recommend following the Conda Forge's documentation, which I've linked to here on the slide. But in general, you'll want to submit that recipe to their staged recipes repository. And you'll do that by first forking that repository on GitHub, and then create a branch within your fork to hold your recipe. And then you put your recipe in its own folder under the recipes directory and commit it. And if you haven't created a recipe yet, you can follow the example that they provided in the recipes folder to help you along. And then you'll submit a pull request to the main stage recipes branch, and then you'll iterate on that pull request into the CI builds pass. And once those are green, you can request a review from the staged recipes review committee. And if they accept and merge your package, then you'll be ready to move on to the next step, which is maintainership. Once a recipe is merged into Conda Forge, a feedstock repository will be created to hold the recipe. The feedstock holds the recipe in the recipe folder of that repository. It also contains CI scripts for building packages in the cloud, and these scripts are maintained by a tool called Conda Smithy. And what Conda Smithy does is, after any time the recipe changes, you'll want to run Conda Smithy re-render, and re-rendering may update the CI scripts that are included in that repository. And you can configure Conda Smithy by editing the Conda Forge YAML file, which you can find in that repository. To keep a package updated once you have it as a feedstock, you need to know a few things, and one of those is that packages are built and uploaded on commits to any branch. So when you want to make changes, you'll want to do them from your own fork of the feedstock repository and submit pull requests to the main branch in order to check that the build works before you merge it. You can also use the build locally script to test the build locally on your machine. To help you maintain the feedstock, Conda Forge provides bots that will send pull requests automatically whenever there's a version update for a new version of the source that is available, or if there's a rebuild that is needed due to dependency updates, such as when a global pin is updated. So like if GNU Radio were to be upgraded from 3.8.3 to 3.8.4, that might trigger a migration within the Conda Forge community where packages are rebuilt against GNU Radio, the new version of GNU Radio, following the dependency tree. So that's all I have. Hopefully this has been enough to get you interested in using GNU Radio and Conda, and hopefully I've given you enough information to be able to jump in and not feel lost. I think there's a lot of potential here for reducing some of the friction that happens with installing GNU Radio and out-of-tree modules. If that's something that interests you as well, and you want to get more packages into Conda Forge, let me know, and I'll be happy to provide guidance and co-maintain any package. I also think it would be a great idea to work on integrating Conda with PyBombs so that some of what I've described in this talk can be automated. In particular, it would be good for PyBombs to adapt to a Conda environment when building from source, or to find and install dependencies with Conda, or to generate Conda recipes from PyBombs recipes. So please, don't hesitate to get in contact with me if you have any questions. Thanks a lot for listening.
All right, thank you, Ryan. Next up is Maitland Bottoms, who manages everything Debian related to GNU Radio and beyond. So I'm going to hand it over to Maitland here. Oh, and one more thing. For our remote presenters, for the presentations that are remote, if you have questions, the presenters are typically hanging out on chat.gnuradio.org. So throw your questions on there during the talks. Like Ryan's very active, and if you have questions, you can hop on there and send him some questions.
Okay. Apparently this isn't the presentation laptop, and we need a presentation laptop. Derek is around.
Anyone see Derek?
Than presentation slides. All right, do we have video yet? Because I love this logo for GRCon. Thanks to our new friends at NASCAR. Awesome. Shout out to all the muscle car collectors, the hot rodders, the racers, the gearheads. Here we go. I'm here to talk about maybe GNU Radio, but that's going to be covered elsewhere. I am a Maitland Bottoms. I'm a Debian developer. I contribute stuff to GNU Radio because I have itches to scratch like anybody else. And I volunteer as a developer in the Debian community, which is a community around free software, or it's an operating system, or it's a Linux distribution. The most recent release of this Debian Linux distribution is codenamed Bullseye. It's Debian 11, and it was released just over a month ago. So now you know everything I'm going to talk about, Debian and GNU Radio. And to talk about installing Bullseye and getting started on GNU Radio and then what you can do. So I could keep talking about Debian and GNU Radio. You're soaking in the community. Thank you for being here. Thank you for being here virtually. And like you've heard already this morning, please help us. We continue to need help to do the task we set out to do, which is to make a GNU Radio toolkit and provide signal processing blocks for you to use. You can get the source. You can get Linux distributions, Debian, Ubuntu, Arch, and you already heard for Conda talking about PyBombs as the installer. There's also an Ubuntu PPA. So there's lots of ways to get GNU Radio. So Debian is also a big community. I could keep talking about GNU Radio. We are all here to build this toolkit, like Debian is here to build an operating system. Debian and GNU Radio share some common beliefs that free and open source software is the way to make the future better. And we're all volunteers, so you can join the Debian project as easily as you can join the GNU Radio project. So for the operating system, it's basically what runs your computer. There's a lot of people, choose, there's an operating system almost per person practically. But the reasons people choose Debian is it's non-commercial, it's competitive, it's easy to install, and it's openly developed and has a good active security team. Now, for GNU Radio, maybe the security team isn't what you're here for. In GNU Radio, you're here for the documentation team. They're the ones that add value to the whole project. And the Debian operating system is the basis for derived distributions. So Ubuntu is one of them. You'll see many GNU Radio developers who are using Ubuntu. Mark Shuttleworth is a keynote speaker here, and he once said that every Debian developer is an Ubuntu developer. But there's also, aside from the community, a source and binary distribution. You can't run a Git repo. You have to install binaries that your computer can run. You can do that without compiling on the target machine. There's lots of toolings around Debian packages. Everyone wants to get binaries to run on their machine, but it's really all about the source. So getting the source to end users, the source for review and audit, the source for reproducible builds efforts, which Debian is key player in that community, a source for derivation improvements. So GNU Radio and Debian, you'll see, they're a natural fit. We value free software. If you contribute to GNU Radio, expect yourself to find yourself contributing to Debian. So on to the release. Debian Bullseye. Debian is big, really big, kind of hard to comprehend how many packages are in it. You might think Red Hat is something, but that's just peanuts compared to Debian. That's what Douglas Adams might say. 4,821 packages updated in the last release cycle. So time marches on. Nobody wants Python 2 or Qt4 or old stuff anymore, which of course was the basis for GNU Radio up to 3.7. It hasn't been out 2 months, but we've got new software, the new GNU compiler collection, CMake 3.18, Boost, Qt, Python 3.9, all fresh off the press, just released a month ago, and I already, I don't hear people in the back. Maybe the people online are grumbling about it's old and obsolete already. The main thing about Debian as a release is it's targeted to be the universal operating system. It runs on everything from laptops to supercomputers. It's got a RISC-V port already. It should be the universal way to go. So in the bullseye Debian release, there is GNU Radio 3.8.2. This is an eye chart. You can Google for stuff later. Everything on the left side is the components that you can get from running GNU Radio config info enabled components on your system. And I'm proud to say this time there are no disabled components in GNU Radio in Debian. So the universal operating system now has a universal GNU Radio. I do want to point out on the right side, GNU Radio was built with certain dependencies. Volz 2.4, which is, the good stuff. UHD 3.15, which is rock solid. The Debian thrift now works with GNU Radio. This is a good thing. Codec 2 library is a fun adventure for many hams. Python 3.9, and I have to say SWIG, because this is a GNU Radio 3.8. GNU Radio 3.9 will be on PyBind 11, but that just wasn't ready by the time the release freeze happened last winter. So I've got a little note on the top about it's GNU Radio 3.8.2, but it's been updated with 53 upstream packages that I cherry-picked out of the Git repo to sort of do my own release management and get as many of the good pieces into the Debian GNU Radio as possible. And they've fixed real bugs and did useful things, so they're important to get in there. But there's an ecosystem. It's not just about the GNU Radio and the enable components. As you saw with the previous talk about how much hardware is supported in Conda, the left-hand side is some of the same stuff. UHD has been, Ettus has got that into GNU Radio since the earliest days, but gr-osmo SDR allows lots of other hardware to come in, and there's also the SOAP mechanism, which will allow a lot of hardware support. And so there's AirSpies, there's Blade RFs, Hack RFs. We have a wonderful community of people who are building hardware to get signals from the antenna into your computer. And as the universal operating system and the universal GNU Radio, I strive to support that in the Debian GNU Radio. The center is all out-of-tree GNU Radio packages or projects. Those are also Debian package names, every one of those. Air modes is for tracking airplanes, and FCD Pro Plus is making the old FunCube dongles work. GR Phosphor is I've already seen it in demo in the gallery. It is the real-time spectrum analyzer display for you. gr-iio, because Debian is releasing with GNU Radio 3.8 to use the analog devices stuff. It has a separate gr-iio add-on to support the Pluto and other hardware from them. And there's also GR satellites. There's also applications that are built off of all this. So there's GCarX, GNSS, InSpectrum, several others, and there's documentation. So the Doxygen documentation gets built into a Debian package. It's very big. You can install it on your laptop, and you can enjoy it on a desert island because you don't have to be online to read the basic documentation. So again, this is part of an ecosystem. Over on the right side, in some of the ham radio packages I'm listing, and for the audience, this is an eye chart, but for later, this is all Googleable. These are all packages in Debian and ham radio. GNU Radio is on the right side of it, but there's support for things like the Joe Taylor WSJT-X modes for ham radio. There's AIS and ADSB stuff that are in other applications, also all co-installable in Debian. So, oops, I'm going the wrong way. So you've got a fresh install. You've gone and you've seen that the OS installer is not that hard, and probably I could have started that and gotten a good way through while getting the slides up. The first thing you'll want to do with a non-GNU Radio targeted one is use the apt and install GNU Radio and libvolk2 bin and gqrxsdr. Now, the libvolk2-bin, it's a sort of a Debian convention. There's libvolk, which is the library for the Volk, the signal processing library that GNU Radio depends on. And the -bin is these utilities that you can run to support the library. So Volk profile is the first thing you want to run on your machine after you've installed and everything's idle. And that will optimize all this library for your hardware. Then the next thing you do is you run on the left there is GQRX. That's showing you a spectrum display, a waterfall plot. It's instant gratification. You can see the RF world around you. You can demodulate and listen. On the right is my example of the GNU Radio Companion. That's a long-term relationship. You'll spend a lot of time there. Now, I didn't just do this so it comes up with a relatively blank screen. I'm giving you an action shot showing you the GR phosphor display. But it's where you sit and spend your time asking yourself, well, what if the signal looks like that? So the first things in the companion is you can actually make a block diagram into something that runs. You are programming. You are a developer, and you can start coding in a few hours or a few days. It'll take a lifetime to master. You start out with the flow graphs. You start tweaking them. So the first thing GRC will do is emit Python that implements your flow graph. Then you start hacking onto Python and learning Python. And then you say, well, my blocks are in C++. So then you start working in C++, and then you realize you have more out-of-tree projects. So as you start down this path, you will learn a lot about Git. You'll learn a lot about Python and CMake. You'll learn more about signal processing and DSP. You'll learn all kinds of software things, but one of the things you'll learn about is you'll learn about other developers. And the first, when you're developing, you edit files. This is new in the bullseye release, is that there's more introspection in the Emacs environment for completion of libraries. Here I'm completing an FFT from FFTW. Or no, it's actually getting the GNU FFT class here. And you get help on hover, so again, using a GNU Radio example, it's actually looking at your work functions. This is great. Python people have been doing this for a long time. Now, with the bullseye release of Debian, you can do this in Emacs. And I presume the Vim users and whatnot also have got some IDE features. This works off the LSP library to do language-specific support. So as you're using other people's code, I want to highlight that this is available in Debian Bullseye. You can probably do this in other OSs as well. You'll want to start doing OOT development yourself too. And you're going to say, well, what do I do? Well, Build Essential is a Debian package you need to install. CMake, Ninja Build. I noticed the Conda one used the Ninja build of the GNU Radio build. So you add some other libraries, get the Volk and FFT library helpers, and then GNU Radio has GR mod tool, and I just wish you good luck. It's an adventure. So as you start down, you're a developer. You got to give credit where credit is due. So when you do your flow graph, put your name in there as author. Copyright your work, license your work. State these things clearly so other people can see them. Credit others whose work you derived. Comply with the licenses of other people's work. But we all would not be here were it not for sharing and making free and open source libraries. So I hope you follow suit as well. Otherwise, we wouldn't be here. We allow ourselves to share our code, and this is part of the development process. So I ask everyone to release clearly. There's one policy is early and often. That's a good release policy. There's another very good one, which is when it's ready. Debian, other distros love tarballs. Git release tags are also a good way to communicate between the person writing code and the user what it is. And extra points, you're at the start of quality control and security ecosystem, so if you can hash and sign things, everybody wins. In documentation, Debian likes man pages, but there's lots of other documentation. Work done in documentation leads to successful outcomes. And I think the fact that there's been so much effort in GNU Radio documentation is going to bode well for future success. Also, new in the Debian bullseye release, there is now a feature where the debugger can actually get all the symbols. And this is for every Debian package, not just GNU Radio. So you can say, oh, well, I want to bug this other support library that I'm using in GNU Radio. And so I want to call out that there's this debug info D, which is a way that if you put this URL in your session, start up the GDB, which is the GNU debugger, your binary will load and all of the symbols will be there, so you know what the variables names are, you can test their value, you can see things in more human readable things. If you want to go look at source code, you still need to find source code, but this is a new feature in Bullseye. Hopefully it will come to every, and I think the Fedora people are doing this too. Hopefully it will come to every Linux distribution to help you debug. I already hear that it's old and in the way. Packages are old, they're not what we want, but Debian has them, and Debian has policies, and so I'm a believer in packages. I think the Conda people believe in packaging. There really are ways to do things that get the code to the people. Having every developer talk to every user isn't the way to do it. There's a role for distributions of any kind. If the packages aren't what you want, you can make your own. I'm going to point out that I'm not going to tell you how to do all that here, but there's lots of examples. And if you're really upset about, GNU Radio isn't being maintained because there's sort of a snapshot. GNU Radio in Debian stable release, it's kind of like the race car that needs to be the same car at the finish of the race. So there's a support period. And you don't swap in a new car halfway through the race in NASCAR. So you don't really stop in the new version of GNU Radio in the stable release. But for development, the future is now. There's going to be a next Debian release, and you can install Debian testing. And there'll be new bits coming soon. GNU Radio 3.9, 3.10, some new packages, requests. There'll be new versions of many of the libraries in our ecosystem. So you can keep up with the future or enjoy the old stuff. So I have to say, in my youth, I had a mentor. He helped me realize that stock products could be a starting point for personalized and modified vehicles custom to my own liking. Old things can be maintained and improved rather than cast away. So on these cars, I put wider wheels and got paint that was made to make me happy. And of course, these cars were also platforms for my amateur radio adventures. So I hope that you enjoy building your own custom thing, using GNU Radio, using Debian, and that you bring somebody younger than you along for the ride. Any questions from, I'm here from Debian, and I'm here to help. So, anyone have any questions about using GNU Radio as part of a distro? Anything online? I know we're just a little late for lunch, but hopefully this is a good time. So. Hearing nothing from the, I assume people are looking online for any other questions, but everyone wants to eat, I think.
All right, thank you so much, mate. It was a very informative and so anyone that's ever, apt-to-get install GNU Radio has Mate to thank for that and the incredible amount of work that goes into maintaining all that tooling. So we definitely thank you, and thank you for the informative talk here.
All right. Well, good luck, and everyone have fun with it.
All right. Thanks. Now, I believe lunch should be coming on shortly, and I think there might be an announcement or two before lunch. Derek or Sam or anybody before we break for lunch? All right. Not getting anything, so just hold tight for 1 minute here.
Oops.
Wonderful. Well, thank you very much, Maitland, and thank you to Ryan before him. The packaging work that's done on GNU Radio is definitely, a key part of getting this software out to everyone. This is now our break for lunch. There's only a very few announcements to make. There's been a little bit of confusion and uncertainty about how the workshops are running, so hopefully I can clarify that a little bit. And other than that, we're looking forward to the afternoon program. So for folks who are here in person, everyone who has registered for in-person has access to all of the workshops. This may not have been clear during registration. Apologies for that. Everyone who has purchased a workshop pass and will be participating remotely also has access to all of the workshops. I believe that there's 2 or 3, unfortunately, that are in-person only, and these are more discussion-based and working group style. And unfortunately, we just don't have the resources and haven't figured out a good way of making those available. If you are interested in the Pluto SDR workshop this afternoon, which is the first one coming up in the afternoon, then hopefully you've received a link to Big Blue Button. This is our workshop platform, and that should have gone out to you last night. We will be resending those links just in case. And if you still don't have them, please drop into our help desk. The Analog Devices has asked me to let people know that the first 50 participants to join in to the workshop on time and submit their information via one of their sign-up forms will be sent a Pluto SDR, and that'll be yours to follow along the workshop, afterwards when you receive the device. So that link again will be distributed. Inside of the Big Blue Button workshop space. So that's how the workshops are going to run. We have the 2 workshop rooms on the side, and so there's also one across the hallway from the main workshop spaces called NODA, and that's a space where if you want to attend this Pluto workshop, which is online only, you as a local attendee can go into that room, have quiet space, and collaboratively watch that workshop. So with that, I don't believe there's any other announcements before lunch. I'm sure during lunch we'll find other things to let you know. But thank you very much. Enjoy lunch, and we'll be back here, I believe, in 1 hour at 1 o'clock, so about 45 minutes. Thanks very much.
wonderful sponsor of this conference, and I'm going to hand it over to David and Neil Tender.
So yes, as Josh mentioned, my name is David Sorber. This is my colleague Neil Tender. We work for Blacklinks, and we're going to tell you a little bit more about Blacklinks in the next 5 or so minutes while you're digesting lunch. So Blacklinks is a privately owned company. We have more than 120. I think the last unofficial count I heard was 126 employees, and we're growing. We have 2 main offices in Rockville, Maryland, and Chantilly, Virginia. So we're based in the Washington, D.C. metro area. We haven't been around all that long. We're founded in 2018. We do primarily government-focused work, although we also have done some commercial work. And we are very much an engineering company. We're not a butts and seats kind of staff augmentation sort of company. And our tie-in to GNU Radio, and the reason that we're here today is we've done some work, some DARPA-sponsored work on GNU Radio that I'll be presenting more about tomorrow.
All right, so I want to tell you about some of the things that we're doing, and just to prelude to that, because if it wasn't clear from our title slide, this is not just a pitch about the company. We're also hiring. We're looking for people interested to join us. So wanted to make this a little bit of a pitch there as well. So we work on a wide range of things. Our core competency at Blacklinks is we're like specialty in high performance heterogeneous computing. We're really good at taking algorithms and problems and finding the best way to accelerate them on hardware, whether it's a CPU or FPGA. We do a lot of FPGA work, and on GPU. So that spans a lot of different categories. Obviously, we work in software-defined radio, and we've contributed to the GNU Radio project. But we're doing other related work. We work in radar processing, synthetic aperture radar. We're doing some stuff with RF machine learning, a lot of signal processing kind of stuff. And then also we've got a new project. We're getting into 5G. We've got a lot of work with machine vision that we're doing. We have a tool that we built to do high-speed search, which we use for some of our customers. We also have a small group that does aerospace engineering. They do like modeling of payloads and orbits, and that's a nice tie-in to some of our other work that we do. So just a kind of a pretty wide range of projects, very heavily engineering oriented. These are the 4 major divisions of our company. I won't go into too much detail here, but we have this mission analytics group that Dave works in that's mostly focused on using our tools and capabilities to do high performance, really fast analysis on big data that comes in for some of our mission customers using our high-speed search and analytics tools. We have this sensor processing group that I'm part of, where we do a lot of edge computing, onboard processing. So the idea is that we collect a lot of data and we want to be able to process it right there on, in the edge and not have to upload it to the cloud. So that's where our high performance computing comes in. We have an aerospace group that I mentioned before, and then we have another group that joined us recently, infrastructure automation. They do resilient networking. I'm going to hand it back over to Dave to talk about our recruiting.
So yeah, as Neil mentioned, we are hiring. We're always looking for good people. If you are interested, you can check out our career site to see all the various job openings. So as I mentioned, we are primarily located in the Washington, D.C. metro area. However, we do have some remote employees, and we will consider employing people that work remotely. We do a lot of government work, as I mentioned, so unfortunately or fortunately, depending on how you look at it, U.S. citizenship is required. Here's sort of a select list of some of the positions we have open, embedded software, FPGA, GPU. As Neil mentioned, we're definitely looking for some people with 5G expertise and also some satellite communications expertise. Blacklinks has pretty great benefits. You start out with 5 weeks of vacation, regardless of your, experience level. We also have 10 holidays, pretty standard medical, dental, vision insurance, 401k matching, disability insurance. We also have company-sponsored education and training. Like I mentioned, remote work is allowed, particularly in the past year and a half. And the company also organizes a lot of fun social and events and has a really good sort of culture built around that.
All right, last slide. So if any of that interests you, then the best thing to do is just come talk to us, me or Dave. We're sitting at the table over there, and we're going to be around. Or if it's just anything you guys are working on that you think you want to just talk to us about now that you know about Blacklinks, we'd love to network with you. Check out our webpage, and then as Dave mentioned, he's giving a talk tomorrow. Definitely check it out. It's at 11 o'clock on the state of GNU Radio acceleration device support, where he's going to talk about how we've accelerated GNU Radio for FPGAs and GPUs. Thanks.
All right, thank you guys. All right. So, next up we have Capture the Signal Challenge. So I will kick off this video. I don't know much about it, but here we go.
Hey folks, good to be here. I'm very happy today to present you Capture the Signal. This is a contest we came up with about 4 years ago with Federico. He's in call with me today, and Jonathan, colleague of us at Trend Micro. The idea of Capture the Signal is to have a contest in which contestants have to reverse radio signals that we distribute either over here at conference or streaming over the internet. We wanted to make this contest flexible in a way that we have both script kiddies, or people that never got into reverse engineering signals to learn something, as well as more advanced contestants that can tackle more difficult problems. So we started the contest really in 2018 at a conference like PACSEC and Hack in the Box. This is because we had contact with organizers, and they were very much happy to have like a village in which people can show up and play with us. And then we extended in 2019 to additional conference, for example, in Vancouver, as well as in Hack in the Box Amsterdam. We also developed a system in Amsterdam in which contestants could play remotely in a kind of hybrid environment where they could join us from internet basically. And for that, we developed a framework to be able to stream these signals over IP. And that came very much useful over the last 2 years due to the lockdown imposed by the regulations, in which we run the contest entirely over the internet. So for that, there are a few challenges, especially when it comes to regulation of the fact of not being able to transmit over the air. For example, when we run at Hack in the Box Abu Dhabi, we were not allowed to transmit these radio challenges over the air. That's why we came up with the first idea of voice over IP streaming. And for that, we use GNU Radio, and Federico now is going to tell you pretty much all the framework we develop, both to stream the signals over the air as well as to receive the signals. Especially the part for receiving the signals is very much useful when you want to play with us in order to connect to our radio infrastructure.
Okay, thank you, Marco. What the framework will provide is that, which is the most important thing of having the CTS as a release tool, is that the framework will take care of everything that is not focusing on a challenge, that is distracting you from developing a challenge. So if you're a challenge developer and you want to have contestants solve your challenge, you just focus on developing a GRC flow graph as you would normally do, and the framework will take care of tunneling and dividing the spectrum into slices and mapping them to a port range and so on. And on the other side, I will show you later, the contestants will also have support from the tool to be able to receive signals as they would in a concrete on-site with a real transmitter. What we ask the developers is to, as I said, focus on developing a GRC and make sure that you make it configurable and parametric. That's why I highlighted down there a CFG file, which contains, it's an init file, native format supported by GNU Radio, where you can specify parameters and various settings for your signals, so that when you deploy it and you want to change it later on, you don't have to reopen GNU Radio Companion or do any heavy editing. You can simply change the signal, maybe to adapt it to another conference and make minor changes. And then together with that, you have the signal GRC, of course, and a few other files that are needed to support, for example, if you have Python requirements and so on. And then we have a make file that will automate the building, the compilation of the GRC into Python, and any other automation that you need to do in the deployment phase. So we wanted the experience of the CTS deployer to be very easy as running Docker. And what will happen now is that, for example, in this case, we have one signal up and running, but if you want, you can bring up all the signals at once and the contestants can start playing. And as I said, on the other side, the experience is very smooth because the contestants will run a client which will connect to a ZMQ streamer, essentially, on whatever server you want to host this. And then what they will have is a FIFO, which they can use as a receiver of IQ samples. So the experience is to tune to a FIFO if you want, which most of the tools support out of the box. And then what they have is that the tool will inform them of the sample rate, of the sampling rate, sorry, and then they can start receiving a signal as they would be receiving it with, for example, in this case, GQRX or Osmocon or even GNU Radio, of course. So what you will experience at GRCon 2021 is unfortunately not the full CTS experience, in the sense that we don't have enough time to assist you during the conference, because if we stream live, of course, we want to be able to assist contestants in case they have any problems and so on. But unfortunately, our schedule could not, we couldn't change our schedule for this week, so we decided to still host it as an offline challenge, as an offline series of challenges, which are still linked together in some way that you will find out while playing. Essentially, one solution to a challenge will give you hints to solve the next one and so on. So for now, what we ask you to do is to head over to cts.newradio.org and create an account to the scoreboard so you can start reading the instructions as soon as possible and hopefully have fun and play. And we hope that will inspire you to bring the CTS to your event. What you can do, if maybe you like it, you can host it. You can host your own CTS, and that's why we decided to release it at Black Hat Arsenal 2021 in the USA. And here you find a link to the full-size video. It's 40 minutes where Marco, myself, and Jonathan Anderson go through the details of the CTS. We explain to you how the internals work, the little bit of story of CTS, and we'll explain you how you can host it. It's very modest requirements, so with a simple AWS account and a few $100, you can run it very easily for an entire week. Thank you for watching this far, and have fun reversing signals.
All right. So next up, we have sponsor lightning talk from Peraton Labs. So you might not recognize the name Peraton Labs. This is because it's a recent name change. Before it was Perspecta Labs. Before that was Vencor Labs. So you might have seen us along the way somewhere. So rather than me blathering on about the company, we have a video about one of our solutions for situational spectrum awareness. So I'll let Andrew Portune do the talking here.
Good day, and thank you for your attention as we discuss the Secure Sense system, designed by Peraton Labs as the next generation spectrum situational awareness system. My name is Dr. Andrew Portune. Visibility to the electromagnetic spectrum is increasingly critical to a wide range of different applications. Those applications could be static in nature, or mobile, or even multi-system. They could consider coordinated system optimization, or the performance of reliable operations in spectral environments that have become congested or contested. When we talk about spectrum situational awareness, we're talking about 5 key areas. The first is time-frequency visibility, which considers what parts of the spectrum are being used and when. The second area is geospatial visibility, which looks where in the world the spectrum is being used. The third is signal visibility, which considers what types of signals are present and whether or not they're interfering with other things that need to be going on. The fourth area is real-time spectrum situational awareness, which considers knowledge of current spectrum usage and how that might be leveraged. And the last is historical spectrum situational awareness, which looks at how the spectrum has been used in the past. SecureSense was designed to provide answers to all 5 of these areas. When we look at the SecureSense system, it's comprised primarily of 3 different elements. The first are low-cost ruggedized sensors. The second is a back-end server which performs multi-sensor data analytics, aggregating data from multiple sensors together in a way that's not possible with just a single sensor that has been deployed. The third area is interfaces to command and control, as well as access to different spectrum data products that are prepared by the system. SecureSense was designed to meet the 8 different features that are shown on the right, including ruggedization, flexibility, scalability, affordability, analytics, accessibility, customization, and adaptation to changes in the environment. These 8 principles direct the system towards providing robust spectrum situational awareness. Peraton Labs has designed its own ruggedized RF sensor hardware to be core to the SecureSense system. These include high-performance sensors that are designed in small form factors and intended to be low cost. The objective there is to allow for the deployment of a broad range of sensors in remote areas, to have a network of sensors that in concert could provide more access to the spectrum situational awareness required for an operation than you'd get with an individual sensor. Sensors can be mounted to static locations, slid into backpacks, mounted to vehicles, so on and so forth. We've also provided access to third-party sensors and telemetry units that could be incorporated with the system, as well as multiple data and power options for the system. The second element of SecureSense is the server, which takes in data from SecureSense sensors as well as third-party sensors, performs a range of different microservices which are easily extensible and customized for different applications, and flows data out through a range of external interface APIs to either our own web-based user interface or third-party platforms such as EWT, ATAC, or the Microsoft HoloLens. We also have the ability to send out alerts and notifications via SMS text messages or email. SecureSense has a host of different features that provide a broad range of spectrum situational awareness. Everything from signal geolocation, spectrum visualization, ad hoc command of individual sensors, to aggregated spectrum data products such as composite spectrograms and mapping of spectral energy distribution, either historically or in real time. The system is also capable of providing precise geolocation, as well as direction finding, customized alerts and notifications, and triggered activities. In summary, SecureSense was designed to provide that next generation of spectrum situational awareness to meet current as well as emerging needs in a broad range of different environments. Through a network of low size, weight, and power, low-cost sensors, we provide affordable coverage and flexibility that's scalable to meet deployment needs. The system has intuitive displays of spectrum utilization, as well as automatable system behavior for real-time spectrum situational awareness, and access to historical as well as the real-time data. In summary, SecureSense gives actionable spectrum information to enable operators to achieve operational requirements in complex, cluttered, and demanding environments. Thank you again for your attention. My name is Dr. Andrew Portune. Please feel free to reach me using the contact information shown here for more information on SecureSense.
Hi, I'm Steve Croft. I am a researcher at UC Berkeley, and I have a joint appointment at the SETI Institute. And I'd like to talk a little bit about how we've been using GNU Radio in the context of SETI, the Search for Extraterrestrial Intelligence. So some of you may have attended previous GRCons. I spoke a little bit about what modern SETI entails. Essentially, we are trying to look for the needle in the haystack of a signal that might be an indicator of extraterrestrial intelligence. So this is sort of, people think of tinfoil hats and going out and getting kind of grainy footage of UFOs, flying over cornfields in the Midwest. We try and bring the science and the engineering to the search. The idea here is motivated by the recent research results that there are probably tens of billions of Earth-like planets in our own galaxy, and so we actually just want to go out and do an experiment and see if there's life elsewhere. And we can do that essentially by using powerful radio telescopes. Also, we're using optical telescopes, really a range of facilities. But one of the facilities that we use is the largest steerable radio dish in the world. This is the Green Bank Telescope in Green Bank, West Virginia. 100-meter diameter dish. That's our chief engineer, Dave McMahon, standing looking up at the dish there. For a sense of scale, you might be able to see there's some folks that have just rappelled down from the underside of the dish. They were painting the dish, which is a pretty big job. And we actually have a video on our YouTube channel if you want to go. It's a 3D, not virtual reality, but it's no, it is VR, I guess. It's not 3D. But if you have a headset, or you can look at it in your browser as well, you can actually pan around and look as we ride up the elevator on the telescope and across the walkway there, and then up to the feed platform up near the top, which is actually kind of higher up than the Statue of Liberty up at the top. It's a pretty impressive piece of engineering. So one of the hats that I wear is I'm the project scientist for Breakthrough Listen on the Green Bank Telescope. Breakthrough Listen is the largest search for extraterrestrial intelligence that we've done, basically, as humans to date. The Breakthrough Prize Foundation, Yuri Milner, the sponsor, pledged $100 million over 10 years to really re-energize the search for extraterrestrial intelligence. And so we've got a big team at Berkeley, at UC Berkeley, where the initiative is, the science program for the initiative is headquartered. And then collaborators around the world, including at Green Bank, but also at Parkes in Australia, at the Meerkat Telescope in South Africa. We're working with some folks at the SKA. You're going to hear a keynote from Anna Scaife later in the week, who's not working with us directly on the SETI project, but is involved with SKA. So there's a lot going on, and a lot of it is driven by radio and by radio engineering and trying to ingest as much radio data from these telescopes as we can. On the SETI Institute side, we have access to the Allen Telescope array, which Derek mentioned earlier this morning. It's a 42-element array up in Hat Creek, about 4 hours north of the San Francisco Bay Area. 42 6-meter antennas, flexible back ends, so we can really, unlike with the Green Bank Telescope, we can sort of go and play around a little bit more hands-on with the ATA. We have a workshop coming up on Wednesday afternoon where we'll be taking you through what we can do with the ATA, not just for doing the primary goal of the SETI search, but also there's a lot of radio astronomy, but also we've done observations of satellites, we've done observations of deep space probes, and we're using it as a test bed, essentially to kind of understand the radio environment that's up there. We had a hackathon up at the ATA. I think this was mentioned this morning already. We're hoping to run another one of these probably sometime next year, so just keep an eye out, and we'd love for some of you to come along. Even if you have very little interest in the search for extraterrestrial intelligence, then maybe you want to come along and play around with some of these dishes and the back ends that we have up there, and we'd welcome your participation. So, here's just a little kind of snapshot. Well, some of the folks at the SETI Institute, not just working on SETI, there's actually kind of a whole range of research going on in astronomy and the search for life kind of more generally at the SETI Institute. And then, there is the stuff that's going on with the ATA sort of above and beyond the SETI search, including, and this is actually some work that came out of the GNU Radio project here. So, making images of radio galaxies, and you're going to hear in a couple of minutes from one of our students, Iwei Chai, who was working with us this last summer, working on integrating these backends with GNU Radio, and so you can actually kind of pull the ATA in as a source into a flow graph and play around with the data that's coming out, which we think is really fun. So mentioning our internships, if you do know undergraduate students that are looking for paid summer internships, there's one at the SETI Institute, there's also one at Berkeley SETI Research Center. We open applications in December with a deadline of, I think, February of next year. If you know smart students that would like to get hands-on with some of the data or with some of the hardware, then please encourage them to apply. Through this sort of collaboration with GNU Radio, we've had some fun, particularly with our friends at DeepSig, both in terms of actually coming up to the ATA and helping out with the hackathon, installing their OmniSig sensor up there, but also bringing it to some of these events like these exhibits that we've had at a couple of places where we think it's a really nice tool for visualizing the radio spectrum, visualizing the haystack in which we're looking for this needle of a signal that may have come from beyond Earth. It really is a needle in a haystack problem, so you have to understand the hay that you're looking at basically to look through to find something interesting, to find an anomaly. So again, we're using a whole range of telescopes around the world. If anybody has any interest in chatting about what we're doing in these various places, from optical telescopes through to radio at various wavelengths, please do come find me afterwards and chat. I'll be here all week, and I'd love to sort of figure out with you all how we can expand the work that we're doing, how we can integrate you into what we're doing, and if you have sort of smart ideas about ways that we can collaborate, then yeah, I'd love to chat. Thanks.
Hi, I'm Barry Duggan. I've been involved with GNU Radio about 2.5 years and have done a lot of work in the documentation area. And in doing so, realized that a beginner has an overwhelming amount of information and realized they needed a good way to get started and know where to go, a roadmap. So I wrote this page called Newbie Guide to GNU Radio. It's in our wiki. So if we look at that, it covers the main page of the wiki, tutorials, block docs, repository, our mailing list, and chat rooms. So let's look at each of those in turn. The main page shows an example flow graph, how to get started, what is it, how do you install it, so forth. The tutorials provide a complete course from absolute beginner through intermediate level expertise, and then for developers has details beyond that. So there's introduction, the GNU Radio Companion, which allows you to create flow graphs, understanding sample rate. A number of simulation examples are given here, which do not require hardware to execute, and then goes on through a lot of other interesting topics as well. The block docs is a listing of all of our individual blocks, and we have 471 of them so far that are documented. I don't think we've missed any, but hope not. So let's look at one in particular, the correlation estimator. If we go to that block, it gives a brief summary of what it is, lists all of the parameters, what they do and how to set them, and then has an example flow graph. Now this particular example exists in the GitHub tree for GNU Radio, and there's a link to it right here. And this is for the correlation estimator, and there is the correlation estimator block in this flow graph. And then this one has a example output. When you execute it, it shows various places in the flow graph and tags that show up. And then the general format we have also lists the source files. And as you can see, we still have work to do on this one. Now this particular flow graph has a link to the source code for it. So if we click on that, we get this formatted listing of the code of the flow graph. And it's in the GitHub repository, which is where all of the GNU Radio stuff is. And it's in the digital group, and then every group has some examples. And then this is under the dmod folder, and there is the particular flow graph we're looking at. Now, if you want to copy this and paste it into a local file to try to run, this is a formatted HTML page. So what you need in order to copy that code is to click on this raw button right here. And when you do, that will give you the unformatted file ready for you to copy and use. Now going back to the newbie guide, we have a mailing list, and it allows people to ask questions and then get answers to them. And we have a page that describes the mailing list and guidelines for posting and the lists themselves. And then you can submit questions to it, and you can also, well, here's the links to subscribe and to view. And then the chat describes a chat server, and we use Matrix. But if you happen to use an IRC bridge, then the libIIO IRC server is bridged to the Matrix. And so you can get to it either way. But if you're new to it, I recommend you use the Matrix because it's got more rooms available besides what's bridged from IRC. And please read the basic etiquette on how to use the chat before you dive in. So this is a quick overview, and I hope it helps you get going in the right direction. And I always welcome questions, either now or on a Matrix chat room. Thank you.
Okay, next up is Iwei Chai. I mentioned our student earlier from University of Pennsylvania. She was a student with us this summer at Berkeley SETI, and she's going to tell you a little bit about what she was working on with the Allen Telescope Array. Thanks.
Hi everyone, my name is Iwei Chai. As Steve said, I'm a physics student at the University of Pennsylvania, and this summer I was working with Wael Farah up at the Allen Telescope Array to develop a GNU Radio SETI data processing pipeline. So just a bit of quick intro to the ATA. It's a radio interferometer composed of 42 6.1 diameter antennae. It covers frequencies from about 1,000 to 15,000 megahertz. and is operated by the SETI Institute at Hat Creek Radio Observatory in Northern California. Its main science goal is to search for technosignatures, which will appear as narrowband signals drifting in frequency over time. And so currently the data processing backend of the ATA will take in antenna data and pass it through custom hardware to produce a raw file, which is then turned into a filter bank or HDF file, which is then analyzed through a software called TurboSETI. So TurboSETI is a software for asynchronously identifying potential technosignatures. The key function which does the searching is called find Doppler. And what that does is it reads in a header of metadata parameters from the filter bank or HDF5 files. For example, the number of find channels, the first frequency, the observation time, and it maps these parameters to a data matrix found in the file. And then this is what looks for the technosignatures. The problem with this is that TurboSETI can only handle filter bank or HDF5 file formats, which poses a problem for users without access to the custom hardware that they have up at the ATA. So why GNU Radio SETI pipeline? The aim is to have all data processing run from Telescope to TurboSETI via GNU Radio. And the benefits of this is that it will further the ATA's capability to perform technosignature searches, as well as just make SETI more accessible for amateur radio astronomers and smaller observatories. So the key components of the pipeline we designed with two things in mind. Firstly, we wanted to analyze a high spectral resolution product, but at the same time, secondly, we didn't want to write any data to disk. So under the GNU Radio version of the pipeline, what we have is radio antenna data coming in through the ATA from a US RP source, and then we channelize it first through a polyphase filter bank followed by a fast Fourier transform to produce a NumPy array stored in RAM. After that, we shape this NumPy array into the data matrix that we want in a buffer, and then we apply an adapted version of TurboSETI, which doesn't need to analyze filter bank or HDF5 files, but can directly analyze the data matrix in RAM. To do that, we needed to sort of adapt TurboSETI, and so here Luigi Cruz and Richard Elkins were very helpful in sort of doing a lot of the developing of TurboSETI stream. So this adapts the original find Doppler function from the original TurboSETI software, so that the user running the flow graph can specify metadata parameters in GNU Radio. And the new imaginatively named Doppler finder function would just map these parameters to the incoming data matrix. And this allows us to perform somewhat synchronous analysis on small observation lengths of about 60 seconds. And so a large part of my project this summer was developing the GNU Radio TurboSETI module, which currently consists of two key blocks. Firstly, the find ET buffer, which is what shapes the NumPy array running through the flow graph into a data matrix, and then passes it into the find ET block, which will run TurboSETI stream on the data matrix and tell us if we've found anything interesting. So this is an example of the flow graph with one channel. As you can see, we have data coming in either from a US RP source or from a recording done with the ATA. It's passed through the polyphase channelizer, and then the FFT, and then the find ET buffer and find ET blocks. And currently we have this flow graph running to about a maximum of 1 megahertz sample rates. Here is a test of the flow graph with a Chang'e 5 recording done by Daniel Estevez. So you can kind of see the output of the waterfall plot and the frequency. And this was at a 480 kilohertz sample rate to have a 60 by 480K data matrix. And you can kind of see the output in the command line when running the flow graph. So you can see that it kind of gives you the hits, and then here's just a screenshot of the DAT file that it outputs with the metadata parameters specified in the flow graph. Currently, for the one-channel flow graph, the TurboSETI search time is between about 1 to 5 seconds, which is pretty good. It's well below the 60-second buffer that we want. And a way to kind of boost the bandwidth is to add more coarse channels in the polyphase channelizer. So here is an example of a 4-channel pipeline. The maximum here is around 4 megahertz, and this also does up the search time to about 15 to 20 seconds, but it's still below the 60 seconds that we want. So the next steps is to begin using the pipeline with the ATA, but also to potentially add a function that will automate the plotting of hits in the find ET block code. And lastly, just a huge thank you to Luigi Cruz and Richard Elkins for their help with Turbo SETI Stream, as well as Daniel Estevez and Derek Kozel for lots and lots of advice on working with GNU Radio, which is something that I had never done before this summer. And the project was funded by Breakthrough Listen. If you have any questions, I can be reached at this email, and further documentation and code is available on the project GitHub repo. Thank you.
All right, thank you, Iwe. And next we have Hash, who is going to show his work on reverse engineering smart meters. Handheld or lavalier? Good handheld. Yeah. Yep.
If you haven't installed TikTok, I highly recommend not doing it because it's easier to kick heroin than TikTok. I guarantee it. But I'm glad some people are on TikTok. Let me just, I'm telling you, that thing's crazy, man. Okay. All right, so I prepared more of a video presentation for today, and I'll narrate as I go through it. So what I'm going to talk about is smart meters. They're the power meters. They're on the side of your house, the side of a building, usually the round thing. They used to have little spinning dials on them. Now they're all electronic, and they transmit their data back wirelessly. And so what you see here is a drive from my house in North Texas down to Dallas and back up. And these are all the smart meters. Sorry. These are all the smart meters that I received along the way. And so those red dots are all a different meter that I received with a USRP B200, my laptop, and an antenna stuck on top of the car. And what you see there, that D003 is the meter ID, and the 1767 is the number of days it's been running. Basically, it's uptime that they broadcast. And so you can see all this. And this became interesting to me as I live in Texas. And in February, there was a big freeze, and we all lost power for like a week. And so this information they were saying was super secure, and they didn't want to tell anybody about the outage information, all this stuff. And I thought, well, I've been kind of receiving this stuff in the clear for quite a while now. And that seemed interesting to me. So this is basically kind of like the culmination of the last probably couple years of research, I would say, that I've been doing on this. So this is me. There was a DEF CON talk I just gave. I would say this isn't my background at all. I do this strictly for fun as a hobby. GNU Radio, electronics, reverse engineering. And I mention the names. That's a smart meter right there. Landis and Gear, who makes that smart meter, and Encore, who is the power provider in my area. I don't do that to name and shame in any way. It's just this talk is very specific to that meter and that power provider, and so I don't want it to kind of be viewed as a general talk about all meters or all providers. And so you see kind of a bit of my lab in the background. So I don't know if anyone knows who this guy is, Travis Goodspeed. So he gave a good talk a few years back called In Praise of Junk Hacking. And the premise of that talk was that you shouldn't do what I'm doing because it attracts a lot of undue attention from people with billion-dollar wallets. And instead, you should reverse engineer all the stuff that's inside the smart meter, but that's inside other kind of stuff that doesn't really matter at all, like the CC1020 transceiver chip or the microcontroller. And so find something else that contains that device and reverse engineer it there. And then that way, everyone kind of knows there's an issue with it, but you aren't attacking these kinds of systems. And so when I watched it at the time, it made great sense, and so I kind of kept my research quiet. But the challenge I found is that there's a lot of things that happen, like these kinds of attacks. And I think, as this equipment stays out in the field longer and longer, it just becomes more vulnerable to things. So I thought, why not just talk about kind of the elephant in the room, these devices and what's contained in them and how well they work and how secure really they are over time. So luckily they put together a great video that'll kind of give an overview of this system. It's all I'll voice over their marketing video. Their voiceover is a little cheesy. And so this shows a neighborhood, and inside the neighborhood they'll show a meter, and so they make devices kind of for gas meters and power meters and all these others. And so what they did initially inside is they have a few different models. Some of them have a separate transceiver board, some of them the transceiver board and the metering's all on one, but they'll report back the metering wirelessly, and so it's all over a mesh network. So when the meters transmit, they relay their neighbor's data as well, and they bounce it back across this network, as you'll see, up to a device that if you look around, if this is in your city, it'll be up on a pole somewhere, usually a power pole, that's called a router or a collector. And that device aggregates all that data from the meters, and it sends it back to the power company. Either it relays it at a higher bit rate, kind of in the same spectrum to this thing you'll see here called a collector, or sometimes there's a cellular modem that's inside that router that's on a pole where it's kind of like a combined router collector. And this is just one I found near me driving by a substation that I show there. And then it goes ultimately back to some kind of a command center, I guess, in the power company. Now, when I first started looking at this, I found this paper on the IEEE. Obviously, a lot of this information is hard to come by. It's not like they're publishing the specs anywhere. And it's not open standards as far as I can determine. And so this RF mesh systems for smart metering was written by a couple of people at Landis & Gyr. And funny enough, the test system that was deployed was based in Dallas. So there's a bunch of maps in there of stuff that show meters in Dallas. And this part was the most interesting to me. They had what they employed, they called a geographical routing protocol. And so it used the latitude and longitude of the location to route messages across the network. And so I thought, what is that? Like, is it GPS aware or how does that work? And I was thinking myself, like, could you craft a message that would ride across this network? So I wondered, how could I get some gear to play with this? And, you could go take one off a house somewhere, but it'd be tough to talk about it publicly. But turns out eBay has everything you would ever need, and it's priced pretty well. And I'm fairly certain that on a long enough timeline, everything that's produced, no matter how secure, ends up on eBay. So this is I guess inside my lab, kind of in quotes at home, and you'll see I have a lot of this gear. I've been buying it over kind of a long period of time, so I didn't all pick it up in a day. And so you see a bunch of meter circuit boards there, the round ones. There's some of these modems that are the square devices. I have some commercial meters and residential meters from whoever's selling them on eBay for whatever purpose they sell them on eBay. I'm not really sure. And then GNU Radio that's pretty much running constantly. Capturing, we'll talk more about this flow graph and what this is a little later, but I capture kind of large amounts of data from the area around me to try to understand anything that's happening and try to discern something out of this data. And so that white thing you see on the bottom left there is one of those collectors that was on a pole. I didn't take it off the pole, but somebody, it came somewhere from a pole and it was on eBay. And then that's a Faraday cage that I use to isolate some of the signals when I'm doing testing. And at first when I was doing tests, I wasn't sure what was going on, so I wanted to isolate everything. So I started kind of by reverse engineering the circuit boards. And so just, with a meter toning it out, that's the M16C processor. That one is. The other one was a Teridion microcontroller used to do the metering, and this is the CC1020. That's the transceiver chip made by TI. And one of the other interesting things to me about this was, inside each one of these units is a massive relay that can switch 240 volts at 200 amps 10,000 times, according to their data sheet. I haven't tested it. But what you'll see here, it's got a little motor, and you can send a signal to it. There's an optical port on the front of the meters. That will allow you to control this. And they also say it can be controlled over the mesh network. So basically, you can call up to have power turned on. They send a signal, and a few seconds later, the power turns on, and vice versa, I imagine, if you don't pay your bill. And so that's it. You see there opening and closing as I kind of power the motor. And so that's part of kind of a big part of the analysis. You know, how secure are those messages? How secure is that system? And how do you craft a message to cause that to happen wirelessly? So along that pursuit, I used an FPGA and some glitching to dump the firmware out of the microcontroller. And so this is it you see in Binary Ninja right now, where I'm trying to step through the assembly and figure out what all this stuff is. This is actually the bootloader, and it's only 4K, so it's an easier thing to kind of start with because, you know, like I say, this isn't my full-time job. And the other thing's 384K of assembly, and so it's quite a bit to try to step through and figure out. But even with the bootloader, you can see it's a bit of information to try to dive through. But a fun weekend project. And so this, everyone here is familiar with. This is showing the spectrum. It's 902 to 928 megahertz. So it's about 26 megahertz of bandwidth plus a little over the edges that I'm trying to grab and look at this. They frequency hop within there at about 240 channels. They're 100 kilohertz spaced and about 9600 baud. So when I first started, I wasn't a GNU Radio expert. I started with this. If anyone's familiar with this device from Great Scott Gadgets, it's basically a CC1020 with a USB port that you can plug into a computer, and I could listen to a single channel of data. So I'd set a frequency somewhere, and I just listened to what came in. And since all the meters are supposed to hop evenly across this, I'd hear a decent amount of data, and I could set a sync word, and I'd be very sure that the data coming across was pretty good. At first, I was using this clock recovery block in GNU Radio and had just a shoddy experience trying to get data and be sure the data was correct. And so, you know, ultimately though, I was like, GNU Radio is, you know, it's like the pinnacle of doing something like this. And so I can't stick with this little single channel device. I got to figure it out. And so I did actually get that clock recovery thing to start to work, and the key piece that allowed me to do this was I figured out how they do the CRC calculation on the data they send across. And so I was actually able to verify if the data was correct or not and discard the packets that weren't correct. So what this is basically 1 megahertz worth of stream coming in to a polyphase channelizer that I split across to 10 channels. And then, you know, and there's probably a better way. This was just the way that I figured out at the time, right? Then I feed across to what you can see is 10 of the exact same things, and I dump it to a file that appends the data. And so that kind of worked. I was pretty happy with it. It was the first time I ever received more than one channel of data. And so I thought, well, all I have to do is do that 240 times, and then, you know, bam. So, so I basically turned this into a hierarchy block and built a hell of an AMD computer with a GPU and all this stuff, and basically, am I going? Yeah, and basically did that. And so I was super pumped because 240 channels of data is coming through. The machine's redlining, right? It's just maxed out, everything you can flow through. I probably couldn't have done any other calculations on this thing, but it is dumping all this stuff to a file. And so, you know, like I did a victory dance and then realized like I don't know what the heck to do with it, and stuff's kind of landing all over the place, and it's not really coherent. So who knows who this guy is? So this is Jacob Gilbert. He gave a talk a couple years ago here, I guess. I was sitting in my house in December, kind of stressed and disappointed that I thought I figured it out and I didn't. And I came across this. I'll refer to him from here on out as the Savior, because nothing would have happened until I found this talk from him. And so what he talks about is this frequency hopping spread spectrum toolkit that Sandia had released that basically is the much smarter way of doing what I was trying to do. So it grabs all of this data, it packetizes it into PDUs that then I can just analyze these small packets of data that are already ready to go for me, and I don't have to deal with trying to handle all the other stuff. And so this is that GNU Radio flow graph where he has the burst tagger, and he turns those bursts into a PDU, sends it across, and does the quadrature demodulation and all that. His talk is a much, it's an hour-long version of this that's much better at explaining all of what's awesome about that block. But when it comes down to the bottom here, what it goes into is the ability to specify a sync word, which will then narrow down all these different things that it's receiving to just what I want to receive. And it's doing FSK demodulation of these signals that are coming across. And so down here is where it specifies the sync word. I'll put in the sync word that is for the smart meters that are used by Landis+Gyr. This is this. At first, when I started, I just did kind of the 1010 at the front, but later on, I took a closer look at it. And so they send 52 bits of just the 10 for sync, but then they have a header, and so I was matching on the header that's on the bottom left, which is this 00FF2A. And you'll notice it has start and stop bits, like kind of the old RS-232 protocol that's sent across. And what I noticed when I went back and looked at some stuff again is that they did a couple cool things. So they segregate out systems by using a CRC. So different power providers could be right next to each other, and they'll each have their own unique, they call it a network ID. It's a CRC, the calculation that's done, so that one power provider doesn't see the other power provider's data. But then I think they're trying to advance their system. And so they have this version 1 to version 4 hardware. I have versions 2, 3, and 4, various devices. And they all use that sync word on the bottom left. Now on the bottom right, I got a hold of a newer device, a version 5, and I noticed I wasn't seeing any of the packets. So I went back all the way to the PDU, and I looked at it, and what I realized is they stuck an extra 1-1 in there, and they violated the start and stop bit so that any of the older generation, I think, just discards it. But it allows the newer generation to have backwards compatibility. So they kind of have these two splits. They can do it with the sync word, and they can also split with the CRC calculation. So, and I also realized, actually just probably like a few days ago, that I can specify multiple sync words in this PDU align block, which is pretty cool. So I fed both of those in there now. Now we get to the block that I actually wrote. This is the, it's in a thing called GR Smart Meters. I call it Grid Stream. And so there's a few things that I specify in there that I let you specify. There's a CRC value that's used to pick which network you want to listen to. There's a thing to enable or disable it, because when you're first listening to a network, you don't know what the CRC is, so you need to capture some packets to figure out what it is, and I'll show that. And then I let you, select a meter ID, like if I just want to listen to my own meter. There's a couple different packet types that I'll show here in a minute, and then the packet length, because the length, there's various packets that you might want to filter on. And so this 5FD6 is the CRC for Encore, where I am, and I list that on the GitHub page. And so this one, so there's a couple main packets. This is the one that you see when I visualized all the GPS data. It's called a 5.5 packet. It's basically broadcast once a minute or faster. And inside here, where it says WAN address over here, that's actually the GPS address encoded in. And I have a separate YouTube video of how I figured out what all that encoding is and all that. And then there's their uptime they broadcast and the meter ID and some other information that I'm kind of slowly figuring out what it is. And so that's just a broadcast packet. I think it's saying I'm here and here's where I'm located. And then there's also these packets like this one. There's a various different links of them that are called a D5 packet. And these are basically like a routed packet. So there's a destination meter, a source meter. There's some information that it's asking it to relay across the network, and then some common information that I kind of put on the right-hand side. And so some of that I know what it is, and other parts I'm just kind of slowly figuring it out by capturing data and analyzing it when various events occur. Like it's a good event. When a power outage occurs, then you can capture and see what's different there. And so right here, what I'm specifying is I want to look just at the 5.5 packets and just at the ones that are of length 23, which are those GPS kind of filtered packets. And I use this socket PDU to send it to a TCP stream as well. And then I have a Python program that I wrote that is what actually decodes it and outputs the GPS coordinates and the timestamp kind of data. And so that's what we'll see here when it runs. On this flow graph, I was using a hack RF I had at the time to test it out. And so you see the packets showing up in the bottom left there when I crank up the gain a little bit. And so that's it, picking them up, decoding them. I think right now I don't have the CRC turned on. And so it was part of a demo video where I was showing somebody how to actually set this up and capture the data. And so it does a much better job than that clock recovery block that I had been using before. This is actually really reliable for grabbing data, and it became even more reliable recently when I kind of shrunk down my sync word and wasn't trying to make it conform to the full thing, but just shrunk it down a bit. So when you get this data here, what I'll do is I'll come over here to this page and I show at the bottom there's a tool called RevEng, and it basically is for reverse engineering checksums. So if you don't know the checksum of something, you can feed the data in there along with the CRC, and it'll try every known checksum with every known value and spit out what that is, which is super valuable if you're working on stuff like this. And so the beginning part of the packet all the way up to the length, you don't really need to use. It's everything after that all the way down to the checksum at the end, and you copy and paste. If you give it 4 values that are good, it will spit out what the calculation is. So you don't have to give it a lot of data. It does have to be good though. So you do, sometimes it's kind of trial and error to figure out which packets were good and which ones weren't. And so that's it here. All you really have to specify is the width. So I tell it 16 bits is the CRC and a -S to search, and then you just give it whatever data you want and it will output the result from that. And so I'll feed in 4 of the packets right here and tell it to do a search, and that's that 16 bits for the width. And so it knows then that the 2 bytes that are on the end of each one of these packets, it should consider the CRC that it's going to try to figure out. And I mean, it runs super fast. This isn't a supercomputer that this thing's running on. It's just a regular little laptop, and it outputs a result almost immediately. Especially for 16-bit stuff. And so it tells you that the poly's 1021, which is pretty standard for this stuff, and it tells you the initialization value is 5FD6. Now the network ID that they use is actually different when you look at their documentation. It's actually like the CRC of that value gives you the network ID, but for this block that I wrote, that doesn't matter. And so then I'll go back here, I'll turn this back to true so that we're only going to feed out packets that we're actually sure are the correct packet. And I'll start up this Python application, which is going to decode it and spit out the GPS coordinates. So once just from a pure reverse engineering standpoint, once I figured this out and was able to get packets that I knew were good, then it really helped kind of further things as well, because I knew I wasn't chasing weird bit errors that I thought maybe was something special that I should be looking at. And so this just connects to that output from the flow graph and starts dumping this data. And so what you'll see is it dumps the meter ID, then the uptime in seconds, the uptime in days, the latitude, longitude, and then just the current timestamp, so that if I wanted to plot this visually as I was driving down the road or something like that, I could kind of show the meters pop up as it reads them. And so I take this to basically a website that'll do kind of a CSV to KML converter. And so I can feed that then into Google Earth to do the visualization. I was trying to get with somebody to write me a real-time deal to pop it up, like as we kind of war drive Dallas, to pop up all the meters in the area. And so that's kind of still a work in progress, but it does support the RTL SDR or anything else. So someone with just some super cheap hardware could go out there and capture the data. And so ultimately that's what culminated in this view that you see here of me driving down the road. I wasn't cruising slowly or anything. I mean, that's what you pick up going freeway speed, 70 miles an hour. down the freeway and back. And so everything you've seen so far is just passive listening. But what I realized is that in order to really do some serious testing, I need to transmit back. But then, I can't transmit back on the network that's around me. So what I've been working on most recently is basically trying to construct my own smart meter network with all the stuff that I've got and what I understand about it so far. So what you see on the screen here is actually the collector application that was running inside of that white device there. It turns out that thing runs Windows 7. The whole collector is in a folder and it runs standalone. It's written in .NET, and so I've been teaching myself to reverse engineer .NET. And so this is me taking this thing apart. I have a separate video that shows kind of the teardown of this and discovering all these devices. But I was tweeting something and someone responded and said, hey, have you looked inside that thing? Like there's an SSD in there. And it'd been sitting on my floor for like 8 months. I hadn't looked at it, other than to unplug the big battery to prevent it from trying to talk back wherever it was trying to call. And so I did this teardown video. I started taking it apart, and so when the power goes out, these things can relay the messages back. So like when power goes out on your house, it transmit that message back even once power goes out. So everything has enough time to do that. And so this is one of the modem boards. That's the latest one, that version 5, like what you see inside these other ones that I have. And then when I pull off this metal plate, that's when I saw this Windows computer, and that was pretty much my face when I saw that it had an SSD. And I didn't even know it was running Windows at the time or anything. I mean, it was just kind of jackpot after jackpot as I took that apart. And so I tried initially to run that image itself in a virtual machine and get it to run. And it didn't want to run in a virtual machine. And I thought, well, what if I just take the whole folder onto a different Windows computer and run it? And sure enough, it ran just fine. And it would start right up. I segregated out the network just so it wouldn't try to phone home and do whatever it's trying to do, which turns out it doesn't really do that. And you can also load up dnspy, which basically lets you decompile .NET. And I mean, if assembly, like if that processor was able to do this, who knows what I could do on this system right now. But with .NET, literally everything comes out. It's not obfuscated in any way. You see all the function names, everything about this thing is right there. And you can just click run and run the whole thing in debug and set breakpoints, and I mean the full kind of jackpot of reverse engineering. And so when I ran it, I was trying to figure out, I plugged in one of my modems with a USB to serial converter into that computer, and it started talking to it. And so I had the whole thing kind of set up in that Faraday cage and everything dialed down, trying to figure out, what's it going to do. And I realized kind of quickly that I needed to set some parameters in this application. So there was an INI file. And so I opened up that INI file, and this is what I found. And I thought, well, I'm pretty accustomed to look at it just raw hex. So I was like, I wonder what is what. But I couldn't make anything out of it. And so I thought, well, I'll just start looking around in the .NET application. And so I started trying to figure out how to explore in there. And what I noticed was that, when it loads this INI file, it runs this decrypt block routine. And so it reads the file. And so I set a breakpoint there. And then sure enough, I could see all the variables in memory, and there was that INI file. And so I could see the values. But I tried to change it in memory, and it wasn't having any of that. And the whole thing would just crash. So I thought, well, here's the encrypt block portion of that. I thought, well, what if I just take it? You see right at the top, there's contents, and then there's array. And so it takes contents, it encrypts it into array, and it writes array. And I thought, well, what if I just delete array and write contents instead? And so, sure enough, the INI file shot out. So then I just changed the decrypt routine to not do any decrypting, just to load the file. And now I can set all these different parameters in there and adjust it to try to drive which modem it talks to and how it configures the network. And so that's it running now. The most important thing there is it says timekeeper, like up at the very top at the right. So when I would turn on my own meters, they would transmit a bunch of stuff, but they wouldn't really do anything because they're not finding a network. And so I can't really have any kind of, the simulation isn't really real, right? Because it's not going to do anything until it finds a network. And so when I set this up and got it running, it was talking to another meter. I set both of their network IDs the same because I figured out all these debug modes in the meters and had to set some pins low to enter those special modes and things like that. And they started talking. And I noticed the meter, it stopped transmitting the message it was kind of looking for a network, and it's time synced to this thing. and they started communicating. So now I kind of have the initial makings of my own smart meter network that I'll add some more devices onto. And so that's one of the packets from the meter itself that's in my house that it received and popped up, and that's how I knew, okay, these things are really talking. I'm also receiving the whole thing with GNU Radio at the same time, listening to try to basically say, what do I see here? What did I see in GNU Radio? And how does that stuff correlate? So I've been publishing a ton of videos on YouTube about this stuff. It's kind of like a choose your own adventure book. Like, this is as far as I am in this thing. This is a website I have with some wiki links and things at the bottom where I publish all this information. And I just reverse engineer it and I kind of publish as I go. So, you know, I'm here, we're all here together. There's nothing really further that I've figured out. And so, you know, I just kind of publish this journey as I go and share it with everyone, and whoever comments and gives feedback, then maybe that changes the direction of the journey I go and what I try to look at. That's the GitHub page with the smart meter blog. Jacob Gilbert helped a lot getting that to 3.9. And this is some contact information about me if you're interested in following along with what I'm doing or contributing. Thanks for your time. If you have any questions, I'll take them as well.
All right, thank you so much, Hash. We're on. All right. Do we have any questions for Hash?
I'm also here the next few days, so questions over a beer or also.
All right. In the back corner, can you speak really loud?
No, so there's actually a news article that was released about this where the journalist reached out to Encore, who had no comment, like everybody else, and said the system's very safe and secure. The company Landis & Gyr did reach out to me at one point. They were pretty, the guy that reached out was pretty nice. But so far, you know, I'm kind of careful with what I release because ultimately I don't want to black out my own city, but I do want to make sure that whatever vulnerabilities exist and wherever we are in a state of security, we're all looking at it in the open together, and I'm not letting somebody else find it that's going to black out my city.
Aaron.
Thanks. I understand that some of these smart meter devices, like the Landis & Gyr ones, also have Zigbee support. Have you done any investigation into that at all, or did you encounter that in your reverse engineering?
Yeah, so they do. So I actually have some boards with me that I brought. Surprisingly, I was able to get on the airplane with. And so we can take a look at those and chat about it if you want. They have 2 radios in them. They have a 900 megahertz mesh network, which is at CC 1020, and they also have a Zigbee radio in as well. That Zigbee radio used to be used in Dallas, where I am. You could actually connect a device to it, and it would show you your power readings live and everything else. They released a press statement some year or so ago saying they shut it down because it wasn't being used. Whether they shut it down because it wasn't being used or because of some other issue, I don't know. But it was probably another interesting avenue of attack, but not used there anymore.
All right. And I think we could probably take one more question if anyone else has one. If not, thank you so much, Hash. That was an amazing talk. All right. right, so next up we have Oscar Ekholm, who was our Google Summer of Code student. And Derek mentioned this talk earlier today, and I will let him do the explaining in the video.
Welcome to this talk on the new view-only mode feature of the GNU Radio companion, the GRC. I'm Oskar Ekholm, and I'm a computer science student at KTH, Stockholm, Sweden. And I've been working on this view-only mode feature during the summer for this year's Google Summer of Code. And today I'm presenting an overview of the feature. So, just to summarize what the view-only mode is, briefly, to start off. The view-only mode is a GRC feature which allows the user to open and view untrusted flow graphs without having to evaluate the untrusted code contained in the block parameters. So, you might be familiar with block parameters actually being Python expressions. So, in this block parameter window we can input some Python code and have the GRC evaluate that, which is a nice feature to have since it allows us to have some parameters which dynamically depend on some outside factor. And in this specific example, it's simply convenient to just input the calculation and have the GRC actually calculate the value. And then the evaluated value is used by the GRC for running and generating the flow graph, but also it is shown on the block surface. And whenever you're saving a flow graph, these expressions are saved to the GRC file, but not the values, the evaluated values themselves. Or that's how it has been before the view-only mode, at least. And this is fine and dandy, of course, when we created the flow graph ourselves, since we know the Python code that's inside and we trust it since we've done it ourselves. But if we were to download some flow graph from the internet, we might not be so trusting, and we wouldn't really know what is contained in that flow graph. So I want to show how we could embed some sort of malicious code in an expression. So let's take this expression, for example. I know it's sort of hard to read due to the colors, but it basically says import OS module and then execute the command touch home Oscar GRC test. So we create this file GRC test in my home directory. And this is executed once we load the flow graph. So we open the flow graph, the GRC will execute and evaluate the expressions of the parameters, and thus a file GRC test is created in my home directory. And of course this is quite a harmless example where creating a file isn't a huge deal, but we could easily change this command to something else. Perhaps we could remove our home directory, and of course I would not be so happy if I loaded a flow graph and it would just erase all of my files. So this sort of illustrates the problem that we're trying to solve. And I also just want to add that there are other expressions which are evaluated when loading the flow graph other than the parameter expressions, such as the ones in the image here, where we have some parameters, and in this case we have the hide parameter, which has this conditional. So there are expressions originating from outside the flow graph file itself, but rather from the definitions of the blocks that the flow graph uses. And I will get back to this soon. So let's start to look at the actual view-only mode for a bit. So here. Okay, so let's say that I've downloaded some random flow graph from the internet, and I don't really trust it yet. I don't know what's in it, so So before we have trusted a flow graph, it's regarded by the GRC as untrusted. And whenever we open an untrusted flow graph, it will open it in view-only mode, meaning evaluations are disabled. So, for example, let's say we have this complete.grc file downloaded, and here I'm just running the GRC from source, but of course you will probably run it in some different way. But let's say I want to open this file. And we see it opens, and since it is untrusted, we are actually in view-only mode right now, but it looks like completely the same as if we were not. And that's the point of view-only mode. We want to view the flow graph as it had been loaded using the evaluations. But in this case, we haven't actually evaluated anything on our machine. So we might move around some blocks, or we might just check out the parameters and the info about each block. So for example, here we have this example from previously. And you can see that it renders the evaluated value, even though we haven't actually evaluated it yet, on the block surface. And whenever we try to make some modifying action, such as if we were to, I don't know, for example, we can add a block, or we could change a parameter, then we would get a prompt. So if I show here, we get this prompt, which says that you cannot do this action in view-only mode, since we would need to re-evaluate the parameters or the expressions. So to perform the action, you have to trust the flow graph. And you can trust it once using this button, or you can trust it indefinitely. If you trust it once, it will be trusted in this session, and whenever you close and reopen the flow graph, it will be untrusted again. And if you trust it forever, it will be regarded as trusted between sessions until you manually revoke that trust. And we can also see this expression overview here, where there is a list of all the expressions that would have been evaluated if we were to trust the flow graph. So, for example, you can see the expression from the example and some other expressions here. And you can see that it has the origin of flow graph. So these are expressions that are actually stored in the GRC file, in the flow graph file. But if we scroll down a bit, we can also see other expressions which originate from the block definition. And this is what I showed you briefly before, where the block templates may contain expressions as well. So you can see those here. And of course you can see the name of the blocks where it belongs to. My window is quite small, but of course you can resize it and drag the borders of the table and stuff. Right. So, and if perhaps you think it's too cluttered in the view where you have all of these block definitions, so you can choose to only show the flow graph expressions. And this provides an easy method of just looking at the expressions, and then you can sort of gauge if this flow graph contains malicious code or not. So there are not that many expressions here, but if we were to look at all of the parameters, we would see like literals and identifiers. But since we know that those are not malicious and cannot be malicious in any way, we filter those out. So here we are only interested in the parameters where they actually contain some sort of interesting expression that the user should take a look at. Okay, so for example, we can choose to cancel. Avbryt is cancel in Swedish. So we choose to cancel, and you can see the block was not placed. And if we were to add a block, we can choose to trust it, and we have the block. And additionally, I also want to show that under the file tab, you can enable or disable view-only mode. So perhaps you're not interested in using this view-only mode. So just disable it in the file tab using this toggle button. or you can press the Manage Trust, and you open this Trust Manager. And the Trust Manager basically lists all of the flow graphs which you have trusted indefinitely. So you can see here which I've trusted indefinitely, and you can add new flow graphs here, or you can remove flow graphs from that list. And you can also add an entire directory where so basically you add a directory, and all of the flow graphs contained within that directory are also regarded as trusted. So for example, this is a directory, whereas this is just an individual flow graph. We can, for example, remove it from the list. Alright, so there is one more thing that I would like to show you about the view-only mode. But first I need to explain sort of how the view-only mode works under the hood. So before the view-only mode, only the parameter expressions were saved to the flow graph file. But after view-only, I've also made it so that the parameters evaluated values are saved as well. So the view-only mode works in the way that it loads the evaluated values and uses those for displaying the graph, instead of having to evaluate the values. But in the case where such values are missing, for example, if we have saved some file before introducing the view-only mode, we have this problem that we do not have evaluated values, but we also do not want to evaluate the expressions. So the behavior in those cases is that a prompt is displayed immediately on opening the file, and the text is slightly different to describe this case. And the typical expected workflow is to just look at the expression overview and sort of gauge, okay, so I can't view it in view-only mode, so I either have to trust it or just disregard viewing it at all. So I look at the expressions in the overview, and based on that I make my decision. If I trust it, it will open just as normal. And you're basically outside of view-only mode. If I were to close this and then cancel, it would simply just close the page. So that is pretty much it for the view-only mode. There is a pull request live on GitHub which contains the code for what I've shown you today. And I'm still working on some small details before it's ready to merge, but hopefully I can get that done as soon as possible. And so please check out the pull request, clone it and try the feature out, and provide feedback if you have any. And to summarize, opening untrusted flow graphs introduces the risk of running untrusted code, but the view-only mode solves this problem by allowing the user to open and view untrusted flow graphs without having to evaluate the expressions themselves. Using the expression overview, the user can sort of quickly gauge how if the user should trust the flow graph or not, if the expressions are malicious or not. And that has been it for today's talk on the view-only mode. So thanks for listening, and thanks to everyone that has taken part of the project in some way, and especially thanks to my Google Summer of Code mentors, Sebastian and Mark.
All right. Thank you, Oscar. Next up, we have Matt Knight from Radio Resilience, who is a diamond sponsor of this conference and is going to step us through the Radio Resilience competition for this year. All right, Matt.
Hey, can you all hear me? Let me see. Is that legible? Cool. And can I do an audio check on my computer real quick? All right, let's see.
Thank you for that.
Cool. Awesome. All right. Hey, everybody. Happy Monday, GNU Radio Conference. Good to be here with you after a couple of years being away. My name is Matt. I'm here representing Sid and Mark. We're going to talk about the Radio Resilience Competition, which is a new type of virtual CTF that we're going to be running here at GRCon this year. So the Radio Resilience Competition was sort of envisioned by Sid Sibrandy, who founded Radio Resilience LLC. In a completely separate context, Sid is also the founder and CEO of, co-founder and CEO of GitLab. This activity with Radio Resilience is completely separate from that, has nothing to do with that, so just want to put that up front. Sid has reached out to myself and Mark Newland, who are the co-founders of Agitator, a wireless and security consulting company, to help him put together this competition and run the event. So we're happy to be here representing Sid in that capacity. And if you want to reach out to us, you can email us. It's just our first names at radioresilience.com if you want to track us down after this. So we're going to briefly run through sort of the motivation and background behind this competition, why we wanted to run this after many other wireless competitions have been run, what we think we're bringing to the table, and why we think it's exciting. We'll tell you a little bit about what we've learned from competing in past SDR challenges. And then we'll tell you about the Radio Resilience competition that we're going to be running here this week at GRCon. And I'm going to try to encourage you to compete, because it's going to be fun. And we'll wrap up with the demo. So first, I'd like to start with a message from Sid, our sponsor. So here we go.
For that, Matt. I've been running a software business for the last couple of years. But I also studied applied physics. And I had to go back in my 5th year of studying and go back and do one course that was left of my first year. It was electricity and magnetism. It was the hardest thing to do. And I never imagined myself going back to that. But when I found software-defined radio, I was hooked. It was super interesting and it's super approachable. So as I started getting into it, I found GNU Radio, which was awesome. And but I also discovered the DARPA SDR competitions, the Spectrum Challenge, and the Spectrum Collaboration Challenge. And that got me thinking. And got me thinking about the progress in radio. Because I think one of the biggest benefits has been unlicensed spectrum. Now that we have unlicensed spectrum, where you don't need permission to broadcast, there's been so much innovation. I cannot live without Wi-Fi. And it's working because devices are well behaved. But I think we should put the bar higher. On the internet, we don't assume that everyone is well behaved. And I think that as things get bigger and there's more users and more devices, that will be the case for the radio spectrum as well. So we gotta make sure that radio works, even if people are intentionally trying to interfere. And when we have protocols that can deal with that, I think it will make radio work better also when there's no interference, because it will just be more reliable, period. And to get there, I think a competition is a great way.
Cool. So a little background on Sid's motivation for starting the RRC here. So what brought Mark and I sort of to Sid's attention was Mark and I competed in DARPA's Spectrum Collaboration Challenge that ran a couple of years ago. If you all have been coming to GNU Radio Conference or following the space for a couple of years, you probably saw this a few years ago. I know some of the some people that were involved in organizing the competition are here today. I see you, Craig. Hey, Craig. So Mark and I competed as a individual team. We were Team How Make Radio, because we were scrappy and sort of coming at it as two individuals. And the SC2's objective was to develop collaborative radio links that wouldn't interfere not only with themselves, but with other radios in the environment. And it was a really cool competition. They built some amazing technology. It was very complicated, though. So it was a very complicated game structure. Scoring was complicated. The number of variables that we were optimizing for, like the state space, was so huge. DARPA built some really incredible infrastructure, which was also pretty complicated. And some of the downsides there was it meant that we had a very slow iteration time. It would take upwards of 30 minutes to get back 10 minutes of data. And there was also a lot of sort of bespoke development that went into developing for this really powerful, but very complicated hardware testbed. So coming out of this, we definitely learned some, or picked up some things that we knew we wanted to reflect in this competition, and things that we wanted to sort of build on as well. SC2 definitely reminded us that the PHY was still a space where there was a lot of work to be done. If you looked at the types of PHYs that different competitors were building, they all looked very different. There was a lot of OFDM, but there were also some other sort of more off-the-wall things that were kind of cool. So we figured there was still plenty of room to run here on just the PHY. We also wanted to optimize quite a bit for the infrastructure and sort of ease to build and develop on, so that we can lower that barrier to entry and get more people involved. And in doing so, we wanted to tighten up the development cycle, so that competitors could iterate really rapidly and locally on their designs before running them sort of in the larger centralized infrastructure. So that brings us to RRC, which I'm excited to tell you about right now. So the Radio Resilience Competition is a new kind of virtual CTF, and our key objective here is to improve the state-of-the-art of resilient radio links. If you've heard of RRC, maybe you heard us talk about it last year. We announced it at GNU Radio Conference 2020, and we soft launched it last fall with 6 teams. We ran sort of 5 warm-up events called scrimmages, and then had a final event where we had a number of different scenarios and sort of put together all the things that we built up to till then. And in spring 2021, we ran another series where it was more of a continuous competition. Rather than having these sort of events that we focused our efforts on, we built more automation so that we would run daily matches and automatically publish the scores on a daily basis, so that competitors could iterate and see that improvement day after day. So why should you compete? Well, we're at GNU Radio Conference. RRC is built on GNU Radio. I'll tell you more about the infrastructure when we get a little bit more into it, but GNU Radio is all over the infrastructure that runs this thing. It's also fully open source. So the infrastructure is open source, and SID, being a big believer in open source, is asking that all competitors open source their submissions under an OSI-approved license. Again, just fostering the spirit of collaboration and innovation. And also, it's fully virtual. So given that this is a unique event, a unique year, where a couple hundred of us are here in person, a couple hundred of us are virtual all over the world, this is a CTF that we can all compete in, whether we're here in Charlotte or if we're just on the internet too. And everybody's on equal footing in that regard. So if you want to compete, we've got a couple events that we're going to be highlighting throughout the week here. First thing you should do, if you're even remotely interested in competing, hit that link up top, radioresilience.com. There's going to be a link from that page to register. Go ahead and register right now, and that'll kick off some things in the background that will stand up the infrastructure for you to submit your image if you decide to build one and submit it later. So do that now, get that out of the way, and you'll hear from us with some more information. So other events, sort of how the week is going to go. We're featuring 3 rounds. The submissions are due Monday, Tuesday, and Wednesday at 6 p.m. Submit your image before 6, and we'll run it overnight, and then we'll provide your update sort of in a daily leaderboard. We'll post the results online prior to the lightning talks we're going to give, so you can check back earlier in the day to see how you did and make changes and things like that. but we will do a daily check-in as well where we'll talk about how things are going, what we're seeing, that sort of thing. I'm also going to be here in person today and tomorrow, and then we're going to be online, virtual on the GNU Radio Matrix channel, on our own Slack as well, for any help and questions and things like that you might have. And then Thursday at 4:30, we're going to announce the final results as well. We've got some great prizes this year. So if you win, one lucky winner will take home a B205 Mini and a MacBook M1 Pro, MacBook Pro M1. There you go. So some pretty sweet prizes. It's a pretty sharp, SDR development rig there for you, for whoever comes in first. Terms and conditions apply. U.S. residents only, unfortunately, due to like tax and contest laws and stuff like that. Stuff the lawyers figured out. And see our website for all the full terms, but nothing too crazy there. So how does RRC work? So RRC takes place in a fully virtualized testbed that we call the simulator. Very creative name. In the simulator is an environment where basically what we have is we have GNU Radio running in a number of different Docker microservices that are all orchestrated with Docker Compose. Docker Compose is basically a framework for running different Docker images sort of in concert with one another. Provides some networking and some other sort of glue that makes all that nice. The signal processing is primarily in GNU Radio and Liquid DSP, and we provide a fully working environment, including a submission-ready image out of the box. So if you git clone the simulator and just run the build script, you're ready to compete. Obviously, you can then take that and build on it, tweak the knobs, make it perform better, but we really wanted that on-ramp into the competition to be as friendly and accessible as possible. So for local testing and development, the environment is fully reproducible locally. It requires, I believe, Ubuntu 20.04, but you can run it on your laptop. It does not run in real time, so you do not have to have a beefy machine. The simulator is like sample synchronous and will slow itself down to match whatever hardware you're running it on. For the competition, however, we're going to take your image and run it on an EC2 box that we have. Everybody runs in the same box. And then we'll post your results and logs and things like that somewhere where you can pull them down the next day. If you want an architecture diagram, here's what it looks like. There are 5 different kinds of microservices. Only one of them you will be developing code for. So where you see those 2 blue arrows, points to 2 microservices called the Blue Radio container TX or RX instance. What we're going to do is we're going to take the image that you build and we're going to create 2 instances of it, and the traffic flows for scoring purposes from the transmit radio to the receive radio. All of the IQ that's being generated is getting, by these different microservices, gets pushed into this microservice called the channel emulator, which takes all those IQ streams, muxes them up, and then redistributes the product out to all the other microservices for, ingestion, reception, decoding, traffic that interferes with the blue radios, etc. And if you want to get more into detail, we really break all this down on the website. There, if you go there and then you click on the go to the radioresilience.com and then click on the competition page, we break down the architecture and what these different microservices do in a little bit more detail than I can provide right now in 25 minutes. But so the key takeaway is that there's all this stuff happening in the background, but the only 2 things that you're touching are those blue radios. So the rules are also available online. But basically our traffic marshal container, the one on top, it's a container that we control that you don't touch, is going to generate a number of packets for your blue radios to deliver to each other. What the packets contain is a sequence number, a bunch of pseudo-random data, and then a signature. And what we're doing when we receive a packet back from you is we're checking, first of all, to see if that signature matches, and then to see if we're getting contiguous sequence numbers from you. And if you drop a packet, that caps your score. So basically your score at the end of this is equal to the highest contiguous sequence number that you receive. And the reason why we do that is because we want to incentivize the development of really reliable radio links. So you could deliver, if we send you 1,000 packets to deliver, you drop the first one and then you deliver the 999 that follow, I'm sorry, your score is 0. But if you deliver 998 and then drop the penultimate packet, then your score is 998. So again, you're just going to be modifying those two, the blue radio microservice there. Those are the paths in the simulator, the ones in bold there that are going to be interesting. Everything else is just there to run the environment, but those are the things where you're really going to focus your attention when you go to do your development here. And again, just to highlight, we're providing a fully functional node to get you started. You don't need to make any code changes to compete. If you want to just build it and then resubmit that image, you will be entered and eligible to win that prize, assuming you meet all the other terms and things like that. I do encourage you to make some code changes because the stock image is not very good. This is what our interference scenario looks like. I mentioned that we're here to develop resilient radio links. To make it interesting, we do have some different scenarios that sort of shake up the channel that your radio will have to find different ways to get around. This interference pattern, if you can, I don't know if you can see with the contrast on the screen, but basically what you'll see is there's an interferer that's pulsing on and off periodically. It's also getting stronger as the match goes on. So the first pulse is kind of weak. You can see it's sort of blending in with the top of the baudline interface there. And then towards the bottom, it's pretty strong. So you have an interferer that's getting stronger as the match goes on. You also have some time-based elements that you can maneuver around if you want to stay quiet when the interference is on and then try to sneak a bunch of traffic through when it's off. You can get clever like that. As of now, we'll see how everybody does with this, but the plan is to just run this one scenario all week. If people are struggling with it, we might make it easier, but this is the plan for this week. So to get started, go to radioresilience.com and register. Go to the website and read about the terms, the architecture, the rules, and things like that. And if you want some help getting started, we're doing an optional workshop somewhere around here at 3:30, so 30 minutes after this talk ends. I will be there in person. Mark will be online to help out with any online support, things like that you might need. In parallel, you can clone the simulator, gitlab.com/radio-resilience/simulator. Pull that down, follow the README. It's got all the instructions you need to build and run the simulator, to build your first radio image locally and run a full match locally as well. And then after you complete that first registration step, what we're going to do is we're actually going to make a GitLab project for your team. And the reason why we do that is because each GitLab project brings with it its own unique container registry, and that's how we're going to take your image. So what you're going to do is you're going to push your image up to that GitLab container registry, and then we're going to pull it down when we go to run and evaluate it. When you register, you'll get sent instructions on how to do all this. It's pretty straightforward. If you have any trouble with it, we're here to help you out with it. And then we want you to iterate on this too. So make changes to your blue radio locally, run it, see what happens to your score. Score goes up, that's great, keep going that direction. Score goes down, maybe try something else. And then daily we're going to be running those matches. You can pull down your logs and things like that to see how it's running in our real environment, which for all intents and purposes should be identical to your local environment, but your logs will be available too. And we also will render your IQ and sort of sync up your score in real time, and you'll be able to watch that on the website on our leaderboard as well. And we also want to sort of foster a community of collaboration here too. So we have a Slack channel that we'd love to invite you to. Feel free to jump on there and share ideas. If you want to try to find people to team up with, by all means. And then if you have any technical support questions, we just ask that you submit those on the simulator GitHub project as issues so that we can sort of answer them once for everyone. I'm going to roll a quick demo, pre-recorded, and I'll narrate as we go here. If it cooperates, we'll see. Oh, yeah, here we go. Back up here. Okay, so what we're going to do is we're first going to modify the base image, the base blue image. So the font's a little bit small, but what we're doing is we're turning down the modulation to PSK2 and we're turning off all the FEC, and we're going to run it, and we're going to see a score. And then we'll tune up the knobs, and we'll see how the score improves, and we'll show sort of the cycle of how you can run these images locally and get feedback from them. This is on fast forward because the match takes a little while to run. Here you can see the interference pattern sort of, on the right-hand side of your screen, pulsing on and off. You got your big PSK2 channel in the middle there that's just, plugging away, doing its thing. For the purposes of time, I might try to skip ahead a bit, because otherwise we're just watching log scroll, and who wants that? Oh, whoops, I missed it. See if we can spot the score at the end here. Anybody see the score? There we go. Score 1,780 at the bottom there. So we're going to make some changes here to the configuration of the radio, and we'll run it again and see how we do. So we're going to turn up the modulation of PSK4. We're going to add some pretty basic FEC, 2 layers of FEC, and then we'll run it again and we'll see how we do. And off it goes. There goes the radio again, and I'll skip ahead for time. If I can. Multimedia on Linux is always a bit of a journey. Well, I'll let this run, but take my word for it, the score goes up. So you can pull down the simulator, get started with it locally, join the workshop if you have any questions about getting started or just want any help. And I really hope that you'll consider competing. We think this is going to be a fun addition to the GNU Radio conference program, and we hope you all enjoy it. Let me just find my slides as we wrap up here, and I think we are done. Let's see. Nope. There we go. Workshop at 3:30. Come find us if you want to play, either in person or virtually. Go to radioresilience.com to register, and thanks so much. Hope you'll consider playing.
All right. Thank you, Matt. All right. Do we have any questions here for Matt? He does have this workshop set up to go more in depth into the setup and getting involved in this. But any questions anyone here has right now? Sam?
So we had an online question about the U.S. citizens versus non-U.S. Or residents, I guess. But can you still participate and just not get the prizes? Is that how that works?
You can definitely still participate. It's just the prize eligibility, unfortunately, based on the.
Understood.
I'm not a lawyer. I'm just.
But you can still participate and compete.
Definitely still participate and compete.
Okay.
All the bragging rights in the world.
Okay. Any other online questions? All right. Any other questions? Anyone in the room here? All right.
There was just one online question. They want to make sure people understand that there are 2 different contests here. This is not the one associated with the conference.
So there is a CTF competition that's running as well. This is separate from that, but definitely play in that one too. These are both awesome. So I think.
Yeah, both competitions are part of GRCon. We just thought we would give people kind of a more traditional and then something very new and different.
Yeah.
And we thank you guys for bringing this. It's exciting.
Cool. All right. Thank you, Matt.
Cool. Thanks, everyone.
All right. Derek.
Yep. So we're into break, right? Yeah. So thanks, folks. We are into our next bit of break. So please do stretch your legs and enjoy. Right after the break, the Introduction to Signal Processing workshop is going to be starting. For in-person people, that is in Graham C, just down the hallway to the left. It looks like it's going to be a really amazing workshop. I've seen some of the animations and slides over the last couple days. and it looks like it will be excellent. Yeah, all of the source code and the images of that are available, so there'll be a lot of materials posted up. For folks who are online, if you are still having trouble finding the workshop links, please do drop in at the help desk or email grcon@gnu-radio.org. We know that there's a few people who haven't gotten that, whether they registered in the last couple hours or had other circumstances, and we want to get you into that. So thanks.
So the first thing I have to announce is our Azure Development VM. So this VM will be an image available on our Azure Marketplace. It will have GNU Radio built in, ready to go. Phosphor will work on VMs that have GPU enabled. We'll also have some other Azure tooling like the Azure CLI, which is just a way to interact with Azure, set up resources. And then we'll have remote in tools like VNC, XRDP. And then we'll also have our Azure Software Radio out-of-tree modules, which we'll talk about more in our main talk Thursday. So that includes the Diffie block, blob storage, and Key Vault, which I'll briefly talk about too. So just to give a quick preview of that. So, well, this is our Azure Marketplace. And here's basically just the sample of how that will look to create your VM. And we have some pre-configuration settings that will help you pick VM SKUs that we recommend that will optimize the image and help you set up, you know, the GPU-enabled VM if you want, or you can create it from scratch. So you can sign up today to get informed about our when the VM's released. You can also go to our Azure Software Radio GitHub page, which is right there on the screen, and that will have more information about how to sign up, how to set up the VM. And then you can also get a $200 Azure credit today. That's available for anyone. You can just search that. Anyone can get that. You can all be ready to go for when the VM's released. And so going on to our out-of-tree module, so the first block we did was Azure Blob Storage block. And you can think of this block as just works the same way a file sync and a file source works, but instead of, you know, reading and writing to disk like the file source, you know, it's going to read and write from Azure. So when you hit play, you know, stream the data down from Blob and write it back. In the future, we're going to support SIGMF for this. So right now, we don't support metadata getting written to Azure. We will in the future, and then those blocks will work just like the GR SIGMF source and sync blocks work today, but, you know, writing them and pulling them from Azure. And then the next block is our Azure Key Vault block. And so what Azure Key Vault is just a way to keep sensitive information secure. So those could be crypto keys, those can be any type of credentials. So if we go back to the blob storage block, one way to authenticate to blob storage is with a connection string. A connection string, just, you know, you give that to someone and then they can get access to your storage account. So you don't want to store something like that in a GRC file or a flow graph, or, you know, commit that into Python code, right? Because someone gets that connection string, they have full access to your account. So what the Key Vault does, and what the Key Vault block will do, it will pull that string down or any other secrets at runtime and fill those into the blocks that need them, so nothing gets stored in the GRC file or anything like that. And so this blob storage is just the first service that will need something like that. Or you can store, you know, if you need to encrypt a signal or something, you can store your crypto keys there as well. So I'll give a quick demo of this. So as you can see here, I have this flow graph. It's just going to generate a cosine wave. But if I enable these in our Key Vault block and our blob sync block, and in here, these is the Key Vault block, so it's going to pull down our secret string, which is that connection string I was talking about. And it'll pull down two other values to scramble the sequence. And these variables are accessed just like any other GNU Radio variable. So basically, you can see here, my secret string, you just access it just like you would a regular GNU Radio variable. So if we play that, it's scrambling the sequence and storing it to blob. And we'll stop that real quick. And then we'll just play that back from blob storage. So this is just storing it to a storage account in South Central US, which I think is in Texas. So now we're streaming that back. And I'm just using the Wi-Fi network for this, so not super fast speeds, but. and that's playing it back. And that's it. Thank you.
All right, thank you, Steve. All right. All right, so our next talk, let's switch this over. Our next talk is analog devices. So one of the more recent things that has been upstreamed into GNU Radio is gr-iio. Analog devices has a rich set of utilities for utilizing IIO instrumentation. So Paul Cercueil from Analog Devices is going to go more into IIO, libIIO, and how that is wrapped into gr-iio. A little bit of technical difficulty here.
subsystem or the audio subsystem or the input subsystem. So, hello everybody, my name is Paul Cercueil. I'm a software engineer at Analog Devices, and today I'm going to talk about libIIO and gr-iio. So I don't know if you noticed, but about 2 months ago, a new set of blocks were merged in GNU Radio, the gr-iio blocks, and I'm going to talk about this today. First, I can't really talk about gr-iio without talking about IIO. So I'm going to do an overview of IIO. Then I'm going to talk about libIIO. Finally, I'm going to show the various blocks that you can use in gr-iio. I will end with a demo showing well, how to use the blocks, and finally talk about the performance and future developments. So IIO stands for Industrial Input-Output Framework. It is a subsystem of the Linux kernel. It can be found in the kernel sources in driver/IIO. And it is basically for all the devices that don't fit in the hardware monitoring subsystem or the audio subsystem or the input subsystem. So in this IIO subsystem, you're going to find ADCs, DACs, VJs, PJs, magnetometers, gyrometers, and all kinds of sensors. It has wrappers to other subsystems. For instance, you can use a gyrometer, an IO driver for a gyrometer, and use it in the input subsystem. That totally works. It's widely supported by many vendors, including Analog Devices, of course, but also Texas Instruments, Xilinx, Qualcomm, STMicro, and many others. About the binary interface, so the IO subsystem has two main interfaces, the CCFS interface, which will contain all the metadata and allows you to set the parameters and configure really the radio. And then you have the dev interface, which you will have device nodes for each IO device, and it's used for streaming data from the IO device or to the IO device. Note that some devices only have the CCFS interface, the slow sensors, slow as in human scale slow, for instance, 10 samples per second or less. They don't really need to stream data. You can just read the data by polling an attribute. So these devices don't have a dev interface. For instance, to configure the gain control on an amplifier from Analog Devices, you would have to go to sys plus IIO, then go to IO device 0, which is the device that allows you to configure lots of settings. And in that folder, you will have the name, for instance, which is a device attribute, and then out voltage 0 hardware gain, which is the hardware gain for the first channel, and then out voltage 1 hardware gain, which is the hardware gain for the second channel, etc. So reading and writing samples. First of all, you need to enable the channel by writing the scan element / name of the channel _ EN, that stands for enable. After that, you just enable the buffer by writing the buffer/enable parameter. And finally, you just start reading or writing the corresponding dev node. There is a caveat to this, is that this is a slow interface because the data is copied between the kernel and user space. So to address this issue, Analog Devices developed a high-speed interface. It consists in a pool of buffers that are shared between the kernel and the user space. The kernel has two queues, one incoming queue, one outgoing queue, and it will endlessly going to pick one buffer from the incoming queue, fill it with the data coming from the DMA, then put it when it's filled to the outgoing queue. And then the application on the other side, on the user space, the application is going to dequeue the buffer of samples, read the data, process the data, do whatever it needs to do with the data, and then once it's done, just enqueues it back to the incoming queue of the kernel. And in this scheme, there is absolutely no copying of the data. The problems with this high-speed interface is it's specific to Analog Devices kernel. It is not upstreamed, and it is not upstreamable. It was probably upstreamable when it came out in the early 2010s, but now it kind of, there are better mechanisms that could be used in the upstream kernel for this solution. The other thing is it is not as simple. It uses IOCTLs. You can't just read and write data using a bash script, for instance. I think it will eventually be deprecated and replaced by an upstream solution, as I said before, probably based on DMA buff, for those who know. Next, I'm going to talk about libIIO. So libIIO is the project I worked on when I first joined Analog Devices in 2014. As of today, there have been about 53 different contributors in the code. The goals of libIIO is to provide an interface to the I/O subsystem and an easy-to-use one. Abstract away all the low-level details of the I/O framework, for instance, whether or not you're using the high-speed interface or if you're using the regular interface. Your application shouldn't have to care about this. And it provides a high-level representation of I/O objects instead of having to deal with lots of file names with really strange structure. Then you have device object, channel objects, etc. On its design, it was designed to provide a very simple, easy-to-use API, and it's written in portable C99. It's modular, it's thread safe, and it runs on Linux, Windows, OS X, all the major operating systems. Inside libIIO, you have different kinds of objects. You have first the top-level object, which is the I/O context. The I/O context basically contains all the devices that you would find, for instance, on your target board. Your I/O context object can have attributes, which will be, for instance, the kernel version, the operating system, etc. Your context can have zero or many different I/O devices. Your device can have zero or many I/O channels, and your device can also have a buffer connected to it. And all these objects, like device, buffer, channels, can have attributes as well. As I said before, libIIO is modular, so it has a clear separation between its high-level API and the backends. The applications using libIIO are compiled against the high-level API, and so which backend you use is completely transparent to the application. So there are a couple of backends. For instance, there is the local backends to use the locally connected I/O devices. You can have a network backend, USB backend, UART backend, etc. And since your application is compiled with the high-level API, there is no distinction between the backends. The API is the same, and as such, it can run with different backends. It doesn't even have to be recompiled, just works out of the box through USB or through network, etc. And this is a modular system because you can choose which backends you want compiled inside the library. You can compile only the local backend if you want to, only the network backend if you want to, or USB, or any combination of these. And the good thing with these backends is they allow libIIO to be used on non-Linux systems. So you can use libIIO remotely using the network backend or the USB backend on a Windows PC, for instance. And that's what makes it able to run on other operating systems. A small word about the applications that run on top of libIIO. We have the I/O utils, which are shipped with libIIO. I'm going to talk about them later. There is the I/O scope, which is used heavily internally at analog devices to debug hardware, and also by the clients, of course. There is the Scopy software, which is software oscilloscope and signal analysis toolkit that was designed for the M2K product from analog devices. And we have MATLAB, Simulink, GNU Radio running on top of libIIO, and then third-party apps where analog devices didn't have any was not involved. For instance, SDR Angel, GQRX, SDR Sharp, etc. The context can be, since there are different backends, the context can be identified with the URI. URI is basically just the address of IEO context. For instance, you would have a USB colon 2.8.5, which identifies the IO context at the USB address 2.8.5, or you have IP colon IP address 192.168.2.01. These are examples of IO of URIs that are using libIIO. A little bit about the command lines tools that are in libIIO. IO info is the most useful one, gives you an overview of all the information that libIIO has on the system, on the devices, on the channels, the attributes and their value, etc. IO@, which can be used to read and write IO attributes, IO read dev, IO write dev to read and write samples, and IO reg to read and write directly the registers. This is the output of IO info. I'm not going to talk that much about it. If you want to have a look after in the slide. libIIO can be used, of course, in C because it was written in C, but also in C++ using the regular C API. And we also have official bindings for Python, C#, and MATLAB. There are also third-party bindings for JavaScript, for Rust, for Julia, for Lisp, Haskell, and probably others. That was just from a quick search on GitHub. Now let's talk about gr-iio. gr-iio basically is the gateway between IAO and GNU Radio. It was created a couple of years ago, I think in 2015. I created them in 2015. I was out of tree until about 2 months ago, where they were merged inside GNU Radio. In gr-iio, you have a couple of blocks. You have, for instance, the IO device source block, which is the block that allows you to receive samples from any IO device that supports the dev interface. And here, for instance, as you can see in the properties, we just set the URI, the device name that we want to read samples from, the channel, and then the data is going to flow through the output of the block. The IO device thing is basically the exact same. You just set the URI, the device name, the name of the channel, and you can upload samples to the IO device. Attribute blocks. So they allow you to read, write, and update attributes, be it device attributes or channel attributes. The IO attribute source just reads IO attribute at a given interval. The IO attribute sync just writes an attribute, and the IO attribute updater generates the messages at a given time interval to be used with the IO attribute sync. Then we have ADI-specific blocks, the FMCOM2, 3, 4, FMCOM5, and the Pluto SDR blocks, source and sinks, which can be used with ADI-specific products. These blocks are actually just specializations of the I/O device source blocks. You can do everything you can do with a Pluto SDR source. You can do it as well with the I/O device source and the I/O attribute blocks. And now I'm going to present you with a demo, flow graph demo. I'm going to use the Adam Pluto device from Analog Devices. It has a loopback cable between the TX and the RX. It's connected over USB to my laptop. And on the other side, I have a gaming handheld that is connected over USB as well. That runs Linux, and the joystick is connected to an I/O device. So let's just start by creating a Pluto SDR source block because we want samples from the Pluto. So I'm going to do just this. We're going to configure it for 320 kilosamples per second, and with the given URI, USB 3.6.5. That's the address of my Pluto. I'm not going to leave the other settings to the default because I don't know what most of them do anyway. And we're going to leave the base frequency at 2.5 gigahertz, that's fine. And I'm just going to enable a time plot and a frequency plot so that we can see what we are receiving. As you can see, that's not very interesting. We're just receiving zeros. There's nothing going on. So let's actually actively send something on the TX so that we can loop it back to the receiver. I'm going to enable Pluto SDR sync that's configured for the same URI, same settings, same sample rate. I'm going to send it a 10 kilohertz sine wave. I'm just going to send a 10 kilohertz sine wave. And I'm going to enable this block, which is a Qt Ranch. That's a widget that I'm going to use to change the attenuation. So let's start. As you can see now, we have a beautiful sine wave. That's what we send on the emitter and receive on the RX side. And if I change the attenuation on the transmitter, as you can see, higher attenuation means lower amplitude, smaller attenuation means higher amplitude, just as you would expect. That's still quite a boring demo. What we can do something more interesting. Because right now I'm using Pluto, which is a product from Analog Devices, and I'm using the Pluto sync and the Pluto source. That's not very generic. That's still very specific to Analog Devices. But what I can tell you is that this Pluto sync, for instance, we don't really need to use it. We could very well use a regular I/O device sync. So I'm going to do just this right now. So I'm going to disable the Pluto SDR sync. We're going to enable the I/O device, the regular I/O device sync block. So it's configured the same way, same URI, USB 3.6.5. That's the address of my Pluto. We're going to use the CF809361 DDS core LPC, which is the device name where we can stream the data with the channels voltage 0, voltage 1. And what we have in the middle is just to make sure that the data is properly scaled to the maximum range of the DAC. There we go. Let's try again. And as you can see, we have more or less the same sine wave. What is not going to work, however, is the attenuation slider, because this was just setting a property in the Pluto SDR sync. And now we don't have the Pluto SDR sync anymore. However, we can still make that attenuation slider work using the I/O attribute updater and the I/O attribute sync blocks. The I/O attribute updater, what it is going to do is just send messages, key equals value, every given time. So now we just configure it for a 500 millisecond interval, and every 500 milliseconds is going to send hardware gain with the value that is set in the range. However, since we are setting hardware gain and not an attenuation, then the value needs to be negated. So this block just negates the widget value. Then the I/O attribute sync, we just say that the messages that we receive have to be returned to the 809361 PHY block. Sorry, 809361 PHY device to the output channel voltage 0. And now if we start again, we get the same sine wave, and as you can see, if I decrease the attenuation, then we increase the amplitude. If I increase the attenuation, then it reduces the amplitude, just like before. So now we're going to do something a bit more interesting. I'm going to disable all of this. We're going to receive data, like raw data from the joystick that is on the handheld. So I'm going to enable the I/O device source block, which is properly configured with the address of my handheld. We're going to use the JZ-ADC device, JZ-ADC device, which is the device that delivers the data, and using the voltage 3, voltage 4 channels. And just so that you can see, I'm just going to print them on the time sync, on the time plot. We have to scale the data. We're going to scale the data to 0 up to 2 range, so that it can be displayed properly. And the sample rate of this data is more or less 35 samples per second. It's pretty slow. So I press play now. We still have our previous data that is now pretty not interesting. This is the joystick output. As you can see, if I press up on the joystick, then my y-axis moves. If I press down, it moves the other way. And then if I move the x-axis, then the x-axis line moves. So the reason I scale this in the 0 and 2 range is because we're going to shape a signal that we're going to send on the sync. We are going to have 2 sine waves, one which is 10 kilohertz and one which is 1 kilohertz. And we're going to multiply these 2 sine waves with the value of the axis that we get. So to be able to do this, knowing that we have on one side the Pluto SDR sync, Pluto SDR source, which work at 320 kilosamples per second, and on the other side the I/O device source, which works at 35 samples per second, we need to a repeater block in the middle. So this block is going to repeat the samples from the joystick so that the 2 sample rates more or less match. Then we're going to scale the data so that we get in the correct range, convert them to complex, multiply them with the sine waves, just add the 2 and send them to the sync. And I'm going to keep this enabled because it's interesting to see. Yeah. And I think that's all. Let's execute the flow graph. And now you can see in the middle, we have the sine wave that we're receiving. It's quite small. I'm going to lower the attenuation a little bit. Yeah, they should be fine. And now, as you can see, if I raise the y-axis, so raise the joystick, the 10 kilohertz sine wave increased in amplitude, the value is in dB is much higher. And if I lower it, then it looks like we almost only have the 1 kilohertz sine wave. Then if I move the X joystick, you can see on one side I can really reduce the 1 kilohertz sine wave, and on the other side I can just make it more strong. So this is an example of how you can use the gr-iio blocks with a real SDR focused hardware, which is the Pluto, but also with something that was really not sought for SDR, which is just a regular joystick on a gaming handheld. Yeah, that's my demo. A little bit about libIIO performance now and gr-iio performance. On the right side, you can see the local backend performance. If you have buffers big enough, so 8K samples or more, then you can go as high as 60, 70 megasamples per second, not lose any data. If you have smaller buffers, then you might actually start to get underflows, overflows. On the IP backend, the USB backend, it's a different story. There, the buffer size really changes the sample rate that you can reach without losing data. Using a small buffer, for instance, 1K samples, then you're going to start losing data at 2 megasamples per second. If you use a bigger buffer, 16K samples, 32K, 64K samples, then you can reach maybe 8 megasamples per second, 10 maximum, without losing data. And above this, you're going to lose data. The problem is that the communication between libIIO and the IEO daemon, which is the server side of libIIO, is synchronous. You just ask for data, the server sends data, you ask again, the server sends again, etc. So if you have big buffers, that means you spend more time transferring data and less time asking for data. And if you have small buffers, then you basically just spend your time asking for new buffers. So there is really room for improvement using an asynchronous protocol and using a better mechanism inside the IO daemon based on DMA buff, as I talked before, so that there is no data copy within IOD itself. And so far we've had promising results with current experiments. It went from 24 megabytes per second peak to maybe 82 megabytes per second on the network backend with a Pluto. And that's my presentation. Thanks a lot for following. And if you have any questions, I will be glad to answer them.
All right, thank you, Paul. And if you have questions for Paul, he is on the GRCon talk, on the chat channel, GRCon Talks. So please send those questions that way. And thank you for Jeff Long for bailing us out of our technical issues. So we are switching over next to the man that needs no introduction. He's going to step us through MIMO diversity, and he has some live demos. So very confident, very brave to do live demos up here. All right, so we got the audio.
Okay. Hold your ears adjust in case, but I'm going to test the audio.
Yes, please. Do test because we have a sound.
Okay, so we see my whole screen over there? that better? Okay. Cool. Thanks everybody for coming. This is actually the talk that I was intending to present 2 years ago, which at the last minute I swapped for a latency talk. But don't let that make you think that I actually finished it 2 years ago. I finished it quite a bit more recently. I'm going to be talking about MIMO and easy ways to use it from within GNU Radio. So my first brush with MIMO came, actually I can remember back to when I was in 5th grade, and I was coming home from my friend's house in his parents' car, and they had the radio on, and there were these 2 flickering amber LEDs next to each other, and I asked what that was, and it turned out it was indicating which of the 2 antennas on the car was actually being used at that moment to generate the audio. And so that's actually a very early, this was in the 80s, this was early use of selection combining, and that's one of the techniques we'll talk about today. But really the motivation here is that you know, almost all the radios that you guys use all have MIMO, or most of them have MIMO capabilities. Even the original USARP1 from 2004 had MIMO capability from the beginning. But the vast majority of users never use the other channels, or they use it as a place to put their other spare antenna and then swap between them depending on the project. But my goal here is to make it so that we can all get good use out of and easy, low barrier to entry use out of those second ports. So first, in any discussion of MIMO, we have to talk about multipath. I'm sure everybody's seen this kind of a picture before, but basically RF propagation, you can sort of divide the phenomena into large-scale effects, which are the distance and spreading, and then shadowing and absorption, like from trees and things like that. And then the small-scale fading, which includes like blockage. Let's say it's a phone, you're holding it in your hand, or your head, there's blockage there, which will change over time. And so that works into fading. And then there's multipath. And that's really what we're mostly going to talk about today. So multipath is a phenomenon that can be both constructive or destructive. But for the most part, the constructive is not as helpful as the destructive is hurtful in most of our communication systems. And so we really try to mitigate this. And so, but what exactly is multipath? We know it's signals bouncing off of things, and those things can move, and the channel can change. But how do we characterize it? So first, if we start with the main categorization is it frequency selective or flat versus frequency? And then is it rapidly changing or slowly changing? And that'll be on the next slide. So, so if we look at flat versus frequency selective, we know we have a channel with all these reflections, but those reflections have to travel further than the main ray. And so there's some excess delay. And the maximum excess delay is the worst delay for a measurable multipath component. And so these are typically modeled with tap delay lines. And whether your fading is frequency selective or flat really depends both on how much excess delay there is, but how much bandwidth you're using. So just like as we always see in the Fourier transform, the longer the time, the narrower the frequency. So if you've got a narrower bandwidth that you care about, it's much more likely to be flat fading than if it's wider. Now, so how do we deal with non-flat fading? In many cases, we can ignore it, but usually it should be flattened for optimal performance. Excuse me. So, so how do we do that? Well, if you've got a single carrier, a single frequency signal, then typically you will use a conventional equalizer, which will try to invert the channel, or it could be a decision feedback equalizer, which has some advantages, things like that. Or you might have a spread spectrum signal, which sort of spreads it so that it's so that the frequency selective effects are not as bad because you sort of average over a wider bandwidth. Or you can use OFDM, and that's actually the most common way to deal with frequency selective multipath is OFDM, because what you're basically doing is you're taking one wide frequency selective channel and turning it into a lot of little, narrow, roughly flat channels. And so for the rest of this talk, we're actually not going to deal much with the frequency selective. It's mostly going to be flat, on the assumption that you would, if you had non-flat multipath, you would have fixed it through one of these mechanisms. And then we can really think about it in the flat sense. So now there's the question of constant versus time varying. So this is normally characterized with what we call the Doppler frequency, which is sort of similar to Doppler shifting, like from fast-moving objects, but this is more that the multipath components are changing delay and amplitude rapidly. And it sort of looks a little bit like Doppler, but don't confuse it like with the Doppler you see in satellites. So if the Doppler frequency is fast relative to what the sample, the symbol period is, then you have what we call fast fading. But starting from the beginning, we have quasi-static. So that means that the channel may vary, but not during a packet. And you can pretty much estimate the channel at the beginning of the packet, let it ride through, and then only re-estimate it for the next transmission. Next up, there's slow fading, which is during a symbol, it's pretty constant, but during a over a packet, it will change. And so that's the most common that we see. And so you do have to track within the packet. Finally, there's fast fading, where you have the Doppler frequency is much greater than 1 over the symbol time. And so that induces this Doppler modulation. And this really, it makes it no longer a linear time invariant system. It's still linear, but it's now time varying. And it induces the picture, what we see on the right, called the Doppler spectrum. And it's essentially modulating your signal. And when this gets very bad, it becomes very difficult to receive. So how do we model multipath? So there's two main distributions that are used, are the Riceian and the Rayleigh, and they're really just probability distributions. I don't think either Rice or Rayleigh did radio stuff. They were probability guys. But the difference is that Riceian has a line of sight component. And so, whereas Rayleigh is no line of sight component, and so what that means is Rayleigh is composed entirely of just the reflections, and you don't have the direct path. In terms of a difference in modeling, they're actually, if you have this K factor, and so if it's 0, it's Rayleigh, and if it's non-zero, it's Riceian, and the stronger K is, the more energy is in the dominant main path, and the less fading you actually get. So a K of infinity is just free space, right? There's no fading at all. And so it's a sort of a sliding scale, but we differentiate between Riceian and Rayleigh. And then there's the Doppler frequency. That's how quickly it changes. So if you look on the right, this is Riceian, and so you have your dominant main component, and then you have these random paths in addition to it. If this was Rayleigh, you wouldn't have this orange, and everything would be back here. And so the bigger the dominant component is, the less likely you are to go through the origin. But if there is no dominant component, you're very likely to go through origin. That's when you get the really deep fades, when you have a 0 amplitude or close to a 0 amplitude. So, I'm going to show a demo of this to help us get a feel for it within GNU Radio. So it's a pretty simple flow graph. Unfortunately, it doesn't all fit on the screen, so I'll scroll it for you. But we start with some noise and a constant, and I'll switch back and forth between them with a button. We throttle it, of course. We go through our fading model, which is already in GNU Radio, and thanks to whoever wrote this block, it's really good. I did have one bug fix, but it's really, I was like halfway through making my own and then realized it was in there. So that was a great, great thing to find. So then we convert it to magnitude squared, and essentially get the power of it, and we send it to a histogram and a time sync and a frequency sync. So I'm going to run this, and hopefully we'll see it all on the screen. Okay, we can't see it all at once. Okay. So first we'll start with a constant signal. So we're just sending 1 through the flow graph, and you can see it's just constant here. It's not changing. If I turn on the Doppler frequency, you can see it change. And so the higher the Doppler frequency, the narrower the more rapidly the path changes. Right. This is versus time here. So we'll slow it down a little bit. And then as we change the K factor, this is at a K factor of 0, so that's Rayleigh. So it's got really deep fades. You can see occasionally it goes below -40. And as we increase the K factor, you get more and more direct path, and so the fading gets less and less bad until at maximum, I mean, if you made it infinite, this would just be a flat line. And so this is, it sort of shows the continuum of the different types of fading. And then, but if we look at this in the histogram, I'm gonna change the K factor. So this is Rayleigh, and you can see the histogram is centered around. So all of these are the same total power comes in and out on average, right? Sometimes it's a stronger signal, sometimes it's weaker, but on average it defaults to 0 dB. But you can see, so there's this distribution, and you can get, you have significant content down to -30 that you can see here, but sometimes it's up to, -7, or sorry, +7 or +8 dB. As we increase the K factor, you can see that distribution narrows. And so it's still centered around 0, but it now doesn't get as great on the high side and doesn't get as bad on the low side. And of course, if we make it super high K factor, we basically don't have much multipath, and you can see it gets pretty narrow. So now I'm going to switch over to the noise-like waveform and lower the Doppler frequency, or actually I'm going to turn the Doppler frequency to 0. I'm going to put the K factor pretty low so that we can see this. And we can see this is flat fading because because we have no time delay. This is all of those taps in that tap delay line are all at time 0. So we can see that this is flat, and if we turn up the averaging here, you can see that it comes out to flat, right? Now, if we go back to a single tone, right, you can see there's a single tone, but as we turn up our Doppler frequency, wish this could all be seen at once, you can see, let's turn up the Doppler frequency some more. And I got to turn up turn down the averaging. So here what you can see is this is that Doppler spectrum, sometimes called the Jakes spectrum. And you can see here's our dominant tone right at the middle. Oops. And then these are the varying tones. Now there's 8 of these because there's 8 selected in the model, but you can see that this bandwidth is essentially what I'm setting at the top here. So if I reduce that Doppler frequency, right, this gets narrower. This is all still flat fading, but it's frequency varying, and so it causes this content in the frequency domain. So now if we go back here and we switch away from the flat model and into the frequency selective model, you'll see similar. So let's turn up Doppler, K factor, and if we look, and we'll turn this, now we'll do it with noise. And let's turn the Doppler off. And now you'll see that it's non-flat. And that's because that block is introducing time delay before all of those or in between all of those taps. Now, of course, if we turn the Doppler away from 0, it's going to change fast enough you can't really see it, but it is non-flat in there. And it really just depends on how fast you make the channel. But you can see it's non-flat, but it's changing. So, and again, we have the same distribution here. And the same dependence on K factor, but now it's frequency selective. So that's actually going to be the last frequency selective that I show during this demo. Everything else is going to be frequency flat because we'll assume used OFDM or some other technique to flatten out. Okay, so that's how we model multipath. So now we come to MIMO finally. So this is the canonical MIMO drawing, courtesy of Wikipedia. But the idea is you have multiple transmitters and multiple receivers. And so, and when they say MIMO, multiple input, multiple output, it refers to inputs to the channel, basically how many transmitters you have, and outputs from the channel, how many receivers you have. And you, of course, all of them couple to each other, but in varying amounts. And that's the coupling or the path loss, and it's denoted with H. So H11 is from antenna 1 to antenna 2. H21 is antenna 1 to antenna 2. That that's how that works. And now we end up with a lot of matrix math at this point because it makes all of this easier. But so effectively, you have multiple channels between your various transmit antennas and your various receive antennas. But those channels can be correlated, and sometimes they're correlated and sometimes they're not. In general, the further apart the antennas are relative to a wavelength and relative to the physical things that are causing the reflections, the less your gains will be correlated between each other. And of course, if it's free space, everything will be totally correlated because there's no other effects. And we can also get diversity through polarization. Of course, that's limited to two ways, either horizontal, vertical, or left, right. But that can be useful at small numbers. And so the terminology, as I say, there follows the channel. If you're pedantic, SIMO is one transmit, and MISO is one receive. And so now I'm going to show a similar flow graph, except this time it is with MIMO. And so it's really the same flow graph, except we have two of these fading models, and they're completely decorrelated. But then I have this matrix multiply here, which is fed by a correlation matrix. And so when the correlation factor is 1, each output is basically the two signals, the two matrices added together. And when the correlation factor is 0, they're totally independent. And then we again take the complex to mag squared and show the amplitudes versus time. In this, I no longer show frequency because it's flat in frequency. We're not doing we're not doing the frequency selective channels. So it simplifies the display a little bit to not have that second thing. So okay, so here we'll turn up the Doppler frequency, right? And now you can see this is the channel gain versus time versus for the two different paths. So you have signal 1 and signal 2. Now this is with correlation of 0, and the correlation slider is down here, unfortunately. But as I increase the correlation up to 1, you can see they become the same. And then if you're somewhere in the middle, like 0.7, right, you can sort of see similarity, but they're not exactly the same. So you'll never see exact perfect correlation. And in terms of using MIMO techniques, the lower the correlation, the better, because you get more diversity out of it. But in general, you can get useful results, down to moderate correlations of 0.5 or so. And now, if you don't have, if you do have perfect correlation, as if it was free space or some other situation where you happen to have the antennas too close to each other, then you won't get the same level of improvement from MIMO, but you may still. Oh, what's going on here? Okay, so good. So that's basically the modeling of the systems that we're working in now, and so. So that that's what MIMO propagation looks like, and there's other models that are more complicated, but this has really the basics. So in the rest of the talk, I'm going to go through a model communication system, and now this is like a full communication system here, right? You start with source coding, channel coding, modulation, all that stuff, and in some situations you'll have different, you may reorder these blocks, but basically you have channel coding, modulation, you would add your MIMO encoding. Then your channelization, whether it's OFDM, root raised cosine filtering, spreading, whatever it is. And then we have the propagation loss and multipath. And then at the receiver, you get your AWGN, right? And that's why your noise should be decorrelated between the two receivers, because it's really receiver noise. Even if it's thermal noise, atmospheric noise, the antennas, as long as they're not highly directional, large, like SETI kind of antennas, they will have independent noise. When they don't have independent noise in radio astronomy, it's because you're doing, or you're attempting to do interferometry, and you don't want it. You do want the correlation, and that's how you control the direction. But if for our purposes, you can assume the noise is decorrelated here. So then you would do time and frequency sync, dechannel it, and you reverse everything else from the above. So what I'm going to concentrate on today is the stuff that's not blackened there. So we have modulation, MIMO encoding, the propagation, AWGN, and then the decoding and demodulation. We left out the channelization and left out the time sync. I know that's something I've said, you never leave out the synchronization because that's the hard part, but the textbooks leave it out. We're going to leave it out today for our purposes, but it's of course important, but all of these flow graphs have the timing synchronization automatically in there. We still do carrier recovery, but we don't do the timing recovery. So, so going back to MIMO, so why do we use MIMO techniques? First, increased reliability. We effectively get antenna gain. At the very least, we effectively get antenna gain through our MIMO techniques, and we can increase throughput. We get path diversity, more reliability, etc. Why wouldn't we? Well, there's hardware complexity involved. You have to have multiple receive chains, multiple transmit chains. There's significant algorithmic complexity and processing that goes along with it. Sometimes, depending on which MIMO methods you're using, you need to pass channel state information. What this means is the receiver needs to report to the transmitter what the channel is looking like so that the transmitter can act on that appropriately. We'll get a little more into that, but this overhead can actually be significant if the link is bad and you're really trying to optimize your MIMO complexity, and often this CSI feedback is a limiting factor. And now, another reason you might also not want to use MIMO is if you have a free space system, then true phased array beamforming is much easier. You could do it in the analog domain, or the math is easier even if you do it in the digital domain, and you can point beams. And if there's no multipath, you're going to get the same results as if you just did beamforming. So that's easier in those situations. So, so to divide up the various techniques, we have receive diversity, and we'll go over three different varieties of that. There's antenna selection, equal gain combining, maximal ratio combining. There's transmit diversity, where we also have similar options. We have space-time coding, which we'll show an example of that as well, and sort of the true MIMO, the sort of advanced MIMO stuff, where you would have what's called spatial multiplexing or pre-coding, and there's a bunch of other techniques around that, and we'll cover that a little. We don't have a demo of those. And then there's massive MIMO, and I'll cover a little bit of that at the end. So, I've talked a lot about diversity, but what does that really mean? So we kind of intuitively know that diversity in paths means that if one's bad, the other might be good, right? And so we can still communicate in that situation. So, but it's actually it can be quantified too. It's not just this sort of fuzzy concept. And so we have what's called diversity order, and if you're able to extract the full diversity, it will improve your links in these fading scenarios. So this is just a plot of a simple communication system, and you probably can't tell the colors very well, but this line here is the bit error rate for this communication system versus in just a Gaussian channel with no fading. And you can see it has that characteristic rapid drop off as the SNR increases. And so it just takes a little bit of increased SNR to radically drop your bit error rate. But when you have a faded channel, it turns out that it's not. You lose that steep slope. And now why is that? Right? We're basically saying that whereas before a 1 dB could give you a huge drop off, now it takes many dB to get the same kind of drop off. So why is that? Well, if you have fades of 30 dB, then adding one, that are 5% of the time, let's say, adding 1 dB, well, maybe you'll have those fades, 4.9% of the time, right? You won't get the same advantage. It's almost like you have something, it's effectively binary, either the channel's there or it's not. And so you get these deep fades, and thus you have to add lots of SNR in order to really get the low bit error rates, right? And this is the primary problem of fading channels. And this becomes, rather than this sort of logarithmic drop-off or exponential drop-off, becomes a very linear drop-off. So, so what happens when we add diversity? So if we can get full diversity of order 2, then you can see we can go from here to this line. Now, what is this saying? This is saying if there was maybe a 5% chance of one of these deep fades that you can't deal with one antenna, but if they're totally uncorrelated, well, the chance of them both being deeply faded at once is 0.05 times 0.05, right? It becomes a much smaller number. And so the more diversity you have, the closer you can get to the ideal curve, right? So this is with 2, this is with 4. Now you can get this diversity on the transmit side, on the receive side, or you can get it as a combination. But diversity 2, you should think of as it's 2 receivers or it's 2 transmitters. Diversity 4 could either be 4 receivers, it could be 4 transmitters, which is less common, or you might have 2 of each, right? But as the numbers go up, your diversity is basically how many independent paths you have. So, right, the chance of all 4 of those, if they're totally independent paths, being deeply faded is extremely low, and that's what we're showing here. So, so that's what we mean when we talk about the diversity number. And if you're good at your mechanisms, whether you're doing selection or equal gain combining, if you do them right, you'll get that full diversity. So. So here I list 3 different mechanisms to achieve diversity. One is antenna selection, which in code is just, take the stronger of A or B, right? So it's pretty easy, and actually usually, and that's what my friend's parents' car had when I was a kid. But it's really easy, and typically if you're doing this, you're usually doing it entirely analog. You're not doing it in code like this, because if you've gone to the effort of getting 2 signals into the radio, you wouldn't bother using this method. But if you have, say, 2 power detectors, you can rapidly switch between the 2 signals, and that's what their car radio was doing. And you kind of have to track the carrier, because when you switch between the 2, it'll glitch, and if it's FM, you hear a little click, but in general, it's a very easy system. Then we have what's called equal gain combining. You just add the 2 together. Again, you have to track the carriers, or if you add them together, they won't line up. But if you're tracking both carriers and you add them, that improves the signal, because you're adding the signal from both of them, and they add in power. They add in voltage, which is better, and the noises will add in power, and so you will get a net gain there. And so that's equal gain combining. Then there's maximal ratio combining, which is provably optimum, where the stronger where you add them, but you apply gain to the stronger signal, not the weaker one. So if one is twice as strong as the other, when you add them together, you first multiply that one by 2, and that emphasizes the stronger one. And it turns out that's the exact same math that happens in beamforming. And so, except this is sort of adaptive, so you don't have to know I'm pointing in this direction. And in multipath, it doesn't form like a direct beam, but it's effectively the same thing, and you're beam forming, and so you get 3 dB of antenna gain if you do this. You get almost 3 dB probably if you're equal gain. It depends on the statistics, but maximal ratio will get you the full 3 dB if there's no fading. So even if there's no fading, these are useful because you're collecting twice as much energy, right? You have 2 antennas, so you have 2 buckets, and you can add that energy together if you do it properly. But when there's, of course, multipath, then the benefit is much larger, right? And so that's what I'll show in a moment. But again, maximal ratio, you not only have to track the carrier, you have to estimate the SNR, which is actually not always that easy, especially at low SNRs. So I'm going to show a flow graph that demonstrates that. Actually, before I show that, I'm going to show my tabs got rearranged here. So I'll just show the blocks I made. So equal gain combining is easy, right? It comes in, you add them together. It's already carrier synchronized before this, right? So this one was very straightforward. Selection combining, it's a little more complicated in the flow graph because I tried to do it without writing code, and it's hard to find something that will say, oh, this one's stronger, pick it. So, but effectively all this, math in there is just figuring out which one is stronger. The argmax block is doing that, and then we're choosing which one to pass through to the output. So that's selection combining. And these are both, I'm doing all two-way here, but all these can be, increased to four-way, eight-way, however many you want. And of course, selection combining will continue to lose to the others because the others are actually adding all the energy, where this is just picking one and you won't get any antenna gain, you'll just get the diversity. And then we have maximal ratio combining, which is the most conceptually complex and algorithmically complex, but it's the block diagram's a little bit simpler. But essentially we're measuring and then averaging the incoming signal levels and then multiplying those signal levels times that. Now, you also really are supposed to track the noise, but the noise is, in these situations, the noise is the same. So it simplifies it a little bit. Ideally, this would be written just out in code, but this is I kind of like to see it as a flow graph, right? So we have the two signals coming in, and they pass through these multiply blocks and added together, and then they're scaled by the sum of the powers, and then comes out, and then this stuff up here is just the power estimation, the SNR estimation. So here's the flow graph that uses this. So we start with just a audio source. It generates, it converts to bits, right? We convert those bits to plus and minus one. So this is all BPSK. All of this works BPSK, QPSK, QAM, whatever. But we're doing all BPSK here today. And now I put a little bit carrier in here because we have to estimate the carrier. We have to synchronize. So I add a carrier by muxing in some ones. Every eight useful bits, I have one bit of pilot. And so we send that through this correlated Rayleigh channel. Same thing goes to both of them, but it's two different channels. So this is transmit. This is over the air. And then on the receivers, right, we have two receivers. So we demux the carriers, and the carriers go into these carrier regeneration blocks. The carrier goes into the carrier regeneration block, which we then multiply conjugate to take that back out of the signal, and so we've transformed back to DC. And then we put it through the three methods: equal gain, maximal ratio, and selection combining. And we can output it to audio, but we can also show the constellation. And I'll show the 5. It's easier to see on the 3, but we'll start with the 5, and then but the display is pretty busy. So anyway, so going back here, we also show the direct paths without the as if you just had one reception. So we'll run this. And so we can add noise here, right? We can add more noise or less, so this is a decent amount. Doppler will change the channel, and you can see it moving around. We'll leave it there. We can correlate it, and you can see how, let's turn the Doppler on, and I'll also turn the K factor down. Right, so here we've got multipath. Now, you're seeing 5 things there, right? So path 1 is blue. Now, you don't really see the blue much because it's followed by the selection a lot. But path 2, and then the green is equal gain combining, and the purple is the maximal ratio combining. So you can see even when like the blue fades and the red doesn't, or the red fades and the blue doesn't, the green and the purple stay pretty good, right? And let me make that a little worse so you can see it better here. Right, you can see everything's moving around, but the green and the purple move around a lot less. It's a little hard to see here, but so I'm gonna switch over to just show 3 of them at once. And I think this is equal gain combining. Yeah, so this is the equal gain combining. Okay, so now you can see. Let me turn up the Doppler. It's changing, and the K factor. Right, you can see that. Sometimes the red is bad, sometimes the blue is bad, but the green is always pretty decent, except when both the red and the blue go into the middle, right? But now if we were in a correlated setup, where the two antennas are too close to each other and they're no longer independent, the green fades with it, right? So we no longer get our diversity, and the green is staying there. Now, I'm going to turn the Doppler down just to make this display real. Now, one thing you can see is, if I can turn this down, there we go. If we zoom in, or actually maybe in too far in, you can see here it's kind of subtle, but the red and the blue are further out than the green. And that's the 3 dB you get from the antenna gain in the fully correlated case, right? Normally, if we had selection here, and the selection would just go out as far as the red and the blue did, right? Because it would not be combining the energy of the two. But here we combine the energy and we scaled it back, and that's why you see that the green is better. So that's our antenna gain in the case of no, essentially the no multipath. Right, now let's go back to the Doppler, and right, and you can see it's still, even when they're together, sorry, in the case of full correlation, even when they're together, the green is better, but when there's no correlation, right, you get the much, much better setup. Does anybody have any questions on any of that to this point? Okay, good. So that's the correlation. That's the received diversity, and now I'm just going to I'm gonna switch this over to audio, so it's not just the constellation display, but it's audio. So I want you to listen closely so you hear the effects of the fading over time and how it affects the audio. So you can see actually if we turn up the correlation and we make the fading bad, as it drops out, you'll hear, and of course we have too little noise here. If we get more noise, you'll start to hear it click. But that's pretty good there. That's with high correlation. Or here, I should do it like this. So that's a lot of noise, and so right, you're starting to hear it go bad there, but it's still here. You can still hear it. But when we turn up the correlation, right, you lose it, right? Because what we're having there is again, when it's not correlated, we get the gain of the diversity gain, and when it is correlated, you lose that. You still get your 3 dB of antenna gain, which is why we were able to go to such a bad SNR and still hear it. So okay, so that was receive diversity. So now let's go to transmit diversity. Okay, so now transmit diversity is actually incredibly similar. You have antenna selection, which you choose, and again you get no gain because of that. No power gain, no diversity gain, no antenna gain, but you do get diversity gain. The downside of this versus the receive stuff is that the receiver has to tell the transmitter which is the better antenna at any point. So the higher the Doppler rate, the more bits per second are wasted in the reverse to tell the transmitter which antenna to choose. But it's it's 1 bit. But now if the channel is very slow, that you could send a bit every every second or so, right? Whereas if it's very fast, it has to be quicker. And at some point, it changes quicker than your latency of the link, and you can't do that. And it doesn't provide any gain. The other choice is maximal ratio transmission, which is really is the reverse of MRC, and it gives the same diversity gain, but which is transmit beamforming, and so it provides antenna gain. So again, if you were to measure this, you would actually, if you were to look at it in free space with the 2 coefficients, you are effectively pointing a beam. Now with only 2 antennas, it's not much of a beam, right? But you're providing gain in one direction. And if it's more antennas, it would be a finer and finer beam. Now, if there's other techniques beyond this, both for MRC and MRT, sometimes if there's interference rather than just noise that you're worried about, it can be better to sacrifice a little bit of gain that you get from MRC or MRT, which is the maximum gain. Sometimes you sacrifice a little bit of gain in exchange for putting a null on the interferer. Now, if it's just Gaussian noise, there's no concept of that because it's, it's uniform. But if there is an interferer that you want to get rid of, you can use these, and they're called zero forcing techniques, but it's essentially just pointing a null in the direction of the interferer. And you can point one null for every extra antenna you have. And so, but that's, of course, certainly in the case of TX diversity needs a lot more channel state information, right? The MRT, and that would require a lot of CSI. But often, like cell phone systems have used this for quite a while. Even Wi-Fi will sometimes use channel state information depending on the mode, and so that the transmitter can, point the signal where it wants. Okay, so next we come to space-time coding. Now, the great thing about space-time coding is that it doesn't require channel state information at the transmitter. Yet the transmitter can do MIMO with it. And so what this means is because it's no channel state information, the transmitter doesn't know how to point the energy in the right direction. So there's no antenna gain from this, but you still can get the diversity gain. And so the way you do that, the easy way, the first way that was discovered to do this is called Alamudi coding, and the general family of these things is called space-time block coding, or if you do it in OFDM and you put, rather than, so space-time block coding means the code symbols you do sequentially, so A then B, A then B. Whereas space frequency block coding would mean you just put them on adjacent carriers in the in your OFDM, but it's the same math. And so, and you could actually do it in CDMA. I've never seen anybody actually do it, but there's no reason you couldn't. It's two orthogonal signals. You can just do that in the coding domain as well. So anyway, Alamudi coding is as close as you get sort of to a free lunch in comm systems. You get, but if you have only two antennas, you can do full rate, which means you don't give up any data rate, and you don't widen your bandwidth, and you get the same data rate through, and it's fully orthogonal, which means you would get the full diversity gain of the system, and there's no impact of one symbol on another. It's been extended beyond two antennas, but you have to give somewhere. You either have to accept reduced orthogonality or reduced diversity, or slow down the data rate so that you can do this, because it doesn't perfectly scale. But there are some versions that go up to like 4 antennas, 8 antennas. Like Wi-Fi has I think a 4 and an 8 antenna, or 3 and a 4 and maybe an 8 antenna version in there. So, but you give up a little. But in any case, the idea is, if you look at this matrix, you have C1 and C2, which means that so the columns are your antennas and the rows are your time slots. So let's say I have 2 bits that I would normally send, called C1 and C2. I would send C1 and then I would send C2. So instead, I send C1 and C2 at the same time, but on different antennas. And then the next time period, I send the negative conjugate of C2 from the first antenna and the conjugate of C1 on the second antenna. Now, what this means is that each symbol is going on both antennas, but it also means you have two bits in 2 times, and so we don't lose any data rate. That's why this is called a full rate code. So what this does is now the receiver gets a picture of both signals coming from across both paths. And so there's a sort of a matrix inversion you can do that gets the symbol separated again, right? Because they're mixed here, but then you would get it separated again, and be able to separate them at the receiver. So I'm going to show this. So we can do, this is the Alamudi encoder, which is basically just that matrix, that matrix that I showed you, where you source in. I multiply by half, right? Because you don't want, cheat. You have if you have 1 watt on one antenna, you have to go to half a watt on each to make the math fair, right? Now, if you happen to be limited by antenna power, then by amplifier power, then adding a second one gets you more power. But that's cheating in the comm system sense, right? You have to divide the power equally between the two. So we separate the streams, and so we take we do the math. on them, and so you take pairs of symbols essentially that come out of the 2 ports of the stream to streams. One goes back in and is and then the other is basically this does the math on it. It does that complex conjugate and takes the so the C1, right? So this is easier if I do it this way. So C1 would come out here and would come out the first antenna at the first time period. C2 would come out the second antenna at the first time period. And then the processed ones cross, right? You cross the streams here, it's allowed in this case. Complex conjugate, and then you multiply by -1, and this one's just complex conjugate. And those become the second symbol on the 2 respective antennas. So that was easy to do in GNU Radio in using hierarchical blocks. The receive is more complicated, and I just went to math in Python for that. So first we have to estimate the channel. So this is just a Python block. I don't know if you can see it, but basically we have the constructor, and we just have this matrix that is the known symbol that we send in the pilot, right? So we just send a 1-1 in the pilot, and that gets Alamudi encoded along with all the data. And so here this is the matrix that we're going to need to invert it, and then every time we receive, we basically multiply by the inverted thing, and that tells us what the channel coefficients are from the 2 antennas to R1, right? Remember, this is single receive in this example. And then the actual receiver then takes those estimated channel vectors, channel coefficients. It makes its own vector out of them, inverts that, and then that gets multiplied by the incoming signal, and then that comes out. And so if we look at that in the Alamudi demo, right? So we again have our data source. We go to the Alamudi encoder, and we have channel gains for the 2 separate channels, and then we add in noise. And then on the receive side, we're demuxing out the pilots, right? So the pilots get demuxed out. They go to the estimator, and it has an alpha, so you can average the estimates over time periods, although I didn't implement that part yet. So it's not averaging them. So you'll see the noise grows a little bit, and I'll point that out. And then we display the estimates, and then it goes into the receiver. The same estimates go into the H path on the receiver, and the data comes into the in path on the receiver, and it demodulates it and comes out, and it'll show it as as a constellation. So turn the noise down a little bit. So here you can see this upper one is this is the estimates. So here I'm setting the path gains, right? And you can see it's estimating the path gains. That's H2, that's H1, right? And you can even if you have one path gain is off, right? Essentially you disconnected one antenna and you only have signal coming through the other, there's still enough information there for the receiver to receive it, right? That's I unhook the antenna version, or I've got two uncorrelated paths and one is incredibly bad, right? So you could still receive it. You won't get the improvement in that case, but at some other time, then a different one will go to 0. Now, if I happen to pull both of these to 0, the flow graph dies because it's a singular matrix, and I need to catch that as an exception. But you could see what it does here, and then down here you could see the blue is what comes into the antenna, right? And you can see it's got this weird point in the middle. That's because we're summing both signals coming in, and so so sometimes one's positive, one's negative, and they go to the center, right? So you obviously can't just decode. You have to do the math to decode it, and that's what the red is, right? But if I were to change this, you could see that, right, the 2 different paths have 2 different gains, and that's why the blue sort of bifurcates like that, but the red stays correct because it's estimated. Now, I'm going to turn the noise up a little. So now and I turned the noise up, and now as we drop the amplitude of the path gains, right, you're going to see that it all gets equalized. So the red signal amplitude stays the same, but the noise amplitude grows because, right, we have worse and worse channels, right? But what you see is when one is really bad and the other one's good, we've got a good signal. And if the other one's really good, we still have a good signal. But as they both approach 0, that's when it goes bad. So obviously when you have the really, if it's either highly correlated or they both happen to go to poor paths at the same time, that's when the diversity is not sufficient. And it's not magical, it's not going to decode a signal from nothingness. So that's the Alamoudi demo. Any questions so far? Okay, almost done here. So that's the space-time coding. I didn't, there's the more complicated versions with more antennas, but that's, the same basic concept. Now, I don't have demos for the rest of it, but we'll talk a little bit about the more advanced MIMO stuff. So the first technique is called pre-coding, and this is basically the transmitter is able to, yes, 5 minutes? Okay. So in this method, the transmitter knows what the receiver channel is, but there's multiple antennas on each side, so the transmitter has to know all of those coefficients. So if the transmitter has 4 antennas and the receiver has 4, that's 16 coefficients that have to somehow be communicated to the transmitter. But once it knows those coefficients, it's able to do, and usually it uses a singular value decomposition to do this, but you're able to figure out which what sort of pre-coding matrix, what to multiply the transmitted signals by in order to send energy to particular paths. And so you can effectively create the minimum of the M and N parallel channels here, right? And you can direct energy to each of them that will be coherently received at the other side. And this other side still has multiple antennas so that, because there's separate channels that may land on one or the other. And so it also gets diversity. But you can, also in a frequency selective situation, it may also be doing this in the frequency domain, and so it's directing energy not just to particular paths physically, but also into particular frequencies, right? So if you have one frequency with a null, there's no point in sending energy there. So pre-coding will put it in a band that's good. So that's how you could take advantage of the improvement of the SNR. When the fading is in your favor, right? When it goes above the 0 line, this helps you take advantage of that. So this is more complicated. It's, and I have some Python code that does it, but it doesn't work. It didn't get it into the demo. But this allows an increase in the bit rate, both because you have stronger channels and also you have multiple channels, right? You can send multiple things at once. And this, of course, can also be used with what's called multi-user MIMO, where you're sending different things to different users at the same time. Again, by having different pre-coding matrices to transmit to each one. So of course that needs a lot of CSI. So the final technique that I list here is called spatial multiplexing. And the advantage of spatial multiplexing is you don't need any channel state, and the transmitter can essentially just sends a separate stream on each antenna. And it's up to the receiver to figure it out. And this is also, there's modes for this spatial multiplexing in Wi-Fi as well, in the newer ones. And so if you have 8 antennas on the transmitter and 4 antennas on the receiver, you can send 4 streams to that user. If you have 8 on each end, you can send 8 parallel streams. Now, it turns out that even if there's a lot of multipath, you don't really have 8 good channels, or if there's 8 and 8, you'll have some number less than that. So typically there's like one super strong channel and then some others. But with spatial multiplexing, you can't choose that, right? So you have to sort of code across it. Whereas with pre-coding, you can choose, this one channel's really good, I'm going to put all my energy there, and this other channel is not as good, I'll only do BPSK on that channel, or something like that. So spatial multiplexing really, on the other hand, leaves it up to the receiver to decode, and this is where you hear about sphere decoders and things like that. Essentially, the receiver has, if there's 4 transmitter antennas and 4 receive antennas, and all signals are sent at the same time, on each receive antenna, it'll receive all 4 of those streams, but because it has 4 pictures of it with different relative phases on each, if there's enough multipath diversity, it's able to decode that and separate them. But certainly it would be always advantageous to use pre-coding if you had the CSI in order to do that. But of course, that's not always available. So the final technique is massive MIMO, and this is a picture I've used many times as a setup at the University of Lund in Sweden, where they had 64 X310s, which each had 2 antennas. So it was 100. Was it no? Yeah, it was a 128-way MIMO. And in massive MIMO, typically it's not 128 on each side. It's a 128 or 64 or 32 on one side, and then it's like a handheld with 1 or 2 antennas on the other side. But what you have here is you have this continuous CSI feedback, and the antenna is essentially attempting to invert the channel so that it can put a beam right at one user. Now, these beams may not be sort of a fan beam, like a directional beam like you're thinking of when I say beam. It can actually be more of a cloud, right? If there's very diverse multipath, it won't be a straight path. It will be, everything combines coherently here, and even right behind it, it might not. And so as you move, it has to keep adjusting. So there's a lot of CSI to do that. And so I call that eigen beamforming versus conventional beamforming. But again, if there's no multipath, this would just sort of collapse down to a phased array antenna. And there's a couple of methods. MRC and MRT just aim as much energy as possible to a certain point. But then there's also zero forcing or null steering, which also tries to make at one user it sends a cloud to them, but also nulls out every other user's signal at that place. And so that's a lot more computation, and so there's a big pile of FPGAs underneath that does all of that all those combinations in this. But you're able to effectively create individual clouds for each user, and it just as they move around or as the channel changes, you have to keep adapting. So unfortunately, we don't have a demo of that. That's wouldn't fit in the overhead. So anyway, that's what I've got on MIMO. Are there any questions? Silence. Okay. Well, thank you. Oh, Balint and I are hiring at Apple. If anybody, certainly anybody with GNU Radio experience or software engineering, comm systems, protocols, we would love to talk to you. Okay.
So we have one last talk for the day, and then we'll be wrapping up. I will preemptively remind folks that at 6 o'clock in the atrium, there's going to be a social there. So please do come along to that, but you have an hour between this to rest, relax, put your bags away, and come back ready for a little bit of food.
That, and so I call that Ivy.
Yeah. Okay, well, thank you very much, Derek, and excuse me. Thank you very much for everybody staying around until this very quick talk. I know that I'm between you and your refreshments, so I'm going to be really quick. So I'd like to speak to you very briefly about the GNU Radio UX group, who we are and what we can do for you. So firstly, a quick introduction to myself. I'm Bernard. I'm a user-centered designer, licensed ham operator, ex-telecoms engineer, a GNU Radio companion newbie user, and an open source contributor. How have I found myself here? Well, earlier this year at FOSDEM 2021, Derek came to our open source design track and put a call out looking for UX designer contributions to GNU Radio Companion. As somebody with an interest in radio and an ex-career, I was really interested. I'd used GNU Radio Companion before, but I thought it was for beyond my level of understanding. So I contacted Derek and said I was interested in contributing, and that's how I've found myself here. So UX, user experience, that's all about logos and making things look nice, right? Well, user-centered design is much more than just logos. It is about understanding what the user of the piece of software needs to do, understanding the tasks they need to do, and understanding their context of use. So UX is from the bottom up here, it's exploring and understanding the user's needs, the problems, the context, the functional specifications, understanding what the software needs to do for this user or these users, deciding on the structure and the behavior of the software, then deciding and designing how the software looks, and then finally, on the very top, logos, graphic design. This is the bit that interests me. This is the bit that I'm reasonably good at. I'm interested in understanding how the software works for the user, what they need to do with it, and then actually creating designs to make that software work for the user. What can the UX group do for you? Well, we can help maintainers and developers learn about their users. I can tell you not everybody is a DSP or an RF expert. Designing UI for some new GRC functionality that you want to implement, and actually carrying out some usability testing of that functionality. It doesn't have to be fully functioning working software. Non-functional prototypes work really well when we're trying to validate designs, and then helping maintainers, developers, and users identify areas of GRC that cause usability issues for users. Again, focusing on people that are not GNU Radio experts. This isn't about simplifying or dumbing down GRC. This is about communicating to the user what it is they have to do, maybe why they have to do it. This is about educating and about helping the user learn about GNU Radio. So some of our contributions so far. First of all, we created the UX studies group. So far, we've got about 30 or 40 people who have signed up to be involved in our UX studies. This is anything from doing a short interview, understanding a little bit about their background, understanding how they use GRC, what they use it for, straight through to doing some designs and some validating those designs with users. With Derek, I created some PR and some feature request and bug report templates for the main GNU Radio repo. Why is this important? Well, it's helpful to try and create some templates for people so that they know what maintainers and what developers are looking to get from them when they're reporting a bug or when they're reporting a feature request. I did a really quick GRC iconography review, essentially what each of these icons in GRC means to a new user. Quite a lot of them are really confusing, even to established and experienced GRC users. Also, the final thing then so far was exploring possible ways to improve the create new flow graph UI in GRC. So I did a really basic prototype, non-functional prototype design, and then did some usability tests with users of different levels of experience. So if my technology works, I should be able to show you just a really quick animation of the design. This is going to take longer than I'd hoped. Essentially, what this should show is, as I said, some non-functional design prototypes, which I tested with 5 users, varying degrees of or varying levels of expertise, trying to improve the situation of having to, first of all, save the GRC before you can then run it. This is a usability issue that trips up a lot of new users. And essentially, the idea of the design was to create a temporary GRC file that would allow the user to basically bootstrap the execution of the GRC, and then if they wanted to keep it, they could then save it to their directory of GRC files. This is taking much longer than I'd hoped, so I'm going to skip this. Essentially, okay, what next? So the idea, first of all, is to iterate on this GRC, iterate on the create new GRC flow design, and then publish the results of the iteration of the design and the results from the usability testing for community feedback. If anyone's got anything else that they really think needs some usability improvements, drop me a line, Bernard at EI8FTB, or I'm Bernat, B-E-R-N-A-T, on the GNU Radio channel on Matrix. And finally, if I can ask as many people, please sign up to the UX Studies group. The more people we have, the more people we can do user research and UX studies with. Link at the bottom. And I think that's it. Thank you for your time, and I hope you all have a nice, enjoyable refreshment.
Are there any quick questions here? Otherwise, questions could be taken in chat. As Bernard said, he is active on the chat. Seeing none, thank you very much, Bernard. And I believe you have a working group session on Friday as well. So hopefully some people will drop along for that, at least as part of the GRC session. So thank you.
Super.
For folks who are here, please, yeah. Great. I have very few notes at this point. As I said, there's going to be a social starting in just under an hour in the lobby. Please do come along to that. Otherwise, we'll be starting up again at 8:45 tomorrow with our opening notes, followed by the keynote from Yosis HQ on open source FPGA tooling. And that's a discussion with a variety of the open source FPGA tooling authors and experts. So definitely something to look forward to. Have a good social, have a good night, and we'll see the stream tomorrow.